Mhm. Hey guys, good morning, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. Yes. So guys, let me know in the chats quickly if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible and visible to everyone. Good morning, people. Good morning and welcome back. Good morning and welcome back. Good morning and welcome back. So, my dear students, I hope you know, till now we have taken 2 marathons. I have taken one, KK sir has taken one, and your, I would say, class 11th chemistry is completed except 2 chapters, periodic classification and thermodynamics, right? Today it's going to be the marathon of your class 12th chemistry, right? Today it's going to be the marathon of your class 12th chemistry, and let me tell you what all chapters will be taken in this particular marathon. My dear students, will be doing solution, we'll be doing kinetics, we'll be doing electrochemistry, haloalkanes haloarenes, alcohols, phenols, ethers, aldehydes, ketones, carboxylic acids, right? Similarly, we'll be taking care of amines as well, right? So 7 to 8 chapters will be done in the today's session. Well, 3 chapters will be still left. One is going to be DNA block, one is going to be your coordination, and one is going to be your biomolecules. Okay? So in the today's session, 7 to 8 chapters will be done. That will be basically your, I believe, 80% of your chemistry of class 12th. So 80% chemistry of class 12th will be done in the today's session. And the PDF of this particular session, the handwritten PDF, I'll be sharing on my Telegram. Okay? The name of the Telegram channel will be, you know it already, Wasim Bhatt Chemistry Official. WASSIMBHAT Chemistry Official is the name of the Telegram channel on which I shall be sharing the handwritten PDF of this particular session. Well, a lot of students are asking about the duration. I have no idea what is going to be the duration of the session. It will be 10-12 hours. Yeah, 10-12 hours for sure. Okay. Well, it is the combined marathon of me and KK sir. Firstly, I'll be doing some chapters, then KK sir will come in and he'll be doing some chapters. All right. So is everyone ready? Is everyone ready? Let me know in the chats quick. Is everyone ready? Also in the today's session, your stereochemistry will be also done, okay? I forgot to tell you that. Stereochemistry part will be also done. And by the way, tomorrow at 8 p.m. Tomorrow at 8 p.m. Maybe it'll be tomorrow or day after tomorrow, okay? I'll show you something. Just a second. My dear students, tomorrow at 8 p.m. Well, it might happen day after tomorrow as well, okay? Tomorrow or day after tomorrow. Stay tuned to the channel though. There is one important session which I'm taking, that is most predicted paper of chemistry, NEET 2026. Okay? And tomorrow it's Yavar sir session. He'll be taking your complete class 12th physics in one session, right? Do join this particular session as well. So these are very important sessions, I must say, right? Which we are planned for you guys on this channel for the upcoming 2 days. Okay? So tell me, before starting, which part of the country you guys are watching me from? I just want to know that. I just want to know that first. Would you stop spamming, okay, and focus on the session now? Focus on the chapters which we have planned for you guys on today's session. Okay, tell me quickly in the chats. I just want to know which part of the country you guys are watching me from. Someone is watching us from North Korea, is that? All right, Tamil Nadu, Gujarat, Karnataka, Bangalore, Andhra Pradesh, Kashmir, UP, Telangana, Goa, AP, Kerala, Bihar, Maharashtra, Delhi, Tripura, and Dubai, Haryana, Delhi. All right, Hyderabad, Nagaland, Jharkhand, Rajasthan, Gujarat, Manipur, Pondicherry, Chhattisgarh. Okay, amazing, great. Hello guys, let's get going then. Let's get started. Okay, let's get going. Let's get started. So my dear students, the first chapter which we are going to do in the today's session, that's going to be your chemical kinetics. Okay, the first chapter which I'll be starting with, that will be your chemical kinetics. So my dear students, before starting the chemical kinetics chapter, you should first of all know from which topics questions will be asked. From which topics questions will be asked in the chemical kinetics chapter. You should know about that first. Let me tell you, my dear students, the first topic from which question comes in chemical kinetics, that is simply the rate of the reaction, which includes your rate of disappearance, rate of appearance, rate of reaction. Number one, this is the first topic from which question will be asked. Number two, question will be asked from order of the reaction. Question can be asked from molecularity of the reaction. Then comes your experimental determination of order. Experimental determination of order, this again one important topic. Then comes your zero order reactions. Then comes your first order reactions. And my dear students, at the end, it's going to be Arrhenius equation. Well, these are the topics. These are the topics from which questions are asked in the chapter chemical kinetics majority of the times. I would say all the times basically. So these are the topics which we shall be covering in detail in this particular session. Okay. So first of all, from the chemical kinetics chapter, these are the topics from which questions will be asked in your upcoming NEET examination. And my dear students, without wasting a lot of time, let's get going. Let's get started with the first topic of your chemical kinetics. What is that? That's going to be your rate of the reaction. That's going to be your rate of the reaction. So I'll just choose a color over here, just a second. Okay. So the first topic, my dear students, with which I'll be starting, that is going to be rate of the reaction. A rate of the reaction as per stoichiometry. A rate of the reaction as per stoichiometry. Now you must be thinking what this topic exactly is all about. Well, from this particular topic, questions have been asked, questions will be asked in the NEET examination for sure. Okay, so try to understand what this topic exactly is all about. So first of all, my dear students, I'm going to take a balanced chemical equation here. Let's say you have got the balanced chemical equation as N1A plus N2B. It gives N3C plus N4D. Imagine this is a balanced chemical equation in which this N1, N2, N3 and N4, these are the stoichiometric coefficients. These are the stoichiometric coefficients of your reactants and products. These are the stoichiometric coefficients. These are the stoichiometric coefficients of your reactants and products. N1, N2, N3, N4. Now, my dear students, you must be knowing one thing. When the reaction starts, the amount of reactants that decreases with time, and amount of products that increase with time. You must be knowing about that. When the reaction starts, amount of reactants that decrease with time, amount of products that increase with time. So can I say reactants disappear with time? As the reaction starts, I would say reactants, they disappear with time, and products, they get formed with time. So the first thing, my dear students, which I'm going to discuss with you, what is that? I'll be talking about the rate of disappearance. I will be talking about the rate of disappearance. Since I used the term disappearance and your reactants, they disappear with time. So I'm talking about rate of disappearance. Rate of disappearance term will be basically for reactants. Rate of disappearance will be for reactants. The first reactant which you have here, that is A. So I would say rate of disappearance of A. How do I write it? Rate of disappearance of A. How do I write it? Since I use the term disappearance, so I'll be starting with minus sign. Then I'll write change in the concentration of A divided by time interval delta T. This particular term, minus delta A by delta T, this is what you call as rate of disappearance of A. Similarly, for example, I need to write rate of disappearance of B. How will I be writing it? I'll again start with minus sign because I'm using the term disappearance. Then I'll write change in the concentration of B divided by time interval delta T. Right? Similarly, my dear students, if I write rate of appearance, if I write rate of appearance of what? Rate of appearance of C. Since I'm using the term appearance, so I'll start with plus. Then I'll write change in the concentration of C divided by time interval delta T. And in the similar way, if I write rate of appearance of D, I'll again start with plus, change in the concentration of D divided by time interval delta T. So my dear students, this is how you write rate of disappearance of a reactant and the rate of appearance of the product. Right? Perfect? Perfect, people? Perfect? Now, my dear students, try to understand one more thing. There is a term called as rate of the reaction. There is a term called as the rate of the reaction. Rate of the reaction. How do I write rate of the reaction? How do I write rate of the reaction? My dear students, if I talk about the rate of the reaction is written as the rate of, it is written as the rate of disappearance or appearance. Rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient of a reactant or product. Rate of the reaction. How do we write it exactly? How do you write it exactly? Rate of the reaction is nothing but rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient of reactant or product. Now let's try to understand what exactly it means. Let's try to understand what exactly it means. My dear students, have a look. I'll write rate of the reaction. Let me tell you, you can calculate rate of the reaction with respect to any reactant or any product. You can calculate rate of the reaction with respect to any reactant or any product. My dear students, let's say I need to calculate rate of the reaction with respect to A. With respect to A. Since A is the reactant, so I'll write rate of disappearance of A divided by stoichiometric coefficient of A. I'll write rate of disappearance of A divided by stoichiometric coefficient of A. What is rate of disappearance of A? That is minus delta A divided by delta T. Divided by, what is stoichiometric coefficient of A? That is N1. So I can write it like this. Minus 1 by N1, change in the concentration of A divided by time interval delta T. Okay. My dear students, this particular term, I will be calling as the rate of the reaction. This particular term gives me the rate of the reaction. Right? Similarly, I can calculate rate of reaction with respect to B as well. Right? B is also the reactant. I'll write rate of disappearance of B divided by stoichiometric coefficient of B. So I'll get finally something like this. Minus 1 upon N2, change in the concentration of B divided by time interval delta T. Similarly, rate of reaction with respect to C. Now C is the product. For products, what do we write? Rate of appearance. So I'll write rate of appearance of C divided by stoichiometric coefficient. So finally, I'll be writing it as 1 divided by N3, change in the concentration of C divided by time interval delta T. Similarly, rate of reaction with respect to D, it's going to be plus 1 upon N4, change in the concentration of D divided by time interval delta T. Let me know first of all in the chats if it is clear. Who is this NEET D4? Sir, please cover NCRT. So what am I teaching? Am I teaching some PG level or something? Would you stop spamming or you'll get blocked? Okay? Do not spam. Do not spam. If you want to spam, go to the other channel, not here. Okay? This is not something which I'm teaching from your PG level or PhD level. This is your NCRT only. So don't teach me what to teach. Okay? Just focus on the session, note down everything. That's it. That's more than sufficient for you. All right, people. So till now, I discussed three terms. One is called as rate of disappearance, one is called as the rate of appearance, and one is called as rate of reaction. One is called as rate of reaction. All right. Perfect. Now, people, let's see exactly what kind of questions can be framed out of all this. For example, this is the first question which is on your screen. This is the first question which is on your screen, which can be solved from the concept that I gave you right now. Firstly, people, you are given with a reaction, okay? You are given with a reaction. And in the question, they have mentioned rate of appearance of O2. Rate of appearance of O2. First of all, tell me, how do I write rate of appearance of O2? My dear students, O2 is your product. I'll be starting with plus sign. Change in the concentration of O2 divided by time interval delta T. This is the rate of appearance of O2. And as per the question, it's given to me as 0.5 moles per liter per second. Okay. What am I supposed to calculate? I am supposed to calculate the rate of disappearance. Rate of disappearance of what? Rate of disappearance of N2O5. Now tell me, how do I first of all write rate of disappearance of N2O5? I'll be starting with minus sign. Then I'll write change in the concentration of N2O5 divided by delta T. This value I'm supposed to calculate. This value I'm supposed to calculate. Now, my dear students, tell me just one thing. Tell me just one thing. What would be the rate of the reaction with respect to N2O5? I would say rate of the reaction with respect to N2O5 will be equal to minus 1 divided by 2. Minus 1 divided by 2. Change in the concentration of N2O5 divided by delta T. Similarly, tell me what would be the rate of the reaction with respect to O2? I'll be starting with plus 1 divided by, stoichiometric coefficient is 1. Change in the concentration of O2 divided by time interval delta T. Right? Simple. Simple, people. Rate of the reaction with respect to N2O5 is this much. Rate of the reaction with respect to O2 is this much. Correct? Now, if I do one thing, I'll just cross multiple. That means I'm going to take this 2 over here. It becomes minus delta N2O5 divided by delta T will be equal to 2 times. 2 times what? 2 times plus delta O2 divided by delta T. Now you tell me, if I write 2 as such, delta O2 by delta T is given to me as per the question, that is 0.5. The value comes out to be 1 mole per liter per second. My dear students, what do I call this particular term as? Look at this carefully. This particular term I'm calling as the rate of disappearance of what? N2O5. This is something which you were supposed to calculate. Yeah? Am I clear, people? Am I clear? Did you understand how do we exactly solve such kind of the question? Did you understand? So first of all, whenever you are asked to calculate disappearance, appearance, or even rate of the reaction, this is the process which you are supposed to follow. That's all. Nothing more, nothing less. All right? Now, my dear students, for example, this is your one more question. This is your one more question. This is your one more question. The question is, you are given with a reaction and you are supposed to calculate rate of the reaction in the interval 5 to 15 seconds. You are supposed to calculate rate of the reaction in the interval 5 to 15 seconds. So this particular time interval they are talking about. And this time interval, 5 to 15 seconds, I'm representing with delta T, and delta T time interval will be 10 seconds. Now, as you can see, this is the graph between concentration versus time. The graph is between concentration versus time. And as you can see, with the time, the concentration is decreasing. With the time, the concentration is decreasing. And with time, it is the concentration of reactant that decreases. With time, it is the concentration of reactant that decreases. Okay? And reactant in this reaction is NH3. So this is basically the graph which is for NH3. This is the graph which is given for NH3. So with time, concentration is decreasing and concentration of reactant decreases with time. So this particular graph is basically for which substance? It is for NH3. Okay? Now, my dear students, try to understand what exactly I'm going to do. At 5 seconds, what is the concentration of NH3? That is 0.6 molar. At 15 seconds, what is the concentration of NH3? That is 0.2 molar. So I would say this is the initial concentration of NH3. This is the final concentration of NH3. Now, what am I supposed to calculate? Rate of the reaction. Rate of the reaction. My dear students, rate of the reaction. Rate of the reaction. With respect to NH3 will be what? Rate of the reaction with respect to NH3 will be what? NH3 is the reactant. So I'll be starting with minus sign. 1 divided by 2. It's going to be change in the concentration of NH3 divided by time interval delta T. So I'll write minus 1 by 2. What is the change in the concentration of NH3? That will be final concentration of NH3 minus initial. Final is 0.6. Final is 0.2. Initial is 0.6. Divided by time interval is 10 seconds. Now it's a matter of calculation. And you will be getting the rate of the reaction by solving this particular equation. Right? The answer will be 0. When you solve it, it will be 0.02 moles per liter per second. This is the rate of the reaction in the interval 5 to 15 seconds. Am I clear with this? Am I clear with this, people? Right? Perfect. Now, for example, you can get a question like this as well. You can get a question like this as well. Now, it looks very difficult question because some data like this is given, right? But it's a simple question, guys. Why is it simple? Try to understand. First of all, we are given with a reaction. So tell me what would be the rate of the reaction with respect to N2O5? Rate of the reaction with respect to N2O5. Start with minus 1 divided by stoichiometric coefficient is 1. Change in the concentration of N2O5. So you can write either delta N2O5 or you can write D of N2O5. D of N2O5 divided by dt. Why am I not writing delta? Because in the question, the data is in terms of D. So I'm using the term D instead of delta. Okay. Similarly, guys, what would be the rate of reaction with respect to NO2? NO2 is the product, so start with plus 1 divided by stoichiometric coefficient, that's 2. It's going to be change in the concentration of NO2 divided by time interval dt. Similarly, rate of the reaction with respect to O2. O2 is again the product, so start with plus 1 divided by stoichiometric coefficient is 1 by 2. It's going to be D of O2 divided by dt. Now, 1 divided by 1 by 2. 1 divided by 1 by 2 comes out to be 2. Perfect. Now, people, you just have to put the values. That's it. You just have to put the values. That's it. Minus d N2O5 by dt. Minus d N2O5 by dt. What is that? That is K1 multiplied by concentration of N2O5 is equal to 1 by 2. dNO2 by dt. That's given to me as K2 multiplied by concentration of N2O5. Right? Similarly, 2 times dO2 divided by dt. That's given to me as K3 multiplied by concentration of N2O5. Now, my dear students, this term and this term gets cancelled out. So I'll be left with K1 is equal to K2 divided by 2, which will be equal to 2 times K3. Now, if I take LCM of the denominators, LCM of the denominators will come out as 2. Now multiply throughout with 2. This becomes 2 times K1 is equal to K2 is equal to 4 times K3. This is the relation between K1, K2 and K3, which you were supposed to calculate, right? Sir, I'm already done with all of this. I want session of organic chemistry. What time it will be? Organic chemistry will start in 3 to 4 hours. Okay? Your organic chemistry will start in 3 to 4 hours. If you're done with your physical, right? Then no need to watch it. Perfect. Just wait for your organic chemistry. It will start in 3 to 4 hours. Perfect. Am I clear, people, till here? Am I clear till here? Did you understand how do we deal with such kind of the questions? Perfectly done. Amazing, guys. Now, let me show you one more type of the question that can be asked. You will be asked with this sort of a question as well. You'll be asked with this sort of a question as well. Anyone who gets problem in understanding in between, you can drag the video a little back. It'll be a replay for you. Don't tell me to repeat it again because we have to complete a lot of things in the session, right? So it'll be very difficult for me to, repeat things again and again. So if there'll be a problem in between in understanding, just drag the video back. It'll be a replay for you. Perfect. All right, people. These sort of questions are also asked in your examination. And how do we deal with such kind of the questions? Try to understand. We are given with a chemical reaction A gives B. Whose rate constant is K. Okay. My dear students, let the order of this particular reaction is equal to N. let the order of this particular reaction is equal to what? Is equal to n. Okay. Now let me show you first of all, how do we write the rate law? How do we write the rate law? Understand. Whenever you are supposed to write the rate law, write it like this. R is equal to K. R is the rate of reaction. K is what you call as rate constant, multiplied by concentration of reactant raised per order. That's equal to n. Okay. I'm calling this as equation number 1. This is how you write the rate law. Now, as far as the question is concerned, if you look carefully, it is found that the rate doubles. So initially rate was R. Now after some time it will be 2R. When it's going to be 2R, the rate doubles when the concentration of A is increased 4 times. So now instead of A, I'm writing 4 times A raised per n. Perfect. So how many equations I got? 2 equations. Now, my dear students, just do one thing. Divide these 2 equations. When you divide these 2 equations, let's say I'm doing equation 2 divided by equation 1. Equation 2 divided by equation 1. I'll say R and R gets cancelled. So on left side, I'll be left with 2. K and K gets cancelled. A raised per n gets cancelled. So I'm left with 4 raised per n. Right? Now you tell me one thing. What should be the power of 4? Such that it comes equal to 2? I would say n value should be 1 by 2. Then only this equation is satisfied. What was this n? N was the order of the reaction. Did you understand how do we deal with such kind of the question? Did you understand? I'll show you one more question. With that, things will be more clear. For example, you have got a question like this. My dear students, the rate of the reaction becomes half. When the volume of the vessel is doubled. Find the order of the reaction. Sir, please solve some JEE mains questions as well. Would you please tell me the answer of this question first? Whosoever is asking me to solve JEE mains questions, would you please tell me the answer of this question first? I'm giving you 30 seconds. Quick. Quick. Quickly, everyone. What do you think is the answer of this question? It's a simple question. Every one of you. There'll be a separate session wherein I'll be taking all the PYQs of JEE mains of year 2025 and 2026. Okay, of your physical and inorganic. That'll be a separate session. In coming 2 to 3 days, I'll be taking that. Quickly, guys. Perfect. If you look at this particular question, the reaction is given to me, that's A gives B. The rate constant of the reaction is K. What am I supposed to calculate? Order of the reaction. First of all, let the order of the reaction is equal to N. What is the first thing which I do always? I always write the rate law first. So R is equal to K, concentration of A raised per N. Now, if you look at the question, the rate of the reaction becomes half when volume of the vessel is doubled. Do you see volume here in this equation? Do you see V here? No. But remember, concentration is nothing but moles divided by volume. So let me convert this equation into the volume format. So I'll say R is equal to K. Instead of concentration of A, I'll write moles of A divided by total volume raised per N. Calling this as equation number 1. Now the question says the rate is becoming half. Right? So initially the rate was R. So finally the rate is going to be R by 2. Rate is becoming half when volume of the vessel is doubled. So initially volume was V. Now it's 2 times V raised per N. Equation number 2. How many equations I got? 2 equations. Now divide the 2 equations. If I divide the 2 equations, for example, 2 divided by 1. Or let me do one thing. Let me divide equation 1 with equation 2. If I divide equation 1 with equation 2, R and R gets cancelled. This 2 goes up. So this becomes 2 is equal. K and K cancels out. Na by V cancels out. This becomes 2 raised power n. So 2 raised power n is equal to 2. So that means n value has to be equal to 1. And what was n? N was the overall order of the reaction, which I was supposed to calculate. These sort of questions are again frequently asked in your NEET examination, my dear students. Okay. Now, people, there is something called as molecularity. There is something called as molecularity. Theoretical question will be asked from this. What is molecularity exactly? There is one theory which you would have studied, I believe, collision theory. What collision theory says? Collision theory says that for any reaction to happen, collision theory says that for any reaction to happen, reacting species, which can be either atoms, molecules, or ions, reacting species, they must collide first. Your collision theory says that for any reaction to happen, reacting species, which can be atoms, molecules, or ions, okay, reacting species must collide first. Now, my dear students, the number of reacting species, which can be atoms, ions, or molecules, the number of reacting species which must collide simultaneously, to form the products, that defines molecularity of the reaction. The number of reacting species which must collide simultaneously to form the product. You call that as the molecularity of the reaction. For example, look at this reaction, second reaction. So, how many molecules do you see here? 1 and 1. So I would say 2 molecules are colliding to form product. I'll say molecularity of this reaction is 2. 2 and 1. I would say 2 plus 1. 3 molecules are colliding to form the product. Molecularity of this reaction is 3. Over here, you have got only 1. So molecularity of this particular reaction is 1. Over here, you have got 2 molecules. So molecularity of this reaction is 2. The number of reacting species which must collide simultaneously to form the product, that defines molecularity. And my dear students, based on molecularity, you classify reactions into certain types. Any reaction with molecularity 1 is called as unimolecular reaction. Molecular 2 is called as bimolecular reaction. This is called as trimolecular reaction, right? Molecularity 1 is unimolecular. Molecularity 2 is bimolecular. Similarly, molecularity 3 is trimolecular, right? Now, guys, remember one more thing. The concept of molecularity, which is theoretical. It is theoretical. It does not have any experimental background, right? It is complete theoretical. This particular concept was basically given for elementary reactions. The molecularity term, it is basically defined for which reactions? Elementary reactions. And what are elementary reactions? Elementary reactions are the ones which get completed in one step. Elementary reactions are the ones which get completed in one step. So molecularity concept is defined for elementary reactions, those reactions which are completed in just single step. Okay. Now, my dear students, tell me one thing. Can molecularity of the reaction be 0? Think over it. What is molecularity? The number of reacting species colliding to form the product. Can molecularity be 0? What does that mean? That means 0 molecules are colliding. 0 molecules are colliding does not make any significance. Right? Can molecularity be negative? Can I say molecularity of the reaction is -3, -4? What does that mean? -4 molecules have collided. Does that make any significance? No. Okay? So molecularity of the reaction, it can never be 0. It can never be fractional. Even it can never be negative. Perfect. Even, my dear students, reactions with molecularity greater than 3, they are rarely found. Or as per your NCERT, you can say the maximum value of molecularity. The maximum value of molecularity, you'll be taking as 3. The maximum value of molecularity, you'll be taking as 3. And as I told you, molecularity concept is defined for which reactions? Elementary reactions. It is defined for elementary reactions. These are few points, my dear students, which you have to remember. One more thing which I would want to add here, remember that for an elementary reaction, whenever you see an elementary reaction, my dear students, in case of elementary reactions, remember order is equal to molecularity. In case of your elementary reactions, order is equal to molecularity. Okay? So whenever you see an elementary reaction, whatever is going to be its molecularity, same is going to be its order as well. Perfect? Done? Now people, one more important thing which I would want to tell you over here. What is that? For example, you have got the reaction like this. Half of H2 plus half of I2. It gives HI. Now, if I ask you what would be the molecularity of this reaction, don't just say 1 by 2 plus 1 by 2 makes it 1. Don't say its molecularity is 1. Whenever the stoichiometric coefficients are in fractions, convert these fractions into the simplest whole numbers first. So what I'll be doing, I'll be multiplying this reaction throughout by 2. When you multiply this reaction with 2, it becomes H2 plus I2, gives 2 times HI. Now, if I ask you what is the molecularity of this particular reaction, it's going to be 1 plus 1, that's 2. Whatever is going to be the molecularity of this reaction, same is going to be the molecularity of this reaction as well. So whenever the stoichiometric coefficients are in fractions, convert them into simplest whole numbers first, and after that, whatever reaction you get, whatever is going to be its molecularity, same is going to be the molecularity of the reaction which you were supposed to calculate. Understood? Now there is one more concept, my dear students, which is asked. What is that? That is your experimental determination of order. Frequently asked question. How do we calculate order of the reaction experimentally? Again, question is asked from this particular one. Let me show you how do we calculate order of the reaction experimentally. For that, what am I going to do? I'm going to take one question. I'm taking directly. Understand how I'm going to tackle this question, and that's it. My dear students, whenever you are given with a reaction and some experiments will be given to you like this, perfect, some experiments will be given to you like this, and you will be supposed to calculate order of the reaction. How do we exactly do it? The first thing which you'll be always doing, you'll be always writing the rate law first. For the given reaction. Now, if I write rate law for this reaction, I'll just write R is equal to K. Concentration of NO raised power for is equal to X. There is one more reactant, concentration of Cl2 raised power Y. This is how you write the rate law. Since you have got two reactants, so that's why I wrote concentration of NO raised power X, concentration of Cl2 raised power Y. What is this X and Y called? X is called as the order of the reaction with respect to A, and Y is called as the order of the reaction with respect to B. And let me tell you, X plus Y is what you call as the overall order of the reaction. And I need to calculate this X, I need to calculate this Y. How am I going to deal with such kind of a question? Understand, people. First of all, look at the first experiment. Whatever values you are given with first experiment, put all these values in this equation. Now, as per experiment number 1, what is the value of R? R is rate. What is the value of rate? That's 10 raised power minus 3. So 10 raised power minus 3 is equal to K. What is the concentration of NO in the first experiment? That is 0.05. Raised power X. What is the concentration of Cl2 in this experiment? That is 0.05. Raised power Y. Calling this is equation number 1. My dear students, put the second experiment data in the same equation. As per the second experiment, R value is 3 into 10 raised power minus 3. R is 3 into 10 raised power minus 3 is equal to K. What is the concentration of NO in the second experiment? Concentration of NO in the second experiment is 0.05 raised power X. What is the concentration of Cl2 in the second experiment? That is 0.15 raised power Y. Equation number 2. Now, the third experiment data in the same equation. What is the value of R in the third experiment? That's 9 in 10 raised power minus 3. 9 in 10 raised power minus 3 is equal to K. Concentration of NO in the third experiment. That is 0.15. 0.15 raised power X. Concentration of Cl2 in the third experiment. That's again 0.05 raised power Y. So how many equations I got? I got 3 equations, right? Now, people, you are just supposed to divide these equations. Nothing more. So what I'll be doing, for example, if I divide equation 2 with equation 1, I first of all wrote the rate law, right? What did I do? I made 3 equations out of it with the help of the 3 datas which were given to me. Now I'm dividing equation 2 with equation 1. So 10 power minus 3 cancels out. So I'll be left with 3 on left side is equal. K and K gets cancelled. This entire term gets cancelled. 0.15 divided by 0.05. That will be 3. But this is going to be 3 raised power Y. So 3 raised power Y is equal to 3, which tells you that Y value has to be equal to 1. So you got the value of Y. Right? Similarly, my dear students, just do one thing. Divide third equation with the first equation. If you divide third equation with the first equation, again 10 power minus 3 cancels. I'll be left with 9 on left side is equal. K and K gets cancelled. This entire term gets cancelled. 0.15 divided by 0.05, that is 3. But it's going to be 3 raised per x. So what has to be the power of 3? What has to be the power of 3 such that it becomes equal to 9? I would say the value of x should be 2. Then only 3 ka square comes out be 9. So you got the value of x, you got the value of y. So I can say overall order of the reaction. Overall order of the reaction is going to be x plus y. That means it's going to be 3. Am I clear? Did you understand how do we deal with such kind of equations? Write the rate law, put the value of all the experiments in this equation. You'll be getting few equations, divide these equations, get the value of x and y, which you are supposed to calculate, right? I'm giving you one question as homework of the same pattern. This is your homework question, and I believe you can easily solve it. Yes? Tell me quickly in the chats. Tell me quickly in the chats, people. Done? All right. The next topic, my dear students, from which questions are frequently asked. What is that? That is your zero order reaction. That's your zero order reactions. Remember what exactly I say. I am not going to derive any equation. I'll just give you the equations. I'll show you how to use these equations. That's all. Nothing more, nothing less. For example, you have got the reaction like this. A gives B, whose rate constant is K. I'm assuming order of this reaction is equal to 0. I'm assuming order of this reaction is equal to 0. Now, my dear students, first thing, at time t is equal to 0, let the concentration of reactant is A0. This would be 0 because the reaction has not started yet. I'm using the term time t is equal to 0. That means reaction has not started yet. That means product has not got formed yet. So at time t is equal to 0, I'll only have reactant with me. And what is the concentration of reactant at time t is equal to 0? That's A0, right? My dear students, as the reaction starts, what will happen to the concentration of reactants? Concentration of reactants will decrease with time. Concentration of reactants will decrease with time. So I'll say at some time t, let the concentration of reactant be AT. Let the concentration of product formed be BT. So first of all, you should know what is the meaning of these two things. A0, AT and BT. A0 is the initial concentration of reactant. AT is the concentration of reactant left. AT is the concentration of reactant left at time t. BT is the concentration of product that has got formed at time t. Okay. The first thing, if I ask you, how do you write the rate law? I'll say R is equal to K. That's the rate constant. Concentration of reactant, raised power, order. Order here is 0. So I would say R is equal to K here because anything raised power 0 is 1. Anything raised power 0 is 1. So if I have to divide this, if I have to define the zero order reaction, I would say zero order reaction. In zero order reaction, what happens? Rate of the reaction is independent. Rate of the reaction is independent of the concentration of reactant. Rate of the reaction is independent of the concentration of reactant. Perfect. Now, my dear students, there are few equations. Which you need to remember when it comes to zero order reactions. What are those equations? The first equation is called as the integrated rate equation. Integrated rate equation for the zero order reactions. And how this integrated rate equation looks like? It is something like this. AT is equal to A0 minus KT. How this equation came, you have got nothing to do with that right now. Just remember it directly. This particular equation is called as integrated rate equation for the zero order reactions. AT is equal to A0 minus K into T. Okay, number one. Number two, my dear students, there is a term called as half-life. How do we define half-life? It is simply time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction is called as half-life, right? And how do we calculate half-life of the zero order reaction? I'll say T half will be equal to A0 divided by 2K. This is the equation with the help of which you calculate half-life of the zero order reaction. My dear students, the third parameter about the zero order reaction, that is its completion time. Completion time. What is meant by completion time? Simply, time taken to complete 100% of the zero order reaction. And remember, time taken to complete 100% of the zero order reaction is nothing but A0 by K. is nothing but A naught by K. All these equations have got the derivations, but I'm skipping those derivations. That's of no use to us at this point of time. If they ask you calculate the half-life, it's A naught by 2K. If they ask you calculate the completion time, it's A naught divided by K. My dear students, do you see A naught by 2K, A naught by K? So from these two, I can say one thing. A zero order reaction is 100% completed in 2 half-lives. A zero order reaction is 100% completed in 2 half-lives. Right? Similarly, what if they ask you to calculate the concentration of product? Calculate the concentration of product at time t. At time t. So technically they are asking about Bt. Technically they are asking about the value of Bt. Concentration of product formed at time t. It's going to be simply concentration of product at time t is nothing but K multiplied by T. Remember again this directly. Concentration of B at time t will be nothing but it will be K multiplied by T. Again it has got the derivation. I'm skipping that. That's of no use to us. Okay. Similarly, the fifth point, my dear students, which you need to know. They can ask you about the degree of dissociation of the zero order reaction. Degree of dissociation of the zero order reaction. Degree of dissociation I represent with alpha. And remember, alpha is nothing but Kt divided by A naught. This is one more parameter which they can ask. Calculate the degree of dissociation, alpha, for the zero order reaction. So alpha is nothing but Kt divided by A naught. Okay? Alpha is nothing but Kt divided by A naught. And my dear students, there can be few graphs which they can ask. Some simple graphs. For example, if they ask you a graph about rate of reaction versus concentration of reactant. Now tell me, is the rate of reaction depending on concentration of reactant? No. In case of zero order reaction, rate does not depend on the concentration of reactant. So if you increase or decrease the concentration of reactant, nothing happens to rate. It's constant. But this graph is only valid for zero order. For example, if they ask you the graph between AT and T, if they ask you the graph between AT and T, my dear students, remember AT versus T graph is a straight line with negative slope and its slope will be equal to minus K. Its intercept is equal to A naught. Its intercept is equal to A naught. Similarly, they can ask you one more graph. Related to what? They can ask you about T half versus A naught. T half versus A naught. As you can see, T half is directly proportional to A naught. So it's a straight line passing through origin. And what will be its slope? Its slope will be 1 upon 2K. Remember these three important graphs, and these graphs are basically valid for your zero order reactions. Right? These graphs will be valid for your zero order reactions, which are important ones, I must say. Now, my dear students, there are some examples of zero order reactions which I would want you guys to remember. This can be the memory-based question which can be asked to you. A direct memory-based question. Remember, photochemical reaction between H2 and Cl2. That is the example of zero order. Decomposition of Hi over gold. That's again the example of zero order reaction. Decomposition of NH3 over molybdenum. That's again the example of zero order reaction. So these can be your memory-based questions which can be asked when it comes to the zero order reactions. Okay? Perfect? Perfect, guys? Similarly, what kind of questions can be asked? Let me show you one question, you'll understand. How do we deal with the questions? My dear students, for example, we are given with a zero order reaction A gives B, whose rate constant is K. Since it's the zero order reaction, that means order is equal to 0. Now tell me one thing. At time t is equal to 0, what is the initial concentration of reactant? That's A naught. This will be 0. Now in the question, if you look carefully, they have mentioned one thing. A zero order reaction is 20% completed in 10 minutes. Time taken to complete 20% of the reaction is equal to 10 minutes. Time taken to complete 20% of the reaction is equal to 10 minutes. They're asking us to calculate time taken to complete 80% of the reaction. They're asking us to calculate time taken to complete 80% of the reaction. Time taken to complete 80% of the reaction. I'll show you one shortcut, direct shortcut. See guys, this is 20, this is 80, right? This is 10, this is for example x. This x I have to calculate. Perfect. So let me show you how do I write it. I'll write this like this. 20 divided by 80. I'll write 20 divided by 80 is equal. This will be 10 divided by x. So this gets cancelled. X value comes out to be 40. What was x? X was time taken to complete 80% of the reaction. So you got to know time taken to complete 80% of the reaction is 40 minutes. A direct shortcut. A direct shortcut this is. Okay? Direct shortcut this is. Remember, these sort of questions can be asked. Even this sort of a question can be asked. You're given with the reaction A gives B. You're given with the reaction A gives B. You're supposed to calculate its rate constant, right? And the data like this is given. If you look carefully, at time t is equal to 0, concentration of reactant is 1 molar. That means A naught value is 1 molar. At time t is equal to 0, concentration of reactant is 1 molar. That means A naught is 1 molar. At time 120 seconds, concentration of reactant left is 0. What does that mean? What does that mean? At 120 seconds, concentration of reactant left is 0. That means this is the time at which 100% of the reaction has got completed. When 100% reaction gets completed, at that point of time, there will be no reactant left. So this is the time when 100% of the reaction has got completed. And time taken to complete 100% of the reaction, what do we call that as? Completion time. So technically, I would say completion time is given to me as 120 seconds. Few minutes back, I told you completion time is nothing but A naught by K. So A naught by K is 120. So can I calculate K from here? K will be A naught divided by 120. What's the value of A naught? A naught value is 1. So it's going to be 1 divided by 120 moles per liter per second. Okay, this is how you calculate question like this. Right, people? Similarly, my dear students, when it comes to your first order reactions, in case of your first order reactions, again, there are some important equations which you need to remember directly. We don't have any sort of time to derive these equations. I'll be giving you these equations. I'll show you how do we use them. Okay. Now try to understand what exactly I'll be doing. For example, I'm given with the reaction A gives B. Assume its rate constant is K. Assume order of the reaction is equal to 1. First of all, at time t is equal to 0. Initial concentration of reactant A naught. This will be 0. At time t, let the concentration of reactant be AT. Let the concentration of product be BT. Now, my dear students, the first equation, what is that? How do I write a rate law for this particular equation? How do we write rate law? Simple. I'll say R is equal to K, concentration of reactant raised per order. That's 1. So this is how you write rate law. Now, my dear students, what is the integrated rate equation for the first order reactions? In zero order, there was only one form of the integrated rate equation. But in first order, there are different forms. Let me show you all those forms. The first form of the integrated rate equation, that is the ln of AT is equal to ln of A naught minus KT. This is the first form of integrated rate equation of the first order reactions. The second form is log AT is equal to log of A naught minus K divided by 2.303 multiplied by T. The third form is K is equal to 1 divided by T ln of A naught divided by AT. The next form is K is equal to 2.303 divided by T log of A naught divided by AT. Similarly, the next form is AT is equal to A naught e raised power minus KT. These are the 5 different forms. Of your integrated rate equation when it comes to the first order reactions. Okay? When it comes to the first order reactions. Now, few more parameters. They might ask you calculate the half-life. Half-life, that means time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction is 0.693 divided by K for the first order reactions. They might ask you to calculate the completion time. Remember, in first order reaction, completion time is infinite. What does that mean? That means a first order reaction never undergoes 100% completion. A first order reaction never undergoes 100% completion. A direct result I'm giving you, time taken to complete X% of the first order reaction. Time taken to complete X% of the first order reaction. X can be anything. 10%, 20%, 30%, 40%, 60%, 70%. So time taken to complete X% of the first order reaction. How do I calculate it? The formula is simple. 2.303 divided by K. It's going to be log of 100 divided by 100 minus X. 100 divided by 100 minus X. Right? What are the units of rate constant in case of first order reaction? It can be second inverse, minute inverse, hour inverse. Right? These are the units of rate constant of the first order reactions. Similarly, there are some important parameters, my dear students, which you need to know. What are those parameters? Remember, time taken to complete 75% of the first order reaction is equal to 2 times the half-life. time taken to complete 87.5% of the first order reaction is equal to 3 times half-life. Similarly, time taken to complete 90% of the reaction is equal to 10 by 3 times half-life. Similarly, time taken to complete 99.9% of the reaction is equal to 10 times the half-life. 10 times the half-life. And remember, time taken to complete 99% of the reaction is 2 times the time taken to complete 90% of the reaction. These are some of the direct results from which questions will be asked, and all these results are basically valid for your first order reactions. All these results are basically valid for your first order reactions. Okay. Now, there can be some graphs asked too. Some graphs can be asked too. And what are those graphs that can be asked? My dear students, the first graph that will be asked is between ln AT versus T. Ln AT versus T. And ln AT versus T. If you want to make a graph, this is how you make a graph. Ln AT is equal to ln A0 minus KT. Now, ln AT you are plotting along y-axis. T you are plotting along x-axis. This becomes your M. Sign is minus. This is C. Y is equal to minus mx plus C. Straight line with negative slope, and its slope is nothing but minus k, and its intercept, the distance from here to here, intercept is C. C is nothing but ln of A0. This graph is basically for what? It's for your first order reaction, right? Similarly, there can be one more graph asked. What can be that? What that can be? That can be between log of AT versus T. And let me tell you, log AT versus T is the similar graph, but remember its slope is equal to minus k divided by 2.303, and its intercept is equal to log of A0. Log of A0. There can be a question asked between rate versus concentration of reactant. Rate versus concentration of reactant. Few minutes back I told you, rate of the reaction is equal to K. Concentration of A, raised power 1. Rate you are plotting along y-axis. Concentration of reactant x-axis. This becomes your M. Y is equal to mx. Straight line passing through origin. And if you talk about its slope is nothing but K. Okay. Similarly, they can ask you the graph between a half-life versus initial concentration of reactant. Now, you know, if you talk about it, your half-life is 0.693 divided by K. So half-life is independent of A0. There is no A0 here. So on increasing A0, decreasing A0, nothing happens to half-life. These are some of the important graphs which can be asked when it comes to your first order reactions, right? Am I clear with this? Am I clear with this, people? Quickly. All right. So, what kind of questions can be framed? Look at these questions. Simple questions can be framed. How exactly? A first order reaction is 75% completed in 100 minutes. So, time taken to complete 75% of the reaction is equal to how much? 100 minutes. What do I have to calculate? I have to calculate time taken to complete 87.5% of the reaction. Few minutes back I told you it's equal to 3 times the half-life. So, technically, in order to calculate this, I need half-life. How do I calculate half-life? You know, T 75% is equal to 2 times the half-life. So this value is equal to 100. So I can say T half is nothing but 50 minutes. If you got T half, put it here. So 3 into 50 will be 150 minutes. So this is the time taken to complete 87.5% of the reaction. They can ask you anything. Calculate the time taken to complete 99.9% of the reaction. It is 10 times T half. 10 times T half. T half is 50. So 10 into 50 will be 500 minutes. Anything can be asked out of these things. Yeah? Or for example, you can get a question like this as well. Read the question once. Read the question once. Guys, you have to be very quick and active. Okay? We don't have a lot of time left. Tell me, people, what do you think about this one? For an elementary reaction, I told you a few minutes back, in case of elementary reaction, order is equal to molecularity. What is the molecularity? Molecularity is 1. So what would be the order? Order would be also 1. T half is given 10 minutes. T half is given as 10 minutes. In what period of time would the concentration of X, in what period of time would the concentration of X be reduced to 10%? In what period of time would the concentration of X be reduced to 10% of its initial value? That means technically we are supposed to calculate time taken to complete 90% of the reaction. Because when 90% reaction would be completed, at that point of time, 10% reactant would be left. When 90% reaction will be complete, at that point of time, 10% reaction will be left. So T 90%, few minutes back, I told you 10 by 3 times the half-life. Half-life is given. How much? So 10 by 3 multiplied by 10, the value will be 33.3 minutes. The value will be 33.3 minutes. So in this much time, in this period of time, I would say 10% of reactant would be left. That means 90% of the reaction would get completed. Am I clear? Let me know once in the chats, quick. Quickly, people. Yes? So these sort of questions you can expect from your first order reactions. Look at this question also. Look at this question also, people. The graph is between log 80 versus T. Few minutes back, I told you, what is the slope? What is the slope? It is log 80 versus T. So it's minus K divided by 2.303. So minus K divided by 2.303 will be equal to slope. Slope is tan of theta. Theta is 135. And tan of 135 is how much? Minus 1. So I got to know minus K divided by 2.303 is equal to minus 1. So I would say K is equal to 2.303. Time is given in minutes. So the units of rate constant will be minute inverse. Right? Now, what am I supposed to calculate? I am supposed to calculate what? I am supposed to calculate the half-life. How do you calculate the half-life? In the first order, 0.693 divided by K. K is 2.303. When you solve, the value comes out to be 0.3 minutes. So this is your half-life. If you got half-life, they can ask you time taken to complete 75%. 2 times half-life. 87.5, 3 times half-life. 90%, 10 by 3 times half-life. 99.9, 10 times half-life. Anything can be asked. Got it? I believe I'm clear with this. I believe, people, I'm clear with this. Yeah? Once in the chats. Okay. Now, there is one more topic from which questions will be asked in your chemical kinetics. What is that? That's your Arrhenius equation. My dear students, how Arrhenius equation looks like? K is equal to A, e raised power minus Ca by RT. K is equal to A, e raised power minus Ca by RT. This is basically your Arrhenius equation. K is equal to A, e raised power minus Ea by RT. Now, first of all, you should know what are these different parameters. This A is what you call as pre-exponential factor. Pre-exponential factor, or you call it as frequency factor. Or you call it as frequency factor. EA is nothing but that is the activation energy of the reaction. That is the activation energy of the reaction. Let me tell you, A and EA, combinedly they are called as Arrhenius parameters. Combinedly they are called as Arrhenius parameters, right? Similarly, let me tell you one more thing. E raised power minus Ea by RT, this entire term is called as Boltzmann's factor. Is called as Boltzmann's factor. And Arrhenius equation simply says that on increasing the temperature of the reaction, rate constant of the reaction increases. On increasing the temperature of the reaction, rate constant of the reaction increases. So when you increase the temperature of the reaction, rate constant of the reaction is going to increase. That means automatically rate of the reaction will increase. So in short, on increasing the temperature, rate constant of the reaction increases, or you can say rate of the reaction increases. And remember, my dear students, remember one more thing. When you increase the temperature of the reaction by 10 degree, when you increase the temperature of the reaction by 10 degree, remember rate constant. Remember rate constant. Rate constant doubles or becomes even more. Remember, rate constant doubles or becomes even more. Whenever you increase the temperature of the reaction, rate constant doubles, or you can say rate of the reaction doubles. When you increase the temperature of the reaction by 10 degree, rate constant. When you increase the temperature of the reaction by 10 degree, rate constant doubles or becomes even more. Similarly, you can say rate of the reaction doubles or becomes even more. Okay? My dear students, you can be asked one thing. That's called as temperature coefficient. What is the value of temperature coefficient? Remember, it is between 2 to 3. Temperature coefficient is between 2 to 3. N value, temperature coefficient. This can be direct question asked. Okay? It's between 2 to 3. At the same time, there is one more thing which I'm going to tell you. For example, you have got the reaction A gives B. Let's say at temperature T1, rate of the reaction is R1. At temperature T2, rate of the reaction is R2. Is there any equation that relates all these parameters? Yes. Equation is like this. R2 is equal to 2 raised power delta T divided by 10 multiplied by R1. This one equation which relates to your R1 with R2. Now you must be thinking, what kind of questions? What kind of questions can be framed from this equation? For example, there is a question asked. Questions like this. You have got the reaction A gives B, right? On increasing the temperature from 10 degrees centigrade to 100 degrees centigrade, how many times the rate of the reaction will increase? How many times rate of the reaction increases? So you'll just use the result. R2 is equal to 2 raised power delta T, change in temperature, final minus initial. That's 90 divided by 10 multiplied by R1. So you'll say R2 is equal to 2 raised power 9 times R1. So directly you will say, when you increase the temperature from 10 degree to 100 degree, a rate of the reaction increases how much? 2 raised power 9 times. Simple. Okay. There's one more thing that can be asked in your examination. Perfect. My dear students, there are some different forms of Arrhenius equation as well. I gave you one form of Arrhenius equation. K is equal to A e raised power minus Ca by RT. There are few other forms of Arrhenius equation as well. And what are those other forms? The first form is ln K is equal to ln A minus Ea divided by RT. This is one of the forms of Arrhenius equation. Similarly, log of K is equal to log of A minus Ea divided by 2.303 and RT. Similarly, there is one more form, that is the log of K2 divided by K1 is equal to Ea divided by 2.303 R. This is 1 upon T1 minus 1 upon T2. This is one more form of Arrhenius equation. Similarly, there can be a differential form as well, that is d upon dt of your ln of K is equal to Ea divided by RT square. These are some different forms of Arrhenius equation from which questions can be asked to you. These are the different forms of Arrhenius equation, my dear students, which you need to remember. Yeah, which you need to remember. I believe this is also clear. And people, at the same time, few graphs can be made too. What graphs can be made? For example, there is a graph between ln of K versus 1 by T. Ln K versus 1 by T, where K is the rate constant of the reaction. Ln K versus 1 by T. Ln K versus 1 by T. Ln K versus 1 by T. Its graph will be straight line like this. And remember, its slope is equal to minus Ea divided by R. For example, there can be one more graph that is between log of K versus 1 by T. The graph is the same, but its slope is right now minus A divided by 2.303 R. Remember these two graphs as well. And people, at the same time, what kind of question can be framed? You can look at the question. You're given the graph between log K and 1 by T. My dear students, what do we have to calculate? Activation energy. First of all, the graph is between log K and 1 by T. What would be its slope? Its slope would be equal to minus Ea divided by 2.303 R. Slope is nothing but tan of theta. Tan of theta will be minus 3. So I would say Ea is equal to 3 multiplied by 2.303 multiplied by R. This is the activation energy. Now you have to calculate activation energy in kilojoules. That entirely depends on the value of R. How many R values do you know? The first value of R is 8.314 joules per Kelvin per mole. The second value of R is 0.0821 atm liter per Kelvin per mole. The third value of R is 1.98 calories per Kelvin per mole. So, first of all, I have to calculate in kilojoules. So, what do? It's going to be 2.303 multiplied by 3 multiplied by R. I'll take this R value, which is 8.314. Since I've taken the R value in joules, so right now this answer is going to be in joules, but I need in kilojoules, so I'm dividing with 1000. When I divide with 1000, the answer will be in kilojoules, right? Similarly, I need to calculate in kilocalories as well. So I'll be writing 3 multiplied by 2.303. Now I'll take R value in calories, which is approximately 2. Since I took the R value in calories, so the answer right now is in calories, but I don't need the answer in calories. I need in kilocalories. So divide with 1000. So this is going to be in kilocalories. Is it clear? Did you understand, people? For example, I'll give you one more question. The question is like this. You have got the reaction A gives B, whose activation energy is equal to 0, for example. Now, at 100 Kelvin, I would say rate constant of the reaction is equal to 2 into 10 raised power minus 1 second inverse. We have to calculate rate constant at 500 Kelvin. Calculate rate constant at 500 Kelvin. Do you understand the question? You have got the reaction whose activation energy is 0. Whose activation energy is 0, right? If activation energy is 0, at 100 Kelvin, rate constant is this. We have to calculate rate constant at 500 Kelvin. Few minutes back, I gave you one result. Log of K2 divided by K1 is equal to EA divided by 2.303 R 1 upon T1 minus 1 upon T2, right? Since activation energy is 0, so this entire term becomes 0. If this entire term becomes 0, that means log of K2 divided by K1 is 0. When is the log of something 0? Log of something is only 0 if something is equal to 1. Therefore, K2 divided by K1 has to be 1, which means that your K1 and K2 should be equal. So that means you can say it like this as well. K is equal to A, E raised power minus A by RT, right? So if activation energy is 0, if EA is 0, if activation energy is 0, anything raised power 0 is 1. So K is equal to A. So K becomes temperature independent. So that means when you change the temperature, nothing happens to rate constant. Rate constant of 500 Kelvin will be same. 2 into 10 raised power minus 1 second inverse. Right? Remember this particular point as well. For any reaction whose activation energy is 0, its rate constant becomes independent of temperature, my dear students. Okay? Subetha, I've already taken a session on that. You can check PYQs of NEET. Is this clear, people? So now let's move on to your solution chapter. And let me tell you what all concepts are there in the solution chapter from which questions will be asked. Let's get to know what all topics are there in the solution chapter from which questions will be asked. The first is your concentration terms. And my dear students, in the concentration terms, 3 concentration terms are important. One is molarity, one is molality, and one is mole fraction. Number one. My dear students, number two is your Raoult's law. Question can be framed from Raoult's law as well. Number 3 is your ideal and non-ideal solution. Ideal and a non-ideal solution. Number 4 is your colligative properties, all the colligative properties. And number 5 is your Van 't Hoff factor. These are basically the topics from which questions will be asked in the chapter solution. So now we are going to jump into these topics of the chapter solution. But before starting the solution, let's take a break for 15 minutes and get back. Okay? Have some tea, refresh yourself, but I would want everyone to be back exactly at 11:40. So break till 11:40. A quick, small 15 minutes break. Be back on time. Okay? I'll see you in a while. Is everyone back? Is everyone back? Yes. All right. So what's up? So should we start with the chapter solution? Ready for the solution chapter? All right, people. So first of all, let's try to discuss these three important concentration terms from which questions have been frequently asked and will be asked too. Okay. Now, my dear students, I believe every one of you will be already knowing about molarity. Everyone would be already knowing about molarity. What is molarity exactly? Number of moles of solute which are present in 1 liter of solution. The number of moles of solute which are present in 1 liter of solution. What does that mean? For example, imagine you have got 1 liter of solution. Imagine you have got 1 liter of solution. If in 1 liter solution there are 5 moles of solute, if in 1 liter of solution there are 5 moles of solute, means molarity of the solution is 5. If in 1 liter of solution there are 10 moles of solute, that means molarity of the solution is 10. In short, number of moles of solute which are present in 1 liter of solution. That is what you call as molarity. Now, what all formulas do we have to calculate molarity? This is our first formula. Number of moles of solute, N2, divided by volume of solution in liters. This is the first result with the help of which we can calculate molarity of the solution. Second result, my dear students, second result is mass of solute into 1000 divided by molar mass of solute into volume of solution in ml. 2 represents solute, 1 represents solvent. So it is mass of solute into 1000 divided by molar mass of solute into volume of solution in ml. Okay. Similarly, guys, this is one direct result. One more direct result with the help of which we can calculate molarity. What is that? It is 10 multiplied by weight percentage of solute into density of solution divided by molar mass of solute. And similarly, one more direct result. What is that? That is 10 multiplied by weight by volume percentage of solute divided by molar mass of solute. These are the 4 direct results with the help of which we can calculate molarity of the solution. I'll be showing you one by one. How do we apply these formulas? Okay, I'll be showing you one by one. First of all, moles of solute divided by volume of solution in liters. Mass of solute into 1000 divided by molar mass of solute, volume of solution in ml. 10 multiplied by weight of solute, density of solution divided by molar mass of solute. 10 multiplied by weight by volume of solute divided by molar mass of solute. Direct results. Now, what are the units of molarity? Molarity units are moles per liter, or you can say molar. Moles per liter or molar. Units of molarity. For example, sometimes if I write 2 molar NaCl aqueous solution, 2 molar NaCl aqueous solution, what does that mean? It means 2 moles of solute. It means 2 moles of solute are present in 1 liter of solution. It means 2 moles of solute are present in 1 liter of solution. Sometimes if I say molarity of the solution is 10, what does that mean? That means 10 moles of solute are present in 1 liter of solution. As simple as that. Okay. And one more thing, molarity is temperature dependent. Molarity is temperature dependent. When you increase the temperature of the solution, molarity of the solution decreases. When you increase the temperature of the solution, molarity of the solution decreases. These are few points which you have to remember over molarity. Right? Similarly, guys, sometimes in the question they'll write semi-molar solution. What is meant by semi-molar solution? Semi-molar solution is that solution whose molarity is 0.5. Decimolar solution, molarity 0.1. Centimolar solution, molarity 0.01. Millimolar solution, molarity 0.001. These are again few things which you have to remember. Okay? Which you have to remember. Now, there is one more term. What is that? That is molality. Where is the difference between molarity and molality? In molality, Here we write 1 kg of solvent. Number of moles of solute present in 1 kg solvent. Number of moles of solute present in 1 kg solvent. Again, there are some direct formulas. There are some direct formulas with the help of which we can calculate molality. We can calculate molality. If you look at these formulas, you have to remember them. In some time, I'll show you how to apply them. Number of moles of solute divided by mass of solvent in kg. Mass of solute into 1000. Molar mass of solute, mass of solvent in grams. Similarly, mole fraction of solute into 1000 divided by 1 minus mole fraction of solute into molar mass of solvent. One more direct result. Similarly, 1000 multiplied by molarity of solution divided by 1000 multiplied by density of solution minus molarity into molar mass of solute. These are some direct results with the help of which we can calculate molality of the solution. Now, what are the units of molality? It's going to be mole per kg or molal. These are the units of molality. Sometimes if I say I have got 5 molal solution, 5 molal solution, what does that mean? That means 5 moles of solute are present in 1 kg solvent. That means 5 moles of solute are present in 1 kg solvent. If I say molality of the solution is 10, that means 10 moles of solute are present in 1 kg solvent. These are some simple things, my dear students, which you need to know. And again, molality, it is temperature independent. It does not depend on temperature. And molality is preferred over molarity. Molality is preferred over molarity. Molality is preferred over molarity. Do remember this particular point as well. Now, what kind of questions can be framed from all this? For example, you have got a question. Look at this question. Calculate what? Calculate the molality of the solution containing 10% weight by weight of NaOH aqueous solution. What does that mean? What does that mean? I'm given 10% weight by weight. What is meant by 10% weight by weight? It means that 10 grams of solute. Solute is our NaOH. 10 grams of solute are present in 100 grams of solution. It means that 10 grams of solute are present in 100 grams of solution. Right? Now, my dear students, what is the mass of solute? Mass of solute we represent with W2, that's 10 grams. What is the molar mass of solute? Molar mass of NaOH, you should know, that is 40 grams. What would be the mass of solvent? Mass of solution is 100. Mass of solute is 10. So mass of solution minus mass of solute, that comes out to be 90 grams. What am I supposed to calculate? Molality. Molality formula, few minutes back I told you, W2 into 1000 divided by M2 multiplied by W1. What is W2? Mass of solute. How much is that? 10 grams multiplied by 1000 divided by. What is the molar mass of solute? That is 40. What is the mass of solvent in grams? That's 90. Solve this, you'll be getting the molality of the solution. As simple as that. Right? Simple. By just using the formula, I'm doing the questions. Right? No like huge concepts or something. Look at this particular question. Look at this particular question. The question says calculate the mole fraction of solute present in 10% weight by weight of NaOH aqueous solution. Again, tell me one thing. What is meant by 10% weight by weight? It means that 10 grams of NaOH are present in 100 grams of solution. That means your mass of solute is equal to 10 grams and your mass of solvent is equal to 90 grams. Right? Now tell me, how many moles of solute do we have? Mass of solute divided by molar mass of solute. Moles of solvent. Mass of solvent divided by molar mass of solvent. Since solvent is water, so molar mass of solvent is 18. This value is 1 by 4. This value is 5. I got the moles of solute as well as solvent. Now people, what do we have to calculate? Mole fraction of solute. How do you calculate mole fraction of solute? Something which all of you will be knowing. Number of moles of solute divided by total moles present in the solution. What is the value of N2? N2 is 1 by 4 divided by 1 by 4 plus 5. When you solve it, the value comes out to be 1 by 21. Simple. Right? Similarly, there can be a question like this. Calculate the molality of a 2 molar. So molarity is given, molality is to be calculated. Molarity is given, molality is to be calculated. And this is the formula that relates molarity with molality. So I would say molality is equal to 1000 multiplied by. What is the molarity of the solution? That's 2 divided by 1000 multiplied by, what is the density of solution? That's given to be as 1.2 minus molarity is 2, molar mass of solute, molar mass of NaOH, that is 40. Again, the matter of calculation, and you can do it. Just remember this direct result, right? This will be used when molarity is given, molality is to be calculated, or molality is given, molarity is to be calculated. Yeah? Perfect. Similarly, my dear students, this can be one more question that can be asked. One more question that can be asked. What is this? Calculate the mole fraction of solute in 0.1 molar aqueous solution. So molality of the solution is 0.1. What do you have to calculate? Mole fraction of solute. Is there any result between mole fraction and molality? I gave it to you a few minutes back. I told you molality is equal to mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute multiplied by molar mass of solvent. Now, m is given to me as 0.1 is equal. This will be 1000 chi2 divided by 1 minus chi2 multiplied by, what is m1? m1 is the molar mass of solvent. Solvent used is water because I mentioned aqueous there. So that's 18. Molar mass of solvent is 18. Now again, just do the cross multiplication stuff and you will get the chi2 value, mole fraction of solute. So these sort of direct questions are frequently asked when it comes to your NEET examination from your concentration terms. The first question is a relation between molality and molarity. Second is molality and mole fraction, right? These are some direct results from which questions can be asked. Now the actual stuff, my dear students, from which question is asked, what is that? That's your Raoult's law. That's your Raoult's law. What this Raoult's law says exactly? What this Raoult's law says? Try to understand what exactly I'm going to say. Try to understand very carefully. My dear students, for example, imagine that over here I've taken a liquid. This is a volatile liquid A. This is a volatile liquid A. If it is a volatile liquid, that means above this, I would say there would be vapors of A present. This is a volatile liquid A. And above this, what do we have? Above this, we have got vapors of A present, right? Similarly, this is the volatile liquid B. Above this, there will be vapors of B present. I mean, here in this particular part, there are vapors of B present. Perfect. My dear students, since P naught A and P naught B, what are these terms? P naught A is called as vapor pressure of A when A is present in pure state. Since in the container, I have taken liquid A. And above liquid A, there are vapors of A. Vapor pressure of A right here in pure state is P naught A. Similarly, vapor pressure of B in pure state is P naught B. Now, if you mix them up, if you put them into this container, what do we get? We get a solution of A and B. There's a solution of A and B, right? So over here, you'll find vapors of A as well as vapors of B. You'll find vapors of A as well as vapors of B. So vapor pressure of this solution will be due to vapors of A as well as vapors of B. Vapor pressure of this solution will be due to vapors of A as well as vapors of B. I would say this PA, it is the contribution made by the vapors of A towards the total vapor pressure of the solution. This is the contribution made by vapors of B towards the total vapor pressure of the solution. And remember, total vapor pressure of the solution will be this partial vapor pressure of A plus partial vapor pressure of B. Now people, this partial vapor pressure of A, that means contribution made by vapors of A towards the total vapor pressure of the solution, that is directly proportional to mole fraction of A in the solution. Chi A is called as mole fraction of A in the solution. So you can say PA is equal to, put the constant P naught A chi A. So PA is equal to P naught A chi A. Similarly, PB will be equal to P naught B chi B. PB will be equal to P naught B chi B. This is something which first of all you have to remember. Now guys, try to understand what exactly I'm going to say. For example, over here, you have taken a solution. This is the solution of A and B. A as well as B both are volatile. Right? So over here, you will find vapors of A as well as vapors of B. Perfect. So vapor pressure of the solution will be equal to partial vapor pressure of A plus partial vapor pressure of B. I told you a few minutes back, partial vapor pressure of A is P naught A chi A plus P naught B chi B, right? So this is the first result which you have to remember. Total vapor pressure of the solution is always equal to P naught A chi A plus P naught B chi B, right? Now you can convert it into different format as well. You should know since in this solution, you have got liquid A and liquid B, let the mole fraction of liquid A is chi A, let the mole fraction of liquid B is chi B. Remember, chi A plus chi B is always 1. Now, what you need to do is, PS is equal to P naught A chi A plus P naught B. Instead of chi B, I am writing 1 minus chi A. And final result which I am getting generated here, that is this form. Or you can do one more thing. There is no need to replace chi B with 1 minus chi A. You can replace chi A with 1 minus chi B. And finally, this is the result which you get over here. These are some direct results, people. Well, you don't have to remember these results. You just have to remember this particular result. That is the total vapor pressure of the solution is equal to P naught A chi A plus P naught B chi B. As simple as that. How do we use this in the questions? How do we use this in the questions? How do we use this in the questions? Or before that, let me tell you one more thing. My dear students, there will be a short question asked wherein what they'll ask you, understand. Imagine this is the solution of A and B. Over here, you'll find vapors of A as well as vapors of B. They'll ask you, calculate the mole fraction of A in vapor phase. Calculate the mole fraction of B in vapor phase. Calculation of mole fraction of A in vapor phase. And let me tell you, mole fraction of A in vapor phase, remember directly, is equal to P naught A chi A divided by PS. What is chi dash A? Chi dash A is nothing but, it is the mole fraction of A in vapor phase. This chi is mole fraction of A in solution phase. That's the difference. This chi A dash, it's the mole fraction of A in vapor phase. This chi A, it's the mole fraction of A in solution phase. Similarly, mole fraction of B in vapor phase. P naught B, chi B divided by PS. What is chi B? Chi B is mole fraction of B in solution phase. Chi B dash is mole fraction of B in vapor phase. Okay, remember these two direct results as well. Now, where do we use these direct results? I'm not talking about their derivations and stuff. I've got nothing to do with that. I'll just give you the results. I'll show you how to apply them. Understand how I'm going to apply them. For example, this is the question, a simple question. The question is the vapor pressure of two pure liquids A and B. Two pure liquids means P naught A and P naught B is given to me. Calculate the total vapor pressure of the solution obtained by mixing 2 moles of A and 2 moles of B. So basically, you have got a container, and in this particular container, you have kept a solution of A and B. Number of moles of A in the solution is equal to 2. Number of moles of B in the solution is equal to 3. So Na is given, Nb is given. What am I supposed to calculate? Total vapor pressure of the solution. Total vapor pressure of the solution. I'll be just using the Raoult's law. PS, total vapor pressure of the solution is equal to P naught A chi A plus P naught B chi B. Simple. Right? So I can say PS is equal to P naught A. P naught A is 100. What is chi A? Mole fraction of A, which means moles of A divided by total moles, plus P naught B, that's 80. Mole fraction of B will be moles of B divided by total moles. Solve this, get the vapor pressure of the solution. That's it. Right? Right, people? Simple? Yes? For example, this is the question. Look at the question. Look at the question once. Look at this question, guys. The vapor pressure of pure liquid A, that means P naught A is given. How much? That is 70 torr. Okay, 70 torr. It forms an ideal solution with another liquid B. The mole fraction of B in the solution, that means chi B, is given to me as 0.2. And the total vapor pressure of the solution is how much? 84 torr. Right? What am I supposed to calculate? P naught B. Again, a simple question. Direct result-based question. Your vapor pressure of the solution is nothing but P naught A chi A plus P naught B chi B. Plus P naught B chi B, right? PS is given to me as 84 is equal to P naught is 70. Chi A. If chi B is 0.8, that means chi A will be 0.8. If chi B is 0.2, that means chi A will be 0.8 because chi A plus chi B is always 1. Plus P naught B, we have to calculate. Chi B given to me in the equation 0.2. Do you see one equation? Only one unknown P naught B. Just do the calculation, get the P naught B value. That's it. That's it. For example, you have got a question like this. A solution has 1:4 molar ratio of pentane and hexane. Let's say there is pentane present and hexane present. The ratio of their moles is given to me as how much? The ratio of their moles in the solution is given to me as 1/4. That means mole fraction of A here will be 1 by 5 and mole fraction of B will be 4 by 5. Correct? If there are P naught values, P naught A, P naught B is given, what am I supposed to calculate? Mole fraction of pentane. Let's say this is pentane, this is hexane. Mole fraction of pentane in vapor phase. So chi dash A I'm supposed to calculate. Mole fraction of A in vapor phase. How do I calculate mole fraction of A in vapor phase? Few minutes back. P naught A chi A divided by PS. This is how you do it. Now P naught A value is given. Chi A value we know. PS we have to calculate first. What is PS? PS is nothing but P naught A chi A plus P naught B chi B. Now tell me, what is P naught A? That is 440. What is chi A? 1 by 5 plus P naught B. How much? 120. What is chi B? Chi B is 4 by 5. So from here you can calculate PS, right? If you got PS, P naught A you have, chi A value you have, put the values and get the mole fraction of A in the vapor phase. Do you understand how exactly this is happening? Do you understand how exactly all of this is happening? Remember this sort of equation as well. Remember this sort of equation as well, people. Remember this sort of equation as well. If you look at this result, PT is equal to 220 minus 110 chi B. Okay. What do we have to calculate? P naught A and P naught B. P naught A and P naught B. Right? My dear students, understand one thing. If for example, chi B is equal to 0. If chi B is equal to 0. If chi B is equal to 0, that means in the solution there is no B. There will be only A present. That means A will be in pure state. Right? A will be in pure state. And vapor pressure of A when in pure state, that's equal to P naught A. So you have introduced chi B is equal to 0. So the total pressure at that time is 220. If you put chi B here as 0, you get the vapor pressure as 220. Right? If chi B is 0, that means there is only A present. So vapor pressure of A, that too in pure state, will be 220. Correct? Correct? Do you understand this? Do you understand this, people? Do you understand this? Yes? Now, if for example chi B is equal to 1, if chi B is equal to 1, that means in the solution there is only B. In the container there is only B present, right? If there is only B present, that means vapor pressure will be only due to B, that is P naught B. Now put chi B is equal to 1. When you put chi B is equal to 1, it's 220 minus 110. That will be 110. So that 110 will be the vapor pressure due to pure B only. Okay. Again, there can be a question asked on ideal, non-ideal solutions. My dear students, this is a direct table which I have come up with. Question will be directly asked from this particular table. You have to remember each and every parameter here in this particular table. Ideal solutions, non-ideal solution showing positive deviation. Anything can be asked. Delta V mixing, delta H mixing, delta S mixing, delta G mixing, observed boiling point, theoretical boiling point. And your non-ideal solution showing positive deviation, they form the minimum boiling azeotrophs. Right? Similarly, non-ideal solution showing negative deviation, anything can be asked. Delta V mixing, delta H mixing, delta S mixing, delta G mixing, observed and theoretical boiling point relation, they form the maximum boiling azeotrophs. All of that stuff. Examples of these solutions are important. See, I'm not teaching all this in detail. We don't have time for that. That's why I have directly made a table. Just remember the table. Question will be asked from this table only. Okay, question will be directly asked from this particular table. But one thing is important here. What is that? That is their examples. These are the examples of ideal solutions. Similarly, These are the examples of non-ideal solutions showing positive deviation. And these are the examples of non-ideal solutions showing negative deviation. Right? These examples are important. These examples are important. Not going into the details of what is ideal, what is non-ideal, showing positive, showing negative. Just remember the table directly that I gave you, and that's going to be super sufficient for you at this particular point of time. Okay? Now, I'm going to start with something called as colligative properties. This is again a short topic from which questions are asked. Tell me one thing, what are colligative properties? These are the properties of the solution. These are the properties of the solution whose value depends on. These are the properties of the solution whose value depends on the number of particles of solute. So such properties of the solution whose value depends on the number of particles of solute, right? What do you call those properties as? Colligative properties. How many colligative properties you have? 4. Relative lowering in vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure. Okay, let me directly write the results. What are the results? A relative lowering in vapor pressure. It is equal P naught A minus PS divided by P naught A is equal to chi B. Chi B means mole fraction of solute. Chi B means mole fraction of solute. First of all, you have to remember the results. Then I'll show you how do I apply these results in the questions. From where it comes, you have got nothing to do with that. Remember it directly. P naught A minus PS divided by P naught A is equal to chi B. Similarly, elevation in boiling point. Elevation in boiling point is represented by delta TB. Elevation in boiling point, which is nothing but it is boiling point of solution minus boiling point of solvent. Minus boiling point of solvent. And this is equal to Kb multiplied by molality of the solution. Kb is the constant. You call Kb as the molal elevation constant. This is called as molal elevation constant. Or you call it as the ebullioscopy constant. Ebullioscopy constant. And remember, it is solvent dependent. It is solvent dependent. It is solvent dependent. Similarly, when you talk about the depression in freezing point is represented by delta TF. Depression in freezing point represented by delta TF. Delta TF. My dear students, delta TF is nothing but it is freezing point of solvent minus freezing point of solution. Freezing point of solvent minus freezing point of solution. It is equal to Kf multiplied by molality of the solution. What is Kf? Kf is either called as molal depression constant or you call it as the cryoscopic constant. Molal depression constant or you call it as a cryoscopic constant. Similarly, there is something called as osmotic pressure pi. Pi is equal to MRT. Molarity of the solution, R is a constant, gas constant or solution constant you can say, T is the temperature. Or you can say pi is equal to CRT as well. Pi is equal to CRT as well. First of all, these are the results which you have to remember when it comes to your colligative properties. Now, one by one, my dear students, I'll show you what kind of questions can be framed. What kind of questions can be framed. Try to understand. Basically, in all of these colligative properties, what happens? When you put a non-volatile solute, into a volatile liquid, when you put a non-volatile solute into a volatile liquid, first of all, vapor pressure decreases, boiling point increases, vapor pressure decreases, boiling point increases, freezing point decreases. These are the 3 points which you have to remember. I did not give you derivation of all these formulas, nor am I going to give you. You just have to remember these formulas and I'll show you what kind of questions can be framed. One thing, my dear students, one thing I'm going to show you, one thing I'm going to tell you here. What is that? For example, this is a simple question. Look at the question carefully. Calculate the relative lowering in vapor pressure. That means you have to calculate the value of P naught A minus PS divided by P naught A. Right? And as you know, it is equal to what? Mole fraction of solute. This is called as the relative lowering in vapor pressure, RLVP. Is equal to mole fraction of solute, which is number of moles of solute divided by total moles present in the solution. Right? Total moles present in the solution. I believe you can easily do it. Right? I believe you can easily do it. See, calculate the relative lowering in vapor pressure if 100 grams of non-volatile solute. So how many moles of solute we have? Mass of solute That is how much? 100 divided by molar mass of solute. That's also 100. The value is 1. Are dissolved in 432 grams of water. So moles of solvent, mass of solvent divided by molar mass of solvent. Right? So NaNB you got, put it here, get the relative lowering in vapor pressure. That's it. That's it. That's it. Okay, that's it. My dear students, one more result I'll be giving you. What is that result? Remember for dilutes, remember there is one direct result which I'm going to give you. What is that? That is P0A minus PS divided by PS is equal to NB divided by NA. This also one result which you can use in the for questions. I mean, this will simplify a bit of calculations. This result, it simplifies a bit of calculations. How exactly? It simplifies a bit of calculations. Let me show you a question for that so that you'll understand it. For example, if you look at this question, what weight of non-volatile solute, urea, needs to be dissolved in 100 grams of water in order to decrease its vapor pressure by 20%? Look at the question. For example, in this particular container, you have got 100 grams of water. The mass of solvent here is 100 grams, right? Let the vapor pressure of this water right now in pure state is P0A. Okay. Now you are introducing some non-volatile solute. Which one? That's urea. You are introducing urea here. When you introduce urea here, what happens? On adding non-volatile solute into volatile liquid, what happens to vapor pressure? Vapor pressure decreases. We have to decrease the vapor pressure. How much? We have to decrease the vapor pressure 20%. If the initial vapor pressure was P0A, vapor pressure of this solution should be 20% lesser. That means it should be 0.8 P0A. Okay. What mass of solute needs to be added in order to decrease the vapor pressure by 20%? That is the question. So what you can do? You can say P0A minus PS divided by PS is equal to NB divided by NA. Right? What is P0A? Write it as such. P0A minus PS is 0.8 P0A divided by PS is again 0.8 P0A is equal to what is NB? Number of moles of solute, which is mass of solute. I need to calculate. Divided by molar mass of urea, that's 60. Divided by NA, mass of solvent. Moles of solvent, that is mass of solvent divided by molar mass of solvent, molar mass of water. P0A gets cancelled. So you can easily calculate mass of solute here. Also, you have to calculate molality of this solution. If you want to calculate molality of this solution, that will be mass of solute multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent in grams. WB, you have calculated from here. Molar mass of solute, you already know. Molar mass of urea, that's 60. Mass of solvent, that's given to me as 100. Put the values and get the molality. So that's how you can solve this sort of a question as well. I believe you can easily do this sort of a question. As I told you, there is something called as elevation in boiling point. So basically, when you add a non-volatile solute into a volatile liquid, boiling point increases. And that increase in the boiling point is what you call as elevation in boiling point, represented by delta TB. And as I told you, this delta TB, elevation in boiling point, which is basically the boiling point of solution minus boiling point of what? Minus boiling point of solvent. This is equal to Kb multiplied by M. One direct result. You can use the formula in the question. And by the way, you have to remember these two values as well. That is Kb for water, you have to remember. Kb for water and Kb for benzene. And there's a formula to calculate Kb as well. That is R T naught square divided by 1000 lV, M1 R T naught square divided by 1000 delta H vaporization. Now, what are these terms? T naught, delta H vaporization. I mentioned all of this here. T naught is the boiling point of solvent. LV is latent heat of vaporization, or you can say vaporization per gram of solvent. Delta H vaporization is called as latent heat of vaporization per mole of solvent. Well, question won't be asked from this. Sometimes, there is very less probability question will be asked from here. Very less probability is there. You have to remember the actual formula. Actual formula is delta TB is Kb multiplied by M. And these 2 points are important. Kb value for water and Kb value for benzene. Okay. Now, look at the question. What will be asked to you? Look at the question. What will be asked exactly? What weight of sucrose should be added? So I have to calculate mass of sucrose, mass of solute. What weight of sucrose should be added to 100 grams of solvent, to 100 grams of water, to have the boiling point of solution. to have the boiling point of solution, equal to 100.5 degree. So first of all, your solvent is water. What is the boiling point of water? What is the boiling point of solvent? Boiling point of solvent is equal to 100 degree. You know that. Boiling point of water is equal to 100 degree. Boiling point of solvent is 100. Now, what weight of solute, what weight of sucrose should be added to 100 grams of water to have its boiling point as 100.5? Again, the question is based on elevation and boiling point. So you can use the result directly. Delta TB is equal to KB multiplied by M. So delta TB is boiling point of solution minus boiling point of solvent. That will be 0.5 is equal to KB value. You already know that is 0.52. Molality of the solution is mass of solute, which I need to calculate, multiplied by 1000. Molar mass of sucrose, 342. Mass of solvent in grams, that's 100. Again, bit of calculation is needed, and you can calculate WB from here. Mass of solute you can calculate from here. Guys, I know I'm very quickly doing all this, but we have to do it like this only. Then only entire thing will get completed. This is your homework question. Just read the question and tell me in the chats if you can solve this. Read the question once and tell me in the chats if you can solve this. Read the question and tell me if you can solve this. Quick. Will you be able to do it? Perfect, guys. Now, what happens in depression and freezing point? What happens in depression and freezing point? When you put a non-volatile solute into a volatile liquid, freezing point decreases. And that decrease in the freezing point is called as depression of freezing point, delta TF. And delta TF, I already gave you the formula. It's equal to KF multiplied by M. KF multiplied by M. Now, there can be question asked from this as well. But before that, you have to remember KF values for water and KF values for benzene. And this is the general formula by means of which you can calculate KF. This is the general formula by means of which you can calculate KF, which I'll show you after some time. What do you think? Will you be able to solve this one? Can you solve this question? The question is find the freezing point of the solution obtained by mixing 18 grams of glucose in 90 grams of water. We have to calculate freezing point of solution. You know your delta TF is basically equal to KF multiplied by M. Delta TF will be freezing point of solvent. Solvent is water, I think, yes. And freezing point of water is 0 degree minus freezing point of solution. I have to calculate. Freezing point of solution I have to calculate is equal to KF value is 1.86. Molality will be equal to mass of solute multiplied by 1000 divided by molar mass of solute, molar mass of glucose 180 multiplied by mass of solvent, that is 90. Again, matter of calculation and get the freezing point of solution. So you will be able to solve this sort of a question as well. These are all direct formula based questions. Check this one. Will you be able to solve this one? Will you be able to solve this one? It is a similar sort of question. 2.5 grams of ethylene glycol is added to 20 grams of water. Find the freezing point of solution. KF is given. So again, the formula delta TF is equal to KF multiplied by molality. Again, the similar sort of question. Again, the similar sort of question. Now, there is something called as osmotic pressure. What is osmotic pressure basically? My dear students, imagine in this chamber, you have got pure solvent present. In this chamber, you have got pure solvent present. In this chamber, you have got solution present. This is solvent, this is solution. Whenever solvent and solution will be in direct contact with the help of a semi-permeable membrane. Whenever solvent, pure solvent and the solution will be in direct contact with the help of semi-permeable membrane, there will be net movement of solvent molecules. There will be net movement of solvent molecules from solvent side to solution side. There will be net movement of solvent molecules from solvent side to solution side, right? Due to which the piston you can see here, it will start rising upwards, it will start going upwards. But if you do not want this piston to go up, you have to apply pressure from the top. The minimum excess pressure which has to be applied on the solution side, to stop the net movement of solvent molecules. the minimum excess pressure that has to be applied on the solution side to stop the net movement of solvent molecules from solvent side to solution side, that's called as osmotic pressure, pi, which is MRT, CRT, which is MRT, CRT, right? Which is MRT or CRT. And my dear students, remember one more thing. Whenever you will be having two solutions which have got same osmotic pressure, two solutions having same osmotic pressure, we call those solutions as isotonic solutions. Two solutions which have same osmotic pressure, you call those solutions as isotonic solutions, or you can call them as isoosmotic solutions. You can call them as isoosmotic solutions as well. Okay? And whenever you see two solutions having same osmotic pressure, pi 1, pi 2 equal, right? Their molarities, their concentrations will be also equal. Their concentration will be also equal. Okay? So two isotonic solutions, their osmotic pressure will be equal. Their temperature is already same. And their molarities, their concentrations will be same as well. And here do remember, if my dear students, if you have got two solutions, first solution has got osmotic pressure pi 1, second has got pi 2. If pi 1 is greater than pi 2, then I can say solution 1 is hypertonic to solution 2, or solution 2 is hypotonic towards solution 1. And if pi 1, pi 2 is equal, we call them as the isotonic solutions. We call them as the isotonic solution. Okay? For example, this is the question. This is the question, guys. This is the question. Calculate osmotic pressure at 273 Kelvin of a 5% weight by volume solution of urea in ATM. Look at this. What do we have to calculate? Osmotic pressure. There is 5% weight by volume. What does that mean? That means 5 grams of urea are present in 100 ml of solution, right? Are present in 100 ml of solution. What do you have to calculate? I have to calculate osmotic pressure pi. Pi is equal to, MRT, right? Pi is equal to, M means molarity of the solution. Number of moles of solute divided by volume of solution in liters multiplied by R multiplied by T. Number of moles of solute will be mass of solute. That's 5. Molar mass of solute, molar mass of urea. Volume of solution in liter. This is the volume of solution in ml. Convert in liter. That means 0.1. I have to get the answer in ATM. So I'll use the R value as 0.0821. And temperature is given to me as 273, I think. Yeah. Solve this and get the answer in ATM. These sort of questions are asked. These sort of questions are asked. These sort of questions are asked. A 4% solution of sucrose. A 4% solution of sucrose is isotonic with 3% solution of unknown organic substance. So we have got two solutions, sucrose and organic substance. They are isotonic. Isotonic means their osmotic pressures are same. Now the point is, 4%, what does that mean? That means 4 grams of sucrose are present in 100 ml solution. Similarly, it is 3%. That means 3 grams of organic substance is present in 100 ml solution. Correct? Their osmotic pressure is same. That means pi 1, pi 2 is same. If their osmotic pressure is same, that means their molarity should be same as well. What is molarity? Molarity of this is number of moles of solute, which means mass of solute divided by molar mass of solute divided by volume of solution in liters. Right? Volume of solution in liters. So VV also gets cancelled out on both the sides. M2, number of moles of organic substance. That is mass of organic substance divided by molar mass of organic substance divided by V. VV already has got cancelled on both the sides. So from this particular equation, you can calculate a molar mass of organic substance by just cross multiplying things. Yes? This sort of equation can be easily done. So you have got isotonic solutions, their molarities will be same, right? Their molarities will be same. So technically their moles will be same because volume will get cancelled on both the sides. Volume will get cancelled on both the sides. These are two important points, guys. Do remember these points. Okay. Best method to determine molecular weight of biomolecules like proteins and polymers is osmotic pressure, right? And this particular point as well, 0.91% weight by volume NaCl is isotonic with blood. These are some memory-based things. Anything can be asked out of these 2 points. Remember these two as well. Okay, and these two are mentioned in your NCERT. Now comes one point. That is your Van 't Hoff factor. That is your Van 't Hoff factor. My dear students, relative lowering in vapor pressure. If you talk about your relative lowering in vapor pressure, relative lowering in vapor pressure means P0 A minus PS divided by P naught A. That's equal to chi B as per the formula. Elevation and boiling point, that's your delta TB, is equal to KB multiplied by M. Depression and freezing point, delta TF is equal to KF multiplied by M. Osmotic pressure, pi, is equal to CRT. All these are colligative properties. All these are colligative properties. My dear students, these formulas are not 100% accurate. They are not going to give you 100% correct answers. These formulas are not going to give you 100% correct values of relative lowering, elevation, depression, or osmotic pressure. You have to correct them. You have to correct them. And that correction factor is called as Van 't Hoff factor. That factor by means of which you correct these formulas, you call that as the Van 't Hoff factor. You correct them as the Van 't Hoff factor. So why there is the correction needed? Why these formulas do not give the correct values? There's a logic. Because sometimes the solute which is introduced in the solvent, that either dissociates or associates. If the solute dissociates or associates, then Van 't Hoff factor I needs to be introduced. And when the solute undergoes dissociation, I value is calculated as 1 plus n minus 1 into alpha. When the solute undergoes association, I is calculated as 1 divided by 1 by n minus 1 into alpha. This is the case when the solute undergoes dissociation. And when the solute neither dissociates nor associates, I value is taken as 1. So without I, these formulas are valid only for those solutes which do not dissociate or associate. But if you have solute that dissociates or associates, you have to consider I as well. And this is how you calculate I when the solute undergoes dissociation. This is how you calculate I when the solute undergoes association. I value is 1 when it comes to your solute which neither dissociates nor associates. So how do I use this? And one more thing, guys. One more thing. In case of dissociation, remember I is equal to 1 plus n minus 1 into alpha. So I and n, they are directly proportional here. In case of association, when the solute undergoes association, I is equal to 1 plus 1 by n minus 1 into alpha. Right? I is inversely proportional to n here. Now if you see, let's say you have got solute like NaCl. How NaCl dissociates? Na positive plus Cl negative. Do you see one particle is giving 2 particles? So n value is 2. One particle is giving 3 particles, n value is 3. 2 particles are giving 4 particles. If 2 are giving 4, that means 1 gives 4 by 2. That means n value is 2. So this is how you get the n value. Number of particles of product which you get from one particle of reactant. But here in case of association, how do you calculate n? See, 2 particles are associating to form 1 particle. So n value is 2. 3 particles are associating to form 1 particle. N is 3. 4 particles are associating to form 1 particle. N is 4. So that's how you calculate n in case of dissociation and in case of association. And remember, in case of dissociation, I value is always greater than 1. In case of association, I value is always less than 1. Now, how can I solve the questions based on this? Before solving the questions based on this, remember there is one more way of calculating I. I is equal to MC divided by M naught. What is MC and what is M naught? MC is called as calculated molecular weight. Calculated molecular weight of solute. Calculated molecular weight of solute divided by what is M naught? M naught is called as observed molecular weight of solute. Observed molecular weight of solute. Now, my dear students, from this formula also question can be asked. I is equal to MC divided by M naught. MC is calculated molecular weight of solute, observed molecular weight of solute. Now, for example, this is the question. The values of observed and calculated molecular weights. Observed and calculated is given to me. How much? Is given to me as 92.64 and 170 grams respectively. What do we have to calculate? We have to calculate alpha value for AgNO3. Tell me first of all one thing. How AgNO3 undergoes dissociation? It undergoes dissociation as Ag positive plus NO3 negative. What is the value of N for this reaction? One particle is giving 2 particles, so N value is 2. Since this is the case of dissociation, I is equal to 1 plus N minus 1 into alpha. Right? First of all, how can I calculate I? I is equal to MC divided by M naught. MC is 170. M naught is 92.64. This value will be approximately 1.8. Put the value of I as here. 1.8 is equal to 1 plus 2 minus 1 into alpha. So from here you can calculate alpha. Alpha will come out be 0.8. Like this question can be asked. Like this question can be asked, right? Like this your question can be asked. Similarly, for example, The question is the degree of dissociation. The degree of dissociation of a weak electrolyte AXBY. So we have got the weak electrolyte AXBY. How will it undergo dissociation? It undergoes dissociation as X times AY positive plus Y times BX negative. So one particle is giving X plus Y particles. So N is nothing but X plus Y. How do we calculate I? I is equal to 1 plus N minus 1 into alpha. So I is equal to 1 plus N value is X plus Y minus 1 into alpha. So I would say alpha will be equal to I minus 1 divided by X plus Y minus 1. This is something which you are supposed to calculate. This is something which you are supposed to calculate. Okay. Similarly, guys, for example, this is a question. Hg2Cl2, it's a special case. Hg2Cl2, mercurous chloride, how will it undergo dissociation? It undergoes dissociation as Hg2 di positive plus 2 times Cl negative. This is how it undergoes dissociation. It is 80% ionized. 80% ionized means alpha is 0.8. What do I have to calculate? Van't factor. I is equal to 1 plus N minus 1 into alpha. So I is equal to 1 plus N values. One particle is giving 3 particles. So N is 3 minus 1 into alpha. How much is alpha? Alpha is already 0.8. So this is 1 plus. This is 2 into 0.8, 1.6. 1.6 plus 1 is 2.6. Right? Remember, this Hg2Cl2 undergoes dissociation like this. Hg2 di positive plus 2 times Cl negative. Alright? Similarly, you can solve this sort of equation as well. Millimolar solution. Millimolar means molarity 10 raised power minus 3. K3FeCN6. How will it undergo dissociation? 3 times K positive, FeCN6 trinegative. One particle is giving 3 plus 1, 4 particles, so N value is 4. 70% ionized. That means alpha is equal to 0.7. Alpha is equal to 0.7. Find the osmotic pressure. So pi will be equal to ICRT. Since it undergoes dissociation, so you have to take I into consideration as well. I is equal to ICRT. So first of all, you need to get the I value. I is equal to 1 plus N minus 1 into alpha. 1 plus N value is 4 minus 1 into alpha. So I value you got as 3.1. Put the value of I here. Concentration molarity is 10 raised power minus 3. R value is this, and this is the temperature. Solve this, get the osmotic pressure. These are some simple questions only, right? Which will be asked in your examination. Correct? Now let's move on to your electrochemistry chapter. Let's move on to your electrochemistry chapter. In electrochemistry, again, there are some short topics. What? The question will be either asked from Daniell cell, or the question will be asked from electrode potential. Electrode potential. The question will be asked from your Nernst equation. Nernst equation. Or the question will be asked from your electrolysis part. Electrolysis. Your Faraday's laws of electrolysis. Faraday's laws of electrolysis, right? And at the end, Kohl-Ross law. These are the topics from which question will be asked in the chapter electrochemistry. But electrochemistry will be starting after a small break of 10 to 15 minutes, right? So the time is 12:36. We'll start at okay? But be back on time. Be back on time, guys. Be back on time. I'll see you exactly at 12:50. And this will take almost 1 hour to complete electrochemistry. Okay? All right? So I'll see you exactly at 12:50. Okay, you have got 15 minutes break. Be back on time. See you now. Everyone back? Hello guys. Let's try to revise this particular chapter quickly as well. Okay. So first of all, you have got the Daniell cell here. If I ask you what is the work of Daniell cell, what does the Daniell cell do? Daniell cell is the example of what? It is the example of ganglionic cell. And what does it do? It converts your chemical energy into electrical energy. It converts chemical energy into the electrical energy. Your Daniell cell. And as you all must be knowing, in the Daniell cell, how many electrodes do we use? We use 2 electrodes. One is your zinc, one is copper, right? And these 2 electrodes are connected externally with the help of voltmeter and internally with the help of salt bridge. Internally with the help of salt bridge. This zinc electrode, it behaves like your anode, and copper electrode, it behaves like the cathode. And remember, at anode, what happens? At anode, oxidation takes place. And at cathode, reduction takes place. At cathode, reduction takes place. Now, since at anode oxidation takes place, this rod is made up of zinc atoms. This rod is made up of zinc atoms. And those zinc atoms will undergo oxidation, will get converted into zinc dipositives, and with that, you'll be getting 2 electrons. Similarly, on this particular electrode, what happens? A reduction takes place. Copper dipositives which are there in the solution, they collide with the rod, they take 2 electrons from the rod and get converted into copper solid. Right? Now, what all things will be asked from here basically? From your Daniell cell. In your Daniell cell, the first question will be asked, in which direction electrons move? That's the first question. Remember, in your Daniell cell, the electron movement is from anode to cathode. Electrons go from anode to cathode. This is the first question that will be asked. Second question, what is the direction of current? Current is from cathode to anode. Thickness of zinc rod, that decreases with time. And thickness of copper rod, that increases with time. These are some direct theoretical questions which can be asked. The first one, direction of electrons, anode to cathode. Direction of current, cathode to anode. Thickness of zinc rod, that decreases with time. Thickness of copper rod, that increases with time. Now, what are the uses of salt bridge? First of all, your salt bridge, it completes the internal circuit of the cell, number 1. Your salt bridge, it maintains the electrical neutrality of both the solutions. And at the same time, it avoids the liquid junction potential. Just remember these 3 points, my dear students. Remember these 3 points. These are the main functions of your salt bridge. Number 1, completes the internal circuit, maintains the electrical neutrality of both the solutions, and it avoids the liquid junction potential, right? Similarly, my dear students, in the salt bridge, what do we keep? In the salt bridge, we keep inert electrolyte. What are the examples of inert electrolytes which we keep inside the salt bridge? It can be NH4NO3, KNO3, NH4Cl, KCl, etc. These are the inert electrolytes which are mixed with gelatin or agar-agar, and then we put them inside the salt bridge. So these are some direct questions. What all questions? Number 1, direction of electrons from anode to cathode. Direction of current from cathode to anode. Zinc rod dissolves with time. Thickness decrease with time. Copper rod, thickness increase with time. Functions of salt bridge. Salt bridge, it, what does it do? It completes the internal circuit. Number 2, it maintains the neutrality of both the solutions. Number 3, it avoids the liquid junction potential. Okay? Now, how do we exactly represent a galvanic cell? It's also a simple thing. For example, if you talk about your Daniell cell, in the Daniell cell, the net reaction is like this. This is the net reaction in what? This is the net reaction in Daniell cell. Now, by looking at the net reaction, you should be able to represent the cell. By looking at the net reaction, you should be in a position to represent the cell. And how do we represent it exactly? Have a look. What is the oxidation state of zinc here? 0. This copper is in +2. This zinc is in +2. And this copper is in 0. Now check. 0 to +2. 0 to +2. Increase. Increase in the oxidation state means oxidation. And oxidation takes place at anode. +2 to 0. Decrease. Decrease in the oxidation state is called as a reduction. And reduction takes place at cathode. So first of all, you have checked which one is your anode and which one is your cathode. Now, you'll just draw two lines. These two lines, they represent the salt bridge. On the left side of the salt bridge, you always write anode. On the right side of the salt bridge, you always write cathode. Now, how do I represent this? Have a look. These two lines are your salt bridge. On the left side, what do we write? Anode. At anode, oxidation takes place. Zinc gets converted into zinc dipositive. I would say zinc solid is getting converted into zinc dipositive aqueous. Now, tell me one thing. Is the phase same or different? This is solid, aqueous. The phase is different. When the phase is different, you put a slash. If the phase was same, you put a comma. If the phase was same, you put a comma. If the phase is different, you put a slash. Now on the right side, what do we write? We write cathode. At cathode, reduction takes place. Copper dipositive gets converted into copper solid. So copper dipositive aqueous is getting converted into copper solid. Now tell me one thing. Is the phase same or different? The phase is different. So put a slash in between. So this is how you represent a Daniell cell, right? Similarly, for example, you have got some cell whose net cell reaction is this one. By looking at the net cell reaction, you should be able to represent the cell. Now, how do you represent it? Again, zinc, its oxidation state is 0. Hydrogen, it is in +1 oxidation state. This zinc, +2 oxidation state. This hydrogen, 0 oxidation state. So 0 to +2, 0 to +2, increase. Increase means oxidation. That means anode. If this is anode, this automatically becomes your cathode. Now, in the middle, salt bridge. Left side, anode. At anode, zinc solid is getting converted into what? Is getting converted into zinc dipositive aqueous. Is the phase same or different? Different. Put a slash. On the right side, cathode. At cathode, H positive aqueous is getting converted into what? H2 gas. Is phase same or different? Different, right? Now, this is a hydrogen electrode. So, I'll be using platinum solid as well on this side because it's a hydrogen electrode. Okay. Now, my dear students, there is one more thing. There is one more thing which you need to know. For example, let's say you have to represent this particular cell. Okay, leave the representation aside. For example, let's say you're given with the cell like this. Zinc solid, zinc dipositive aqueous, salt bridge, copper dipositive aqueous, and copper solid. Let's say this is the cell that is given to me. Now, by looking at the cell, I should be able to write the reactions. I should be able to write the cell reactions. How do I write the cell reactions basically? First of all, on the left side of the salt bridge, we always have anode. On the right side of the salt bridge, what do we have? We have cathode. Now, at anode, what happens? Oxidation. And oxidation means loss of electrons. Your zinc gets converted into zinc dipositive. So, I would say zinc solid would be losing 2 electrons. Zinc solid would be losing 2 electrons, then getting converted into zinc dipositive. Similarly, what reaction takes place at cathode? At cathode, reduction takes place. Copper dipositive gets converted into copper solid. So, copper dipositive would be gaining 2 electrons and getting converted into copper solid. Tell me, are the electrons balanced in both the reactions? Yes. 2 electrons, 2 electrons. Just add these two reactions. When you add these two reactions, you get the value of N from here. You get the value of N from here. And your net reaction becomes something like this. Zinc solid plus copper dipositive aqueous. What does it give me? It gives me zinc dipositive aqueous. And with it, you get copper solid as well. So this is your net reaction. And once you write the net reaction, you should be in a position to write reaction quotient expression as well. And how do you write reaction quotient expression? You start with the product. This product is in aqueous state. The one that's in aqueous state, use its concentration. So I'm writing concentration of zinc dipositive raised power stoichiometric coefficient 1. The one that's in solid state, you have got nothing to do with that. Divided by, go to the reactant side. This is in solid state, nothing to do with that. This is in aqueous state, so write its concentration. So this concentration of copper dipositive raised power stoichiometric coefficient 1. So this is how you write reaction at anode, reaction at cathode, N value, and QC expression. Simple. Now, my dear students, there's a famous question which is asked based on significance of electrode potential. Significance of electrode potential. So first of all, you should know one thing. Electrode potential, my dear students, gives us electrode potential. It gives us a tendency. It gives us the tendency of an element. It gives us the tendency of an element to undergo oxidation, or reduction. To undergo oxidation or reduction. Electrode potential. It gives us the tendency of an element to undergo oxidation or reduction. Now, you should know electrode potential is basically of two types. One is called as oxidation potential. One is called as the reduction potential. Now, this oxidation potential, it gives me the idea about the it gives me the tendency of an element to undergo oxidation. And this reduction potential, it gives me the idea about, it gives me the tendency of an electrode to undergo what? To undergo reduction. Whenever electrode potential is calculated under standard conditions, whenever electrode potential is calculated under standard conditions, that means when pressure is kept 1 bar, temperature is kept constant, generally 25 degrees centigrade, and similarly when your concentration is kept, when concentration is kept 1 molar, these conditions are what you call as standard conditions. And when electrode potential is measured under standard conditions, you call it as standard electrode potential. And even this standard electrode potential is of two types. One is called as standard oxidation potential. One is called as standard reduction potential. You can either call it as SOP. You can call it also as SOP. Even you can call it as SRP, standard reduction potential. Similarly, my dear students, remember one more thing. For every element, SOP is nothing but it's minus times SRP. For example, if you know SOP of some element, you can easily calculate its SRP by just reversing the sign, right? Now see, for example, I'm writing E naught of zinc gives zinc dye positive. If I ask you, is it SOP or SRP? How do you check? See, 0 to plus 2, increase. Increase means oxidation. So this is SOP. This is SOP. Let it be 0.76 volt. Now tell me, E naught of zinc dye positive gives zinc is equal plus 2 to 0. Plus 2 to 0. Decrease in oxidation state. Reduction. So this SRP. It will be simply minus 0.76 volt. Okay. So SOP is equal to minus times its SRP. Right? Simple. Similarly, guys, there is one more thing which I would want to tell you. What is that? Whenever you have hydrogen electrode, in case of hydrogen electrode, let me tell you, SOP as well as SRP, both the values are taken as 0. SOP as well as SRP, both the values are taken as 0 when you have got the electrode as hydrogen electrode. Okay. Now, remember one simple thing. Reducing power is directly proportional to SOP. And oxidizing power is directly proportional to SRP. Even reducing power, or you can say reducing agent. Oxidizing power, or you can say oxidizing agent. These are the two things by means of which you can do basic questions. Your reducing power is directly proportional to SOP. Oxidizing power is directly proportional to SRP. For example, let's say I'm writing you a question. From this question, you can easily understand it. If you look at all these reactions, my dear students, is gain of electrons happening or loss of electrons? Gain of electrons happening everywhere. Gain of electrons means reduction. So which values these are? These are your SRP values. All of these are your SRP values. How to arrange on the basis of oxidizing power? You know oxidizing power is directly proportional to SRP. Now check which one has got maximum SRP value. Maximum SRP, that's plus 1.81. So this cobalt tripositive, maximum SRP, maximum oxidizing power. So cobalt tripositive will have maximum oxidizing power, followed by 1.67, that's for Pb plus 4, right? Followed by, that's 1.67, that is cerium plus 4. Followed by, that is bismuth tripositive at the end, right? So this is the order of oxidizing power. Got it? Questions like these will be asked in your examination for sure. Similarly, guys, let's say this is the question. We have to arrange them on the basis of their reducing power. Now, you know, reducing power is directly proportional to what? SOP. Which values these are? Gain of electrons, reduction. So these are SRP values. What do I need? I need SOP values. So SOP of this will be 0.76. This will be plus 2.87. This will be plus 2.36. And this will be plus 0.25. Now, which one has got maximum SOP? This is the maximum SOP. That's for calcium. Maximum SOP means maximum reducing power. So calcium will have maximum reducing power. After calcium, I'll prioritize this one, 2.36 value. That's for magnesiums, right? So it's option 2. Right? It's option 2. Simple and basic stuff. There is one more thing. You'll be asked to calculate standard EMF of the cell, E naught cell. How do I calculate E naught cell, standard EMF of the cell? It is simply equal to E naught cathode minus E naught anode. It is simply equal to E naught cathode minus E naught anode. What is E naught cathode? This is called as your SRP of cathode. This is called as your SRP of anode. Now, for example, I'm writing something like this. E naught of A positive gives A is equal to 2 volt. Let's say E naught of B gives B negative is equal to minus 5 volt. Now, my dear students, if I ask you how many electrodes do we have? We have 2 electrodes, as you can see, 1 and 2. For example, I'm connecting these electrodes externally as well as internally. I'm connecting these electrodes externally as well as internally. Can I say I'll get a one complete cell? And I want to calculate E naught cell. I want to calculate E naught cell of that complete cell. First of all, I should know out of these two electrodes, which one is anode, which one is cathode. Tell me one thing. +1 to 0, decrease, reduction. So this SRP. 0 to -1, decrease, reduction. So this also SRP. Which one is more? This has got more SRP. More the SRP, more the tendency to undergo reduction. Reduction takes place at cathode. So this is cathode, this anode, right? So E naught cell is nothing but it is E naught cathode minus E naught anode. So it is SRP of cathode. SRP of cathode, that's 2 minus SRP of anode, that's -5. The value comes out be simply as 7 volt. The value simply comes as 7 volts. Similarly, my dear students, there is one more thing that will be asked here. What is that? Or before doing that, for example, you have got a question like this. You are given the cell. You have to calculate its E naught cell. You know E naught cell. How do we do it? It is E naught cathode minus E naught anode. If you look carefully, zinc is undergoing oxidation here. Oxidation. So, zinc is your anode, this is your cathode. Perfect. Now, whether these values are SOP values or SRP values, loss of electrons, loss of electrons, loss of electrons means SOP. What do I need? I need SRP values. I always need SRP values, right? So, E naught of cathode, this is the SRP of cathode minus SRP of anode. SRP of cathode, SRP of cathode, SRP of iron. SRP of iron is how much? SRP of iron is -0.41 minus SRP of anode. SRP of anode, anode is zinc. SRP of zinc is -0.76. The value comes out to be how much? 0.35 volts. Right? This is how you calculate E naught cell. Perfect. Similarly, guys, there is one more result which you need to know. What is that? That is the relation between delta G of the cell. That is the relation between delta G of the cell and EMF of the cell. Delta G of the cell and EMF of the cell. My dear students, what is the result? The result is something like this. Delta G is equal to minus NF E cell. This is the result. And if you write the same expression under standard conditions, let me tell you, under standard conditions, the same result can be written as delta G naught is equal to minus NF E naught cell. Minus NF E naught cell. Now remember, my dear students, whenever you have got a cell whose delta G will be negative or E cell will be positive, whenever you see a cell whose delta G is negative or E cell is positive, remember in that cell reactions are spontaneous. That means the cell will be working. Cell works. Cell works means the cell produces current and the direction of current will be from cathode to anode. Similarly, there is one more thing which you need to remember. Whenever you have got the cell whose delta G is positive, or I would say E cell is negative, delta G positive, E cell is negative. Remember, in that particular cell, the cell reactions are non-spontaneous and the cell does not work. And remember, whenever you have got the cell whose delta G is 0, or I can say E cell is 0, delta G is 0 or E cell is 0, we say the cell is at equilibrium. We say the cell is at equilibrium. And at equilibrium, there is no current generated by the cell. These are again the three important points which you need to remember. And at the same time, one more thing I would want to add here. Your delta G, it is an example of extensive property, and your E, it is the example of intensive property. It is the example of intensive property, right? Now, the main thing from which question will be asked here, what is that? That is going to be your Nernst equation. That's going to be a Nernst equation. I'm not going to derive the Nernst equation. I'll just tell you how to write the Nernst equation. Nernst equation is written like this. E cell is equal to E naught cell minus 0.0591 divided by N and its log of QC. This is how you write Nernst equation. And with the help of Nernst equation, what can we calculate? We can calculate EMF of the cell. We can calculate EMF of the cell under non-standard conditions. Under non-standard conditions, right? Similarly, Nernst equation sometimes can be written like this. EOX is equal to E naught OX minus 0.0591 divided by N log of QC. When do we write Nernst equation like this? Whenever you are supposed to calculate oxidation potential of an electrode, oxidation potential of the half cell of the electrode under non-standard conditions, you can write Nernst equation in this format. Sometimes you'll write Nernst equation like this. ERED is equal to E naught RED minus 0.0591 divided by N and its log of QC. Now, when do I write Nernst equation like this? Say, whenever I'm supposed to calculate the reduction potential of the electrode under non-standard conditions. reduction potential of the electrode, yeah, reduction potential of half cell under non-standard conditions, then you write Nernst equation like this, right? So these are the three ways by means of which you can calculate either EMF of the cell under non-standard conditions, oxidation potential of the half cell under non-standard conditions, even reduction potential of the half cell under non-standard conditions. Now, for example, this is a small question, right? Let's try to do this. You'll understand what we have to do. See, calculate the oxidation potential. Since we have to calculate oxidation potential, so what do I do? Since we have to calculate oxidation potential, what do I do? I'll make sure that this electrode behaves like anode, because at anode oxidation takes place, and we are supposed to calculate oxidation potential. See, iron is getting converted into Fe dye positive. So the reaction has to be Fe solid getting converted into what? Fe dye positive aqueous, and with that you are adding 2 electrons. So what is the value of N here? N value is 2, right? If I ask you the QC expression, QC is going to be concentration of Fe dye positive raised par stoichiometric coefficient 1 divided by, this is solid, nothing to do with that. What is the concentration of Fe dye positive? Concentration of Fe dye positive is 0.1 molar. That means 10 raised par minus 1. So N you got, QC you got. What do you have to calculate? Oxidation potential. Oxidation potential is equal to E naught OX minus 0.0591 divided by N, and it's log of what? Log of QC. You have all the values. E naught OX. E naught OX, this is the standard oxidation potential. But I'm given with standard reduction potential. So convert it into standard oxidation potential. So this is plus 0.44 minus 0.0591. N value here is 2, and it's log of QC. QC value is nothing but 10 raised par minus 1. Just a bit of calculation, and you can calculate oxidation potential of the half cell. Got it how? Is it clear? Is it clear? Is it clear? Yeah, like this, small questions will be asked, and you can easily solve them, guys. Easily solve them. For example, you have got one more question. Calculate the oxidation potential of this half cell. We have to calculate oxidation potential of this half cell. See, here it is 0, here it is in +1 oxidation state, right? So, if in order to calculate oxidation potential, I'll make sure the electrode behaves like anode, so that at anode oxidation takes place. What will be the reaction? The reaction will be H2 gas should get converted into twice H positive, and with that you will be having 2 electrons. If I ask you N value is 2. If I ask you QC is going to be concentration of H positive raised par 2 divided by pressure of H2. Pressure of H2 is 10, right? So concentration of H positive, that is 0.1, means 10 raised par minus 1 ka square divided by 10. So this value will come out to be 10 raised par minus 3. So if you got QC, you got N, you can calculate oxidation potential, which is equal to E naught OX as per Nernst equation minus 0.0591 divided by N and log of QC. Now put the values. Since we are talking about hydrogen electrode, and for hydrogen electrode, SOP as well as SRP both are 0, this will be minus 0.0591, N value is 2, log of QC. QC value is 10 raised par minus 3. Again, a matter of calculation. The answer will be in volts, right? So like this, questions will be asked, and sometimes they'll ask you to calculate what? Sometimes they'll ask you to calculate the EMF of a complete cell. For example, you have got a question like this. I'm writing a cell, zinc solid, zinc dye positive aqueous, concentration for example 10 raised par, or let's keep it as 0.1 molar, salt bridge, copper dye positive aqueous, 0.1 molar, and this is copper solid. And they'll give you the values like this. E naught, zinc gives zinc dye positive, is equal to 0.76 volt. E naught, copper dye positive gives copper, is equal to 0.34 volt. Now they'll ask you to calculate EMF of this complete cell. Sometimes this sort of a question can be asked. How do we solve? How do we get the EMF of a complete cell? How do we calculate EMF for the complete cell? See guys, it's pretty much simple again. First of all, can you tell me the reaction at anode? Absolutely. Zinc is getting converted into what? Zinc gets converted into zinc dye positive aqueous, and with that you have got 2 electrons. Similarly, what would be the reaction at cathode? Your copper dye positive aqueous will be gaining some 2 electrons and getting converted into copper solid. Electrons are balanced, so you can directly add them. So 2 electrons got cancelled, N value is 2. Your net reaction comes like this: zinc solid plus copper dye positive aqueous. What does it give? It gives zinc dye positive aqueous, and with that you have copper solid. This is your net reaction. Now, net reaction you got, N value you got. Now you just have to calculate QC. How do you get the QC? QC is simply going to be concentration of zinc dye positive. What is the concentration of zinc dye positive here? If you look carefully, concentration of zinc dipositive is 0.1 molar divided by concentration of copper dipositive. That is again 0.1 molar. So QC value is coming out to be 1. QC value is coming out to be 1, right? QC value is coming out to be 1. You got N value, you got QC value. Now I have to calculate E naught cell. E naught cell is equal to E naught cathode minus E naught anode. E naught cathode minus E naught anode, right? E naught cathode means SRP of cathode. SRP of cathode means SRP of copper, 0.34. Minus SRP of anode. This is SOP of anode. I need SRP, 0.76. The value is 1.1. This is your E naught cell. But as per the question, am I supposed to calculate E naught cell or E cell? I am supposed to calculate E cell. So I'll use the Nernst equation. E cell is equal to E naught cell minus 0.0591 divided by N and log of QC. QC is how much? That's 1. Log of 1 is 0. So this term is 0. The final answer is 1.1 volt. This is something which you were supposed to calculate. Yes? So you can expect these sort of questions in your examination, and these are asked frequently. These are asked frequently. Okay? These are asked frequently. Guys, is it clear? I know I'm going very fast. I know that. But it's a complete revision session of your 12th chemistry. Right? So I think it works. Tell me once in the chats. All clear? All clear, everyone? By the way, have you studied my electrochemistry chapter in detail, which I have taken in, I think, 12 hours? If you have studied that, I mean, this would be pretty much easy for you. What I'm doing right now. All right. There is one more topic, guys, which you need to remember. And from that particular topic, what do I have to tell you? I would just want you to remember this particular table. From this particular table, direct questions will be asked. When we do the electrolysis of aqueous NaCl, right? What is produced at anode? What is produced at cathode? This is directly asked. For example, when you do the electrolysis of fused NaOH using platinum or graphite as the electrode, what is liberated at anode? What is liberated at cathode? These sort of questions are frequently asked. You need to remember this particular table, guys. What happens, what is produced at cathode and what is produced at anode. So once you get the notes of this particular session, please do have a look on this particular table and remember it directly. Remember it directly. Okay? Remember it directly. Now, my dear students, what happens during electrolysis? What happens during electrolysis? What happens during electrolysis? For example, here you have got a container. And over here you have taken some electrolyte. Electrolyte is AB. Let's say one is your anode, one is your cathode. One is your anode, one is your cathode. Let's say on one electrode, some substance A is getting deposited. On this electrode, for example, some gas B is produced. Let's say on one electrode, some A is getting deposited. At some electrode, some gas B is getting produced. Now, Faraday's first law says that, I'll just give the result. If they ask you to calculate mass of substance deposited or liberated at the electrode, mass of substance deposited or liberated at the electrode, there is a formula for that. What is that? That is equivalent mass of the substance deposited or liberated multiplied by I multiplied by T divided by 96500. This is the formula by means of which you can calculate the mass of the substance deposited or liberated at the electrode. Equivalent mass of the substance multiplied by current that goes in the solution. T is the time, right? And divided by 96500. Sometimes they'll ask you to calculate number of moles of the substance deposited or liberated. The formula will be current multiplied by time divided by n factor of the substance that gets deposited or liberated multiplied by 96500. Multiplied by 96500. For example, where do we use these formulas? Before that, how do you get the n factors? For example, you have got the reaction like this. 2 times A plus 3 times B gives 4 times C plus 6 electrons. Let's say this is the reaction. I want to calculate n factor of A. I want to calculate n factor of B. I want to calculate n factor of C. How do you do it? How many electrons do you see? 6. 6 divided by 2 will be 3. 6 divided by 2 will be 3. 6 divided by 4 will be its n factor. So when you need to calculate the n factors, what you have to do? When you need to calculate the n factors, you just have to divide the electrons with the respective stoichiometric coefficients. That's all. Okay, that's all. For example, let me solve one question. With that, you'll understand where do we use this. And a solution of aqueous copper sulfate. A solution of aqueous copper sulfate is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited? What is the mass of copper deposited at cathode? When you do the electrolysis of aqueous copper sulfate, this is the reaction that takes place at cathode. And this is, okay, we have to talk only about the cathode, right? At cathode, as you can see, copper is getting deposited. I need to calculate the mass of copper deposited, which will be simply equal to equivalent mass of copper multiplied by I multiplied by T divided by what? Divided by 96500. Equivalent mass of copper will be molar mass of copper divided by n factor of copper. What is the n factor of copper? 2 divided by 1, that's 2, multiplied by 96500. Tell me, how much current goes into the solution? That is 1.5 amperes, I think, right? And for how much time? Time is 10 minutes, so convert in seconds, multiplied by 60. This will give you the mass of copper that gets deposited at cathode by just using the formula. By just using the formula. Okay, by just using the formula. I believe these sort of questions you can easily do. There is a variety of the question that can be asked here from the pH, right? From POH. Now, what Faraday's second law says? What Faraday's second law says? Understand what Faraday's second law says. It's again a simple thing. For example, this is the container. In this container, you are doing electrolysis of some solution. You are doing electrolysis of some solution, due to which some substance A is deposited here and B is produced here. Faraday's second law says simply that gram equivalence of substance A deposited will be equal to gram equivalence of B produced. Matlab, whatever equivalents are deposited or produced here, same equivalents are deposited or liberated here. Whatever equivalents of A get deposited or liberated here, same equivalents get deposited or liberated here at this electrode. So gram equivalence, how do we calculate? I'll write mass of A divided by equivalent mass of A. Similarly, gram equivalence of B will be mass of B divided by equivalent mass of B. So with the help of this particular one, a question can be asked. Right? For example, let me show it to you. Let's say the question is, we are doing the electrolysis of aqueous copper sulfate, right? And when you do the electrolysis of aqueous copper sulfate, at cathode copper gets deposited, at anode O2 gas is produced. So I can simply say one thing, gram equivalence of copper deposited at cathode has to be equal to gram equivalence of O2 produced at anode. Now gram equivalence of copper deposited will be mass of copper deposited divided by equivalent mass of copper. Similarly, mass of O2 produced divided by equivalent mass of O2. What is the mass of copper deposited as per the question? Mass of copper deposited is 63.5 grams. Divided by equivalent mass of copper will be molar mass of copper divided by n factor of copper. N factor of copper is 2. Mass of O2 produced, we have to calculate equivalent mass of O2. Molar mass of O2 divided by n factor of O2. N factor of O2 will be 2 divided by 1 by 2. That's 4. So from here, you can calculate mass of O2 produced. And if you calculate mass, you can convert the mass into moles. If you get the moles of O2 produced, multiply that with 22.4 liters, get the volume at STP. Right? Perfect. Perfect, guys. Now there are a few more things which you need to know. Those are the formulas. Formulas related to conductance. I hope you know. The first formula, that is resistance. How do you get the resistance of a conductivity cell? R is equal to rho L by A. This formula, I believe everyone will be knowing. Resistance units are going to be in ohm. Then comes one more thing. What is that? That is G, conductance. Conductance is inverse of resistance and its units are Simon. Conductance units is Simon. Then comes conductivity kappa. The formula is 1 divided by R into L by A. 1 by R into L by A. Its units are going to be Simon centimeter inverse. Right? Then comes your one more term, that's molar conductance. Molar conductance. Molar conductance formula is like this. Kappa into 1000 divided by molarity. Right? And lambda m units are Simon centimeter square per mole here. Similarly, there is a term called as equivalent conductance. How do we calculate it? Kappa multiplied by 1000 divided by normality, right? And the units of this is Simon centimeter square per equivalent. Now, from these direct formulas, some direct questions will be asked. From these direct formulas, questions will be asked. First of all, you should know what is L, what is A. L is simply distance between the electrodes. L is simply distance between the electrodes, right? A is the area of cross-section of the electrodes. Basically, that area of cross-section which is in the solution. See, guys, understand. See what kind of questions can be framed here. For example, this is the question. Look at the question, read the question. You'll easily solve it. Just the formula-based ones. The specific conductance means conductivity, is given to me as 0.009 Simon centimeter inverse. Okay. Cell electrodes, area of cross-section, 1.5 centimeter square. Distance between the electrodes, 0.5 centimeters, right? How much current should flow if potential difference between the electrodes is 5 volt? How much current? Current I is equal to V divided by R. V is given to me as 5. So what do I need? I need R. How do I calculate R? I know kappa is equal to 1 divided by R into L by A. Now see, kappa is given, L is given, A is given. You can calculate R. When you calculate R, put it here and get the value of I. Is it difficult or something? No, right? There are 2 to 3 things which you have to remember here. What is that? My dear students, when you do the dilution, remember with dilution, molar conductance and equivalent conductance of a strong electrolyte as well as weak electrolyte. When you do the dilution, molar conductance, equivalent conductance of a strong electrolyte as well as a weak electrolyte, that increases, right? But when you do the dilution, conductivity kappa value, that decreases. These things can be directly asked in your examination. With dilution, what happens to lambda m? What happens to lambda EQ? What happens to kappa? So with dilution, lambda m, lambda EQ for strong electrolyte as well as weak electrolyte, that increases, right? But with dilution, conductivity kappa value decreases. And the reason for that is number of ions per unit volume decreases. Number of ions per unit volume. That decreases. That's the reason for that. This can be directly statement-based question asked. So I'm telling you, with dilution, lambda m, lambda EQ increases. With dilution, lambda m, lambda EQ increases. So if I keep on diluting, lambda m will automatically attain its maximum value. That will be called as lambda naught m. Similarly, lambda EQ will attain its maximum value. That's called as lambda naught EQ. And this is called as molar conductance at infinite dilution. And this is called as equivalent conductance at infinite dilution. This is called as equivalent conductance and infinite dilution. So we know with dilution, molar conductance, equivalent conductance for weak as well as strong electrolyte both increases. And molar conductance, equivalent conductance, they attain their maximum values at infinite dilution. Which we represent with lambda naught m and lambda naught EQ. Okay, lambda naught m and lambda naught EQ. Now, there is one last topic, my dear students, which is important, from which questions are asked. What is that? That is your Kohl-Ross law. In short, see what Kohl-Ross law says. For example, you have got an electrolyte like this, AXBY. This is an electrolyte. Tell me, how will it undergo dissociation? X times A, Y positive, plus X times B, minus Y. Right? Now, how do I write? What do I write here? I can write lambda naught EQ, equivalent conductance of AXBY at infinite dilution, as per Kohl-Ross law, will be written as lambda naught EQ of A plus Y plus lambda naught EQ of B minus X. In short, I would say the equivalent conductance of an electrolyte at infinite dilution is the sum of its equivalent conductances of its ions at same infinite dilution. Okay? But remember, when you have to write molar conductance, of the electrolyte AXBY at infinite dilution, you have to take into consideration these stoichiometric coefficients as well. Sorry, this is, I think I made a mistake here. This is Y, B minus X. Okay, molar conductance of AXBY at infinite dilution, you have to consider stoichiometric coefficients here as well. So I'll start with X, then I'll write lambda naught M of A plus Y, plus I'll write Y, then I'll write lambda naught M of B minus X. Remember these two statements. When you have to write equivalent conductance, you don't have to consider stoichiometric coefficients. When you have to write molar conductance, you have to consider stoichiometric coefficients as well. Okay. Where is this used? This is how it's used, my dear students. The first application of this Kohlrausch law is to calculate the conductance of weak electrolytes. For example, I'm given with lambda naught m of HCl, I'm given with lambda naught m of NaCl, I'm given with lambda naught m of CH3CONa. I need to calculate lambda naught m of CH3COH. CH3COH. See, in short, how I'm going to do it. Understand. I need to calculate lambda naught m of CH3COH. So it is technically CH3CO negative, H positive. Now, where do you see CH3CO negative? I can see CH3CO negative here. Where do you see H positive? I can see H positive here. So add these two. Add these two. 426 plus 91 minus, subtract the other one, 126. Solve it. This will give you the answer. So basically, lambda naught m of CH3COH, right? So technically, I saw CH3CO negative, H positive. CH3CO negative comes here. H positive comes here. So I added these two and subtracted the other one. Subtract the other one means subtracted the one that neither has CH3CO negative nor H positive. So 1 plus 3 minus 2. Okay, so it will be 391. Simon centimeter square per mole. Okay. Similarly, guys, there is one more thing. There is one more thing. That is one more application part of it. What is that? Degree of dissociation of weak electrolyte. How do we calculate degree of dissociation of weak electrolyte? There is one formula for that. Degree of dissociation of weak electrolyte is molar conductance of weak electrolyte at a given concentration divided by molar conductance of the weak electrolyte at infinite dilution. For example, you are given with an electrolyte CH3COH. Let's say this is the electrolyte. Now in the question they have said, when the concentration of CH3COH is 0.1 molar, its molar conductance at that point of time is, for example, 4.9. And they are saying at infinite dilution, lambda naught m is equal to 490. Calculate degree of dissociation of CH3COH. Degree of dissociation of weak electrolyte is molar conductance at a given concentration divided by molar conductance at infinite dilution. So this will give you the value of alpha. This will give you the value of alpha. Okay? This will give you the value of alpha. How exactly? For example, you've got a question like this. Let's say you've got a question like this. Look at this question. Look at this question, guys. Molar conductance of 0.1 molar aqueous solution of this is 9.1. So lambda m, molar conductance at a given concentration is 9.54. And at infinite dilution is 238. We have to calculate degree of dissociation alpha. Alpha is this divided by this. So 9.54 divided by 238. This value will be 0.004. So alpha is 0.004. Now they have given in terms of percentage. So multiplied with 100. Sorry, this will come as 0.04. This will come as 0.04. Now they have given the answer in percentage. So multiplied with 100, it will be 4%. It will be 4%. Okay, it will be 4%. Similarly, you can solve the question like this. You can solve the question like this. Ca dipositive Cl negative molar conductance given. We have to calculate lambda naught m of CaCl2. First of all, tell me how CaCl2 undergoes dissociation. It undergoes dissociation as Ca dipositive plus 2 times Cl negative, right? So stoichiometric coefficient here is 1. So I'll write 1 multiplied by lambda naught m of Ca dipositive plus 2 multiplied by lambda naught m of Cl negative. So these values are given. Put here and get the answer. And one last application of it. What is that? That is, sometimes they'll ask you to calculate solubility. Sometimes they'll ask you to calculate solubility of a sparingly soluble salt. You just have to remember one result. Molar conductance at infinite dilution of a sparingly soluble salt is equal to kappa multiplied by 1000 divided by solubility. In the question, they'll give you kappa value, they'll give you this value, so you can calculate solubility from here. Okay. So all this is, guys, very important questions have been asked from this, questions will be asked from this. Okay. So take care of all these things properly. Can you solve this one? Can you solve this one? Let me call KK sir. Because KK sir will be starting the organic chemistry right after I end. Sir, 1 minute lagana na. Hello? Hello? Maklo almost. अब बस लास्ट क्वेश्चन करना हुआ Yorgis Ahmet Rızdemir. Guys, can you check this question out? Can you check this question out? Can you check this question out? Option C is that. So you have got Al2SO4 whole thrice. Tell me what happens. Al2SO4 whole thrice. How will it undergo dissociation? It will be 2 times Al tripositive plus 3 times SO4 dinegative. Right? So you can say lambda naught M of this Al2SO4 whole thrice is equal to 2 times lambda naught M of Al tripositive plus 3 times lambda naught M of SO4 dinegative. Right? Now, this is something which is given to me. Perfect. Lambda naught M of SO4 dinegative is also given to me. I just need to calculate this value, put the values and get the answer. That's it. Okay. Do you need the lunch break? See, we are done with your physical part. Now we'll start the organic chemistry. Huh? Now organic chemistry will be started by KK sir. But I think you should take a lunch break and start the session at 2. Batteries, I'll send you a sheet. I'll send you a sheet on my Telegram. Battery part, you will just do that. Do from there. You just have to read that. Organic chemistry starts at 2 p.m. Huh? Okay, so you have got the lunch break till 2 p.m. Tomorrow at 8 p.m. there is one short question session in which that is the chemistry paper predictor basically. That is tomorrow. Do join that session as well. And in upcoming 2 to 3 days, I'll come up with this also. The JEE Mains PYQs session of your 2025 and 2026. Achha, chalo, let me make it as 2:15. Let me make it at 2:15. Huh? Let me make it at 2:15. So your organic chemistry starts at 2:15. Huh? Okay. Perfect. Chalo, KK sir will be starting at 2:15 then. Hello. No. Mid में break, huh? There's a 2:15 start. Mission बंद करने की जरूरत है. Chalo guys, you carry on. There'll be one session on inorganic as well. I'll keep you updated about that. Okay. But do join the organic chemistry session at 2:15. I hope the revision of physical chemistry was perfect. It was a revision, guys. Okay. That's why I was going very, very, very fast. It was the revision of your 12th physical chemistry. Right? Now KK sir will be doing the revision of your complete class 12th organic chemistry. Okay. So he'll be starting exactly at 2:15. You can have your lunch break till then and be back on the channel as soon as possible. See you guys. Take care. Bye-bye.
Hello and good afternoon, everyone, guys. I believe you all are doing great and having a good time. But before we move ahead, first of all, thank you all for showing so much love and respect here. Now here, we will complete class 12th organic chemistry, from where maximum number of questions will be there in your finals. But before we move ahead, let me know quickly that if you can see me clearly and hear me clearly, let me know in the chats. Let me know in the chats. Am I audible and visible to each and every one there? Let me know in the chats quickly. Let me know. Am I audible and visible to each and every one there? Okay, I believe we are live now, but let me once again tell you that from organic chemistry, maximum number of questions will be there in your finals. So be with me till end of the session, and I would want you all guys to mark the attendance by smashing the like button. And also do share this stream with everyone around. So without wasting much more time, let's begin. In today's session, first of all, we will be completing optical isomerism. Now have a look. What is meant by an optical isomer? These are basically the stereoisomers which differ in their behavior towards plane polarized light. So stereoisomers which differ in their behavior towards plane polarized light are called optical isomers, and the phenomenon is known as optical isomerism. For example, if you have an unpolarized light that can oscillate or vibrate in all possible directions, but when your light oscillates or vibrates in only one plane, in one direction, we call that light as plane polarized light. So, when stereoisomers differ with respect to each other, with respect to this plane polarized light, such stereoisomers are known as optical isomers. What is meant by that? Have a look. For example, let's assume A and B. A and B, these are the two substances which are stereoisomers. If we pass plane polarized light through this stereoisomer and through this stereoisomer, suppose that this stereoisomer simply rotates this plane of plane polarized light towards right, then at that time this substance is known as dextrorotatory and is denoted by small d, or it's denoted by plus sign. So it rotates plane polarized light towards right and this rotates towards left. That means these two are the stereoisomers which differ in their behavior towards plane polarized light. One rotates it towards right, another rotates it towards left. So we can call such stereoisomers as optical isomers because they differ in their behavior towards plane polarized light. They differ here with respect to direction or what we call sign of rotation. This is dextrorotatory, means plus sign. This is levorotatory, means negative sign. Similarly, optical isomers can be those stereoisomers which differ in their behavior but not in direction or not in sign but in magnitude. Say for example, it rotates plane polarized light towards right. It also rotates plane polarized light towards right. That means both are dextrorotatory. But let us suppose it rotates with an angle of theta, and let us suppose that angle theta is plus x degree. Any angle, let us suppose plus 10 degree. But if it rotates more than that, that means they differ in magnitude of rotation. So stereoisomers which either differ in magnitude of rotation or direction of rotation, we call such stereoisomers as optical isomers, and the phenomenon is known as optical isomerism. Now, after that, if a molecule rotates plane polarized light in any direction, whether it rotates plane polarized light or plane of plane polarized light towards right or left, that means in any direction, such molecules, such substances are known as optically active substances or optically active molecules. But the substances or the molecules which cannot rotate plane polarized light, or when plane polarized light is passed through such molecules, net rotation will be zero. At that time, we call such molecules as optically inactive molecules. Now, the question is, why plane polarized light is rotated either towards right or towards left. I mean say, what is the cause of this optical activity? Remember, cause of optical activity is chirality. Now, let's have a question that means chirality. Now, the question is, what is meant by chirality? Listen carefully. A chiral substance or a molecule is that molecule which is basically non-superimposable with its mirror image. Like our hands. Our two hands are mirror images of each other, but they are non-superimposable mirror images. Have a look, have a look. These two are non-superimposable. They cannot, superimpose with respect to each other. These are non-superimposable mirror images of each other, like that of hand, because it is basically a Greek word from which Greek word care is there, from which basically chiral has been obtained. So any molecule, any substance which behaves like that of hand is known as chiral molecule, because molecule is non-superimposable with its mirror image, means molecule is showing property like that of hand. This property of a molecule, when it is non-superimposable with its mirror image, means it is chiral, and the phenomenon of non-superimposability is known as chirality. That means any molecule which is non-superimposable with its mirror image is simply what we call chiral, and if it is superimposable with its mirror image, at that time this is known as achiral. Now the question is, why or which molecules are chiral? That means which molecules are, how can we, identify the molecules whose mirror images are non-superimposable? For that, have a look. Have a look. First of all, we have to identify whether the molecule is chiral or not. Listen carefully. If that molecule is chiral or that molecule is achiral, that means molecule which is chiral is generally optically active, and achiral molecules are generally optically inactive. Now listen carefully. If a molecule does not have any chiral center, first of all, what is meant by chiral center? Let me tell you. Chiral center means that center which itself is sp3 hybridized and is attached to four different groups. If our molecule does not have any chiral center, such molecule is generally optically inactive. That means such molecules are generally achiral. But there are few exceptions. That means there are few molecules which are not having any chiral center, but still they are what we call chiral molecules, but they are what we call optically active molecules. So generally, if there is no chiral center, then we can call that molecule as a chiral molecule, that means optically inactive. But there are few examples where molecule does not have any chiral center, but still that molecule is optically active or chiral. Which are those molecules? Have a look. These are such molecules. Say cumulene. What is meant by cumulene? Cumulene means such compounds in which pi bonds are present at adjacent position. If we are having a cumulene, or if we are having spiro compounds, say those compounds in which there is one atom common between two rings, spiro compounds. Similarly, if we are having cycloalkylidenes, but which type of, cumulene, which type of spiro compound, which type of cycloalkylidene? Listen carefully. If we have what we call cumulene with even number of pi bond, spiro compound with even number of rings, and cycloalkylidene with even number of ring and pi bond. Here ring is 1, pi bond is 1, so 1 plus 1 is 2. So we know 2 means even, 4 means even, 6 means even. So here, these are the compounds in which either pi bond number is even, either number of ring is even, either number of ring plus pi bond is even. When cumulene having even number of pi bonds, spiro compound with even number of rings, and cycloalkylidenes with even number of ring and pi bond are there. And in addition to that, you have substituted biphenyls, where these substituents are present at these positions, ortho positions, and these are bulky groups. Then at that time, we have to check only end center. We have to check only end center. Have a look. This is one end, this is another end. Similarly, this is one end and this is another end. Similarly, this is one end because ring starts from here, and this is another end because double bond or pi bond ends at this position. Similarly, these are two ends. This is one end and this is another end. What we have to do is, what we have to look is, we have to see here that if these two end centers have different groups, have a look, these two are different. Similarly, this end center is having different groups. So this is different. Different from this side, different from this side. Similarly, different from this side, different from this side. Similarly, different from this side, different from this side. Similarly, if you have a look towards this is one of the groups attached to this center. Similarly, this is another group attached to this center. These two are different groups. Similarly, we can say these two are different groups here. So whenever you have cumulene with even number of pi bonds, pyro compounds with even number of rings, and cycloalkylidene with even number of pi plus, I mean to say ring, or you are having substituted biphenyls, then if each end center, this end center as well as this end center, each end center has different groups, remember, such molecules are optically active, such molecules are chiral, even though they do not have any chiral center. So this is point number one. After that, if you are having chiral center, if you are having a molecule in which there is one chiral center only, then they are generally chiral molecules. They are considered chiral molecules. They are considered optically active, but there is once again exception. For example, this species, have a look towards this nitrogen. This nitrogen is sp3 hybridized, and there are four different groups. One lone pair, another R, another R prime, another R double prime. R prime, R double prime, they are not equal. That means they are different. Lone pair is different. That means this is sp3 hybridized center attached to four different groups. That means this is chiral. This molecule is chiral because of presence of one chiral center. That means this is chiral. Similarly, this is chiral. But remember, they are optically, both these are optically inactive. Both are chiral, but they are optically inactive. Why they are optically inactive? Reason is amine inversion, or we can say inversion in case of carbanion like that of amine, known as umbrella inversion. So remember, if your molecule contains only one chiral center, it is generally chiral molecule, or it is generally optically active molecule, except amines, if they are having chiral center, but still they are not, I mean to say, optically active molecules because of amine inversion. Similarly, carbanion, if it is having one chiral center, still molecule is chiral, but it is not optically active because of umbrella inversion or inversion like that of amine. You have to remember these things. Point number third. If molecule is having chiral center greater than 1, if molecule is having chiral center greater than 1, then at that time we have to check whether molecule is chiral or achiral. For that we have to check elements of symmetry like plane of symmetry and center of symmetry. So remember, they may or may not be chiral. That depends on plane of symmetry and center of symmetry. If plane of symmetry is present or center of symmetry is present in a molecule, or both are present, then such molecules are achiral molecules, optically inactive molecules. But if both are absent, then such molecules are chiral molecules. That means optically active molecules. But after that, my dear lovely students, we will be having this one, chiral center. I have already told you that what is chiral center or what is asymmetric center, which contains at least one sp3 hybridized center and that sp3 hybridized center is attached to four different groups. Now, here are few examples. Let me explain. Now we know this is sp3 center and is attached to CH3 on one side, deuterium on another side, hydrogen on another side, and lone pair on another side. So we can call this as a chiral center or an asymmetric center. As this is nitrogen, so we can say this is chiral nitrogen or asymmetric nitrogen. Here, this carbon is sp3, this is sp3, and is attached to four different groups. So we can call this as a chiral center, and this is carbon, so we can call it as asymmetric carbon or chiral carbon. Similarly, this is the center which is attached to Cl on one side and this ring on another side, this part of ring on another side, and H on another side. That means four different groups, and is sp3 and This we will call this as a chiral center. Similarly, this is having sp3 center to which 4 different groups are attached. So this is another chiral center. So in this molecule, one chiral center is present. So this is, I mean to say, chiral molecule. But as this is amine, so amine inversion can take place over here. So this is chiral molecule but optically inactive. Now, this is having one chiral center. This is not amine, this is not carbanion. This is chiral molecule as well as optically active molecule. But this molecule contains more than one chiral center. We have to check whether POS, plane of symmetry, or center of symmetry is present or not. Then after that, we can say whether this molecule is chiral or a chiral molecule. Now, tell me, am I clear till now? Let me know in the chats. Let me know in the chats quickly. Am I clear till now? So that we can move ahead. Let me know in the chats quickly. Let me know in the chats quickly. Am I clear till now? Am I clear till now? Okay, that's great. That is great. That is great. Okay. Now, have a look. After this, there is a question: count total number of chiral centers present in the given molecule. You have to count chiral centers. Now, here, this is the chiral center. So, it's 1 in number. After that, this is the chiral center. This is the chiral center. So, in this molecule, there are 2 chiral centers. To this is having 0 chiral center. Now, why is it so? Have a look. This is not chiral center. Why this is not chiral center? Because here it is attached to Cl, but on this side it is CH2, C. That means this part of the ring, have a look, it's this part of the ring. Similarly, this part of the ring, both are same. Both are same. So we cannot say this is chiral. So this is not the chiral center. Similarly, this is not having any chiral center. So we can simply call this molecule is not having any chiral center. After that, 4. This is having a chiral center, this is a chiral center, this is a chiral center. Sorry. Now, these are having 3 chiral center, but what about this, guys? What about this? Is this a chiral center? Have a look. This is having lone pair on one side, H on another side, CH3 on another side, COCH3 on another side. It seems to be chiral center, but remember, this is not a chiral center because this is sp2 hybridized center as it takes part in resonance. It is sp2, but we must need sp3 center to which 4 different groups are attached or which is attached to 4 different groups. So there is no chiral center over here. So this is having 0 chiral center. After that, this is having chiral center. This is the chiral center. Similarly, this is the chiral center, this is the chiral center, this is the chiral center, but this is not the chiral center because it's having similar H and H. So that means we will be having 1, 2, 3, 4 chiral centers over here. Here, there are 3 chiral centers are here, 2 chiral centers are here. Here, it's 1 chiral center. In these 2, there is no chiral center at all. After that, my dear lovely students, if we want to check whether molecule containing more than 1 chiral center is chiral molecule or achiral molecule, for that we have to check for COS and POS. That means plane of symmetry and what we call center of symmetry. POS, plane of symmetry. Now, the question is, what is meant by plane of symmetry? It is basically an imaginary plane which divides the molecule or any object into 2 equal halves such that one half is exactly the mirror image of another half. Have a look. Have a look. Now, we can imagine a plane over here. We can imagine a plane over here. And this plane divides the molecule into 2 equal halves. So we can say this is what we call POS because it divides molecule into 2 equal halves such that one half is exactly mirror image of another half. So POS is present in this species. So POS is present. If any, either POS or I mean to say COS is present or both are present, we call such molecules as achiral molecule, that means optically inactive. So this is achiral or optically inactive species. Now here plane of symmetry is absent. Here plane of symmetry is absent. This is not having any plane of symmetry. Because what is plane of symmetry? Imaginary plane which divides molecule into 2 equal halves such that one half is exactly mirror image of another half. Have a look. This is having a plane of symmetry over here. This is having plane of symmetry over here. Imagine, just imagine. Just imagine this as a mirror or a plane. That's why plane of symmetry is also known as mirror plane, or it's also known as sigma plane. Now have a look. These two are equal halves, and this half seems to be, say mirror image of this half. So we can simply say plane of symmetry is present over here. Similarly, if you look towards this molecule, this cyclohexane ring is on the board, is present in one plane. After that, this Cl is above the plane here. Here it is H, which is above the plane, and then on this carbon, Cl is behind the plane, and here H is behind the plane. Now have a look. If we draw a plane, if we imagine a plane like this, it will pass here from chlorine, here from hydrogen, then carbon and carbon of cyclohexane, then chlorine, here hydrogen. So it will pass through atoms. Let us suppose it will pass through these atoms. So after that, the plane which is passed through atoms, after that, can I say it divides the molecule, this one and this one, into two equal halves, such that this half is exactly mirror image of this half. So we can simply say plane of symmetry is also present over here. After that, my dear lovely students, have a look. Here, what you have to remember is that there is neither, there is no plane of symmetry, because we cannot say there is an imaginary plane which divides molecule into two equal halves such that one half is exactly mirror image of another half. This is above the plane, that is below the plane. So if we put a mirror over here, it is not, they are not, two parts are not mirror images of each other. Yes, if this is above the plane, that is also above the plane, then plane of symmetry is present. If this is below the plane, that is below the plane, plane of symmetry is present at that time. Now, after this, my dear lovely students, you have other compounds, like you have cumulines, pyro compounds, but no need to remember those, because I have already shown over here that these are the species, these are the cumulines with even number of pi bond. If these are different, then plane of symmetry is, absent over here. And if plane of symmetry is absent, that means they are chiral. So in such molecules, plane of symmetry is absent. Other than them, plane of symmetry is always present in cumulines if they are not different, or whether they are having even number of pi bonds. And if they are different but they are having odd number of pi bonds, that plane of symmetry is always present. Similarly, plane of symmetry is always present in, spiro compounds containing odd number of rings. That is present in, cycloalkylidenes containing odd number of ring plus pi bonds. Or that means you have to remember these only, that their plane of symmetry here is absent. After plane of symmetry, we have another, that is center of symmetry or center of inversion. What is that? It's an imaginary center basically, or imaginary point, from which when lines drawn on one side and produced an equal distance from another side, that means you have to draw line from through point from one side and then on its opposite side. That means, remember, opposite side is very important. After that, when lines drawn on one side and then produced an equal distance on another side, they will meet identical points. That means they will meet identical groups at equal distance. That means 3 points are very important. One is, equal distance. That's very important. Another is on opposite side. Another third one is they should meet identical groups or identical atoms. Have a look. If this is the center, have a look. If this is the center, have a look. If I draw a line from this center on one side, and this side is basically above the plane, because BR is basically here. Now, I will draw line from same center on opposite side. Have a look. Opposite side, equal distance, identical groups or identical points. Similarly, if I draw like this, if I draw line like this below the plane, and from same center at equal distance opposite side, it is like this, then they will meet identical points. Similarly, like this, they will meet identical points. Have a look. This is above the plane, this is below the plane. Similarly, this hydrogen is above the plane, this one, and this hydrogen is below the plane. That means everywhere, when you draw line through center on opposite sides at equal distance, if it meets identical atoms or groups, then center of symmetry is present. So in this case, center of symmetry is present. So we will say center of symmetry is present. Now have a look. This is a ring made up of odd number of atoms. When ring is made up of, when cyclic compound is made up of odd number of, say atoms, remember COS is always absent in that. So note down this point. COS is always absent in a compound if it is a cyclic compound and contains odd number of rings. Odd number of, atoms. After that, have a look. If we draw a line over here through these, say center, on opposite sides at equal distance, identical groups are there. Similarly, on opposite side at equal distance, identical groups are there. Similarly, this is the carbon, this is the carbon. On opposite side, once again, it's a carbon. Similar atoms are there. On opposite side at equal distance, similar atoms are there. So we can simply say center of symmetry is also present over here. What about this? What about this? What about this? Have a look. Here it's oxygen. On opposite side, it is oxygen. Here, on above the plane, it is chlorine. And below the plane, that means opposite side. On opposite side, it is chlorine. At equal distance, identical points are there. So here, once again, it is carbon. Once again, it's CH2 group. After that, you can simply say that COS is present over here. What about this? What about this? Have a look. Have a look. This is the center, imaginary center. Draw line. You have to imagine basically. Now, above the plane, it is bromine. Now, below the plane, it's also bromine. That means at equal distance and opposite sides, at equal distance and opposite side, identical groups are there. Similarly, equal distance, opposite side, identical groups are there. Equal distance, opposite side, identical groups are there. Have a look. So we can simply say COS is once again present over here. So, suppose we have these types of molecules. Have a look. Have a look. This is cumulene with odd number. This is cumulene with odd number. Have a look. Have a look. If I draw a line over here from this side, it's H. Its opposite side is also having H. This is, Cl. On its opposite side, it's once again Cl. On this side, it's carbon. On its opposite side, it's carbon. So we can simply say here in this molecule, COS is present. But if you are having cumulene with even number of pi bonds, remember, then these atoms, this and this, are present in one plane at this end center. And at this end center, you must remember that these groups are present in different plane. That means these are basically present in perpendicular plane with respect to each other. When they are perpendicular with respect to each other, they can never be, opposite with respect to each other. You cannot say that this is the center. Now, on opposite side, there are hydrogen and hydrogen. On opposite side, there is chlorine and chlorine. Why? Because they are not opposite with respect to each other. Opposite means 180. They are actually at 90 degree. So remember for such molecules, remember forever, if you have a molecule in which groups are perpendicular to each other, remember COS is always absent. So, in molecule in which groups are perpendicular with respect to each other, COS is always absent, number one. Number second, have a look. In rings containing odd number of atoms, COS is always absent. Third one is, if you are having fissure structure, vertical and horizontal structures, COS is always absent. These are the 3 points where COS is always absent. Sir, why COS is absent over here? It is OH, and why COS is absent over here? If we change an example like this, suppose we will change this. Suppose we will change this. Have a look, my dear lovely students. This is OH, this is OH. This is H, this is H. Sir, why COS is absent? They are basically two opposite, sides, and identical points are there, identical groups are there. Why you are saying that COS is absent over here? They seems to be opposite with respect to each other, but they are not opposite, my dear lovely students. Actually, we know COH I mean, say whenever you are having Fisher structure, it is basically like this. These groups are actually, have a look. Groups present on vertical line are actually behind the plane, and groups present on horizontal line are considered above the plane. So it is like this actually. It's like this actually. It is like this, my dear lovely students. So we cannot say these two are opposite with respect to each other. This is above the plane. This is also above the plane. They are not opposite with respect to each other. That's why never use COS in Fisher structures as well. So there are three structures. Never use COS. COS is always absent. Number one, in Fisher. Number second, in cumulines with even number of pi bond, or in spiro compounds with even number of pi bond, or in cycloalkylidenes with even number of ring plus pi bond, and in substituted biphenyls. There is always COS absent, and in addition to that, a cyclic compound in which odd number of atoms are there, COS is always absent. Now have a look. You can use, you can check over here. Have a look. Here it is C double bond O on one side, and its opposite side it is C double bond O. After that, if we draw a line, it is NH on one side, and to its opposite side identical atom or group. But the problem is, if you go here, it is Cl, and its opposite on its opposite side. Have a look on its opposite side. On its opposite side, it is Cl once again. That means they are opposite sides are having identical groups. Now, opposite sides are having identical groups. So we can simply say COS is present in this molecule. But if I change this Cl and H, if I draw Cl over here, H over here, then opposite sides are having Cl and H. If we change this, at that time COS will be absent. I hope this is clear to each and every one there. Let me know quickly, am I clear till now? Let me know quickly, am I clear till now? Let me know quickly, am I clear till now? Let me know, my dear students, let me know quickly, am I clear? Let me know quickly, am I clear till now? Come on. Okay, that is great, that is great. That is great, that is great. Listen carefully, because many questions will be from organic chemistry. Sir, break. We came from break now. So Wasim sir has already given you break of half an hour. Okay, now have a look, have a look. This is having one chiral center. This is having one chiral center. So we have to identify chiral and achiral molecule. So this is chiral. So whenever I have already given you this, and remember this forever, whenever you are having one chiral center except these two, that is always chiral. That is always chiral. So this is chiral. So this is chiral. So this is chiral. After that, this is having one chiral center. Hence, once again, overall molecule is chiral. Now after that, this is third one. Have a look, have a look, have a look. If this is the center, if this is the center, have a look. As this is having more than one chiral center, whenever you are having more than one chiral center, you have to check POS or COS. Now, POS is not present now. Have a look. If we talk about this one, this is above the plane. Above the plane. Above the plane is OH. It's below the plane is also OH. That means on opposite side identical groups are there. Above the plane is H, below the plane is H. That means opposite side identical groups are present. Similarly, here CH3 and CH3 are opposite with respect to each other. That clearly indicates that COS in this case is present. As COS is present, hence molecule becomes achiral. Have a look. This is also having more than one chiral center. Whenever you are having more than one chiral center, first check POS and then COS. Here we can simply say this is a molecule where plane of symmetry is present. So plane of symmetry is present, hence molecule is achiral. Have a look. This is chiral center, this is chiral center. It does not have any plane of symmetry, and center of symmetry is always absent here. So we can say POS is absent, COS is absent. There is another basically one more element of symmetry that is known as alternating axis of symmetry, but no need to study that, because whenever POS and COS is absent, for your class, you can say that alternating axes of symmetry is also absent. That's why I'm not talking about that. Now, so POS-COS is absent, hence this molecule is chiral molecule. Now, after that, have a look. This is basically a spiro compound with even number of rings. What we have to check over here is end center. This end center contains two different groups. This end center contains two different groups. Hence, this is a chiral species. No need to check POS-COS in such cases. Now, have a look. Once again, this is cumulene with even number of pi bonds. What we have to check is, I mean to say, end center. These two are different, but here they are same. As they are same, so we can simply say they are not chiral. Hence, this is a chiral. Or we can say plane of symmetry is present in this. Now, have a look. This is cumulene with odd number. In odd number, you have to check POS and COS. And remember, in odd number of, I mean say cumulene with odd number of pi bond, POS is always present. So you can simply say POS is always present. Hence, molecule is achiral. After that, have a look towards this. Now, POS is absent. COS is also absent because on opposite side, one is hydrogen, another is chlorine. So we can say POS is absent. COS is absent. Hence, molecule is simply what we call chiral. So this molecule is chiral. After that, my dear lovely students, we will be having another, that is configuration, but around chiral center. What is meant by configuration? Configuration means a relative arrangement of atoms or groups around chiral center. But there are two types of configurations. One is absolute or actual configuration. Another is relative. But absolute configuration can be understood, and that is simply capital R and capital S configuration. Let me tell you, these are basically the Latin words. It's Latin word rectus, meaning right side or clockwise direction or clockwise direction. Similarly, so Latin rectus, similarly Latin word sinister means left side, or we can simply say anti-clockwise direction. Direction of what? Direction of basically three groups. Around chiral center there are four groups. So for example, this is the chiral center. This is the chiral center. We will be having four groups. First priority group, second priority group, say for example fourth priority group and third priority group. You have to check position of 1, 2 and 3. If 1, 2 and 3 are clockwise, are present in clockwise direction, if they are present in clockwise direction, and if they are present in anti-clockwise direction. If they are present in clockwise direction, we call that as R, because clockwise means rectus. Rectus short form is R. If 1, 2, 3 are present in anti-clockwise direction, we call that as S. But remember, least priority, that means fourth, but this is applicable only if fourth priority group is present on vertical line, in case of Fisher projection, or it should be present on dash line or dash bond in case of dash wedge structure. So in case of Fisher projection, fourth priority should be present on vertical, either at this point or this or at that side on vertical. If it is present on vertical line, or we can simply say like this, if it is like this, this is 1, then this is 2, this is 3 and this is 4. If fourth priority is present on dash bond or it is present on vertical line, at that time this is applicable. 1, 2, 3 means R, and if 1, 2, 3 is showing anti-clockwise direction like this, have a look. This is 1, 2 and 3. So without this 4, what is the direction of 1, 2 and 3? This is 1, here it is 2, here it is 3. So what is the direction over here? Clockwise. So clockwise means R. What is the direction over here? 1, 2 and 3, anti-clockwise, that means 1, 2, 3 anti-clockwise means S. So clockwise means R, anti-clockwise means S. But direction of what? Direction of 1, 2 and 3. Now what is 1, what is 2, what is 3? This is priority of groups around chiral center. And this priority is simply, you can find out the priority with the help of CIP rules. Now, what are those rules? I will tell you. But first of all, remember this. Now, the question is, sir, if in case of Fisher projection, this fourth is not present on vertical line, it's present on horizontal line. So, let me tell you, if fourth priority group is present on horizontal line, in case of Fisher projection, then use golden rule. What is meant by golden rule? If it seems to be clockwise, that means if it seems to be R, you have to reverse that. That means golden rule means then if 1, 2 and 3, have a look, if 1, 2 and 3 are present in clockwise direction, that was R 1, 2, 3, but here you have to reverse it. That means it becomes now S by using golden rule. And if it is present like this, anti-clockwise direction, then you have to change basically. Anti-clockwise basically means sinister, means S. Now you have to reverse that configuration. That means it becomes R. But use golden rule only and only if fourth priority group is present on horizontal line in case of Fisher projection. Never use golden rule in, dash wedge structure. You can use trickwise, but don't use, this in dash wedge structure. Why? Because sometimes it will give you the correct answer, sometimes it will give you the wrong answer. So what we have to do is, have a look. What you have to do is, it's very simple. If your, say for example, fourth priority is not present on dash, suppose it is like this. Now its position is basically dash position. So what you will do is, you will draw this once again like this. You will draw this once again like this, as this is the chiral center. At chiral center, 4 should be on this. So you will simply exchange or interchange position with 2 because 4 should be on dash, but there is 2. So you will interchange the position between 2 and 4. After that, 1 and 3 will be there. Now, what will be the direction now from 1, 2 and 3? This is 1, this is 2, this is 3. It's now clockwise. So it is R, but this R is, a structure has been appeared only when you interchange 2 and 4. That means if this is R question is having S configuration. So this was our question. What is the configuration of this? Just interchange 2 and 4, not 2 and 4. That group which is present on dash and fourth priority group, interchange those. You will get the answer. Whatever is the answer, reverse of that will be actual answer of this question. Similarly, suppose you are having like this. Suppose you are having like this. Now, fourth priority is present over here. Let us suppose fourth priority is present like this. Now, you have to, make one interchange because fourth priority should be present on dash. Now, at dash it is 3. Now, interchange position of 3 and 4. You will get this one. You will get this one. You will get this. It will become 4 here, 3 here because you have interchanged these. Now, after that, it's 1, 2. 1, 2 and 3. They are present in anti-clockwise direction. That means this is S. But question was this. What is the configuration of this? So, reverse that. That means it is R. So, it is very, very, very simple. But never use, golden rule over here. Now, after that, the question is how to prioritize different groups. We can prioritize different groups on the basis of rules, and those rules are known as CIP rules. So, first rule is simply, rule number 1 is very, very simple. That is, you have to assign priority on the basis of atomic number. That means atomic number is directly proportional to priority, or priority is directly proportional to atomic number. Now, if you are having a structure like this, this is I, this is Br, this is, say for example, Cl, this is F. This is having atomic number 1 because it's highest atomic number. Now, after that, this is 2, this is 3, and this is 4. Now, what you have to do is, this is Fisher structure. Now, simply what you will do is, you will check where is 1, where is 2, and where is 3. They are clockwise. So, It should be R, but as fourth priority is present on horizontal, have a look. When fourth priority is present on horizontal, then at that time 1, 2, 3, if it is clockwise, it is S. If it is anti-clockwise, it's R. Have a look. Have a look. Now it is clockwise, it seems to be R, but it is not R now, it is actually S. Because of why it has changed from R to S? Answer is golden rule. Answer is golden rule. But over here, if it is I, this is BR, this is F, this is Cl, this is very, very simple. This is 1, this is 2, this is 3, this is 4. Now check. Now check. Where is 1? Where is 2? Where is 3? This is 1, this is 2, this is 3. So it is clockwise direction. Clockwise direction means R, and it remain as it is because there is no golden rule which we have to apply over here, as fourth priority is present on what we call Fisher, fourth priority is present on vertical line. Now, after that, rule number 2. Rule 2 is simple. Say for example, you have a group like this. Have a look. Four groups are there. This group is different from this. This is different from this. This is different from this. That means, first of all, it must be a chiral center. So this is the chiral center. After that, this is I, which is attached to this. This is carbon attached to this. Carbon attached to this. Hydrogen attached to this. We know iodine is having greater atomic number as compared to carbon, and carbon is having more atomic number as compared to hydrogen. So hydrogen is the least priority group. After that, similar atoms of different groups are attached. When similar atoms of different groups are attached, you have to check for priority. Now how? When similar atoms of different groups are attached to chiral center, then atom next to these atoms is considered. Now, carbon and carbon, they are similar. Have a look. This is the carbon and this is the carbon. They are similar. But after that, what is the next atom or next group? It is hydrogen, hydrogen, and hydrogen. Now here, it is carbon, hydrogen, and hydrogen. Sir, why you have written this carbon? Why not hydrogen, hydrogen, and carbon? You have to write down those three atoms in decreasing atomic number. That means we know carbon is having higher atomic number. After that, it is hydrogen. Now have a look. Now compare one by one. This is hydrogen, this is carbon. Have a look, have a look. This is hydrogen, this is carbon. Which is having more atomic number? Obviously this. That means this is having atomic number, say priority number 1. Now among these two, one will be 2, another will be 3. 2 means higher priority, 3 means lower priority. So give 2 to this, 3 to this. Now have a look. Where is 1, where is 2, where is 3? This is 1, now this is 2, and this is 3. So what is this? This is S, anti-clockwise. Now the question is, it remain as S or should we change this? Now, we will change only this if fourth priority is present on horizontal line. Fourth priority is present on vertical line. That means its configuration is S. We have not to change this. That means there is no need of golden rule at all. After that, if same compound is like this, CH2, CH3. Now, it is like this. I is here, H is here. Now, this is 1, this is 2, this is 3, this is 4. Now, my dear lovely students, have a look. Now, this is 1, here it is 2, here it is 3. So, it is anti-clockwise. Anti-clockwise should be S, but we will change this to R because of golden rule. Because of golden rule. Why golden rule has been applied over here? Because least priority is present on fourth position. After that, we will be having rule number 3. Rule 3 is if isotopes are attached. If isotopes are attached, say for example, isotopes are attached like this, different isotopes, then it is I and this is Br. First of all, with the help of atomic number, we can distinguish this is 1, this is 2, but these are having similar atomic numbers, so we cannot distinguish, we cannot prioritize them on the basis of atomic number, so we will use mass number. So this is then when isotopes are directly attached to chiral center, then priority is directly proportional to mass number, so it is 3, this is 4. Now, have a look. This is 1 here, 2 is here, 3 is here. So 1, 2, 3, that means clockwise should be R. Now the question is it R or will we change this configuration to S? Answer is R, remain as it is because fourth priority is present on vertical line. After that, if same question is like this, this is Br, this is I, this is D, and this is H now. This is 1, 2, 3, and 4. Now, what will happen? What will happen over here? This is 1, this is 2, this is 3, this is S. But it will not remain as it is. It will be changed to R according to golden rule. Why golden rule? Because fourth is present on horizontal line. After that, my dear lovely students, after that, we will be having rule 4. We will be having rule 4. Rule 4 is, if you have an atom like this, which is having, I mean to say, double bond, or you have an atom which contains a triple bond. If basically the group attached to chiral center already contains double or a triple bond, then what we will do? We will simply duplicate such, I mean say, atoms which forms double bond. Now, how? Have a look. Have a look. Now, I will first write down, instead of triple bond, I will write down single bond, and instead of double bond, I will write down single bond. I will write down others as they were. Now, only change is that convert this double bond to single bond, convert triple bond to single bond. Now, after that, mark this and this. Why? Because they were forming double bond. Now, mark these two as well because they were forming triple bond. Now, have a look. This carbon in this forms 2 bonds with oxygen, but in this only 1 bond with oxygen. So, you can form another single bond over here with oxygen. This oxygen is not the actual oxygen. This is the oxygen which basically we have written over here. This is known as phantom atom. Now, similarly, this oxygen give carbon to this, and this is phantom atom. Now, valency, satisfy the valency. So, in this way, carbon is duplicated, oxygen is duplicated. Both these are duplicated. Now, here, carbon forms 3 bonds with nitrogen. Here, it's only 1. So, you can form 2 more single bonds with this, 2 more single bonds with this. But carbon should form 3 bonds with nitrogen. So, one is this, another is this, another is this. These two are phantom atoms. Nitrogen forms 3 bonds with carbon. So, one is this, another is this, another is this. Now, satisfy the valency over here. You know this. Satisfy the valency. Now, after this, have a look. This is carbon, this is carbon. But both are similar atoms. To this carbon, it's oxygen, oxygen and hydrogen attached to this. So, can I write down over here? It is oxygen, oxygen and hydrogen, which are attached basically over here. Here, it is nitrogen, nitrogen and nitrogen. Here, nitrogen, nitrogen and nitrogen. So, you can directly use trick like this. Whenever you form a double bond, whenever an atom forms a double bond to, I mean say, oxygen, write down that oxygen twice and single bonded atom. It forms triple bond with nitrogen. So, write down nitrogen thrice. So, this is triplicated, this is duplicate. So, after that, can I write? This is chiral center attached to I, attached to H, attached to C, attached to C. Among these 4, this is having highest atomic number, this is the least atomic number. Carbon and carbon are having same atomic number. After that, we will go to next atom. Next atom is oxygen and nitrogen. Oxygen is having higher atomic number as compared to nitrogen. So, this is 2, this is 3. So, now, have a look. This is 1 over here, 3 over here, 2 over here, 1, 2, 3, 1, 2, 3 is clockwise. Clockwise means R. Now, the question is, will it remain as R or it will change to S? It will change to S because of golden rule, as least priority is present on what we call horizontal line. Now, so this is what we call R and S in case of Fischer. Now, similarly, you can give priority if chiral center is present in dash-wise structure, and after that, you can do what we call R and S configuration to each and every structure. Now, after that, we will be having DL configuration. What is meant by DL configuration? Have a look. We will be having a glyceraldehyde like this. This is the glyceraldehyde. This is the glyceraldehyde. This is the glyceraldehyde. Remember, this is an example of a carbohydrate which is polyhydroxyaldehyde containing at least 1 chiral center. Now, over here, this is the glyceraldehyde. This is the glyceraldehyde, my dear lovely students. So, whenever you have Fischer structure like this, that CHO is on top, CH2OH is on bottom, at that time, number your carbohydrate like this. Polyhydroxyaldehyde like this. After that, this is the second last. Total carbons are 3. This is second last carbon. And when second last chiral carbon contains OH group on right, we call that as D. And if second last carbon or chiral carbon contains OH on left, we call that as L. These are basically the standard references in case of polyhydroxyaldehydes. So, for example, if you are having a polyhydroxyaldehyde like this in your exam, and you have to assign configuration. Now what will you do? You will first of all check whether CHON is on top. Yes. CH2OH is on bottom. Yes. After that, number this carbohydrate. After that, these are having 4 carbons. So second last carbon will be this one. Now check at this carbon. Where is OH? OH is on right. Whether that resembles with D-glyceraldehyde or L-glyceraldehyde at last or second last carbon. It resembles with D. Hence this is D. If at second last carbon it's having OH on left, then we can call this as L. So this is polyhydroxy in case of polyhydroxyaldehyde. But sometimes you are having polyhydroxy ketone. You are having polyhydroxy ketone like this, in which CH2OH is on top, CH2OH is on bottom, but C double bond O group is at second position from top. Whenever you are having a structure like this, that you are having CH2OH on top, CH2OH on bottom, and C double bond O at second position from top, then remember, my dear lovely students, remember forever, at second last carbon, if OH is on right, this is D, and if OH is on left, it is L. Now, if your examiner gave a question like this, suppose, and you have to assign now configuration. You have to assign configuration. Now, what will you do? CH2OH is on top, CH2OH is on bottom, and C double bond O is at second position from the top. Now, total number of carbons are 5. You have to check at carbon number 4. That means second last carbon. OH is on left. When OH is on left at second last carbon, we simply call that as L. So this is L because it resembles with this configuration, this L at chiral center, at second last, center. After that, this is if you are having polyhydroxy ketone. Sometimes you are having, amino acids. For amino acids, remember this forever. For amino acids, you have to check alpha. You have to check alpha position. What is meant by alpha? Alpha means that carbon which is directly attached to COH. You have to check that. And if COH is on top, and at alpha position, H and NH2 are present at left and right, and after that other remaining structure of amino acid is on bottom, then what you have to do is, if your NH2 at alpha is present on right hand side of fissure, then it is D, and if it is present on left, then it is L. So this is what we call D amino acid, and this is what we call L amino acid. After that, we will be having another, that is trio and erythro terms. What are trio and erythro terms? Suppose you are having a structure, fissure structure like this, in which you are having 2 different chiral centers. Suppose this is having OH and this is having H, this is OH, this is H. Have a look. This chiral center is having different groups attached to it, and this is having different groups attached to it. So if your structure, a molecule, is present in fissure structure and there are at least 2 chiral centers, and those 2 chiral centers are different chiral centers, then identical atom, whether it is HH, whether it is Cl, whether it is OH, whether it is CH3. So if identical atoms are on the same side, we call this as erythro. We call this as erythro form. And if you are having, suppose like this, OH and H, then this is H and this is OH, then you can check position of identical atoms, whether HH or OH, they are on opposite side. So we call this as trio form. I hope this is clear to you. After that, we have another very important, topic, and that is enantiomerism. That means, what are enantiomers? What are enantiomers basically? These are stereoisomers. They are stereoisomers, but those stereoisomers which are non-superimposable with their mirror images. But we know the molecule, if it is non-superimposable with its mirror image, that is chiral. So we can simply say that stereoisomers which are non-superimposable with their mirror images are called enantiomers, as they are non-superimposable with their mirror image, hence they are chiral molecules. And remember, they are having similar physical properties like melting point, solubility, boiling point, etc. So they cannot be separated by fractional crystallization or fractional distillation. And remember, enantiomers have same magnitude of rotation, but they have different sign of rotation. They have same magnitude. That means if one enantiomer rotates plane polarized light towards the right, 50 degree towards right, another will rotate 50 degree, but opposite to that. That means they differ in sign, but magnitude of rotation will be same. Remember that. Remember that. And they may or may not have chiral centers. But if they have chiral centers, then which type of compounds can we call enantiomers? Remember, first of all, two compounds are enantiomers if they are stereoisomers. Second, both must be chiral molecules. Both must be chiral molecules. After that, if both are having more than one chiral center, that means both must have plane of symmetry and center of symmetry should be absent in both these cases then. After that, if one is having configuration at chiral center as R, another should be having chiral center configuration as S. That means configuration at each chiral center should be different. Say for example, if this is I, Br, F and Cl, we know its configuration is R. Its configuration is R. Its enantiomer will be like this. It should be like this. It should be non-superimposable mirror image of this. So how can we check non-superimposable mirror image in simpler way? Just check the configuration. One chiral center, both are chiral molecules, both are stereoisomers, both are having different configuration with respect to each other. Similarly, my dear lovely students, if you are having this one, CHO, this is OH, this is H, then this is what we call OH, this is H, and this is CH2OH. Have a look. And you are having like this. CHO, then it is OH, then it is H, then it is, OH, then it is H, then it is CH2OH. Have a look. If we talk about this chiral center, this is 1, this is 2, and this group becomes 3, that means it is S, but S changes to R as least priority is present on horizontal group. So its configuration is R. Here, its configuration is S. So this is having R configuration, this is having S configuration. Similarly, look towards this. This is having S configuration and this is having R configuration. Now, have a look. If I check between these two, both are chiral molecules, both are, stereoisomers. That means these 2 points are clear. Now, what is the configuration at this chiral center? It is R. Now, you have to check configuration of this with configuration of that chiral center to which similar groups are attached. Among these, which one is this carbon to which CHO, OH, H and this group is attached? It is this one. So I will check this and this. So this is R, this is S. So configuration at this chiral center has been changed. What about this? This is that chiral center to which CH2OH is attached. Which type of chiral center here is to which CH2OH is attached? It is this one. So here it is S, it is R. Hence these are also what we call enantiomers of each other. For example, if I say this is structure 1, this is structure 2, this is structure 3. Suppose structure 3 is this one. Suppose structure 3 is this one. This is structure 3. CH2OH, then this is CHO. After that, have a look. This is OH, this is H, this is OH, and this is H. Have a look. What is the configuration of this? Its configuration is S. And what about configuration of this? It is, R. Have a look. Its configuration is R. Have a look, my dear lovely students. If I compare this, I have to compare this with this, not this and this. Why? Because this is the chiral center which is attached to CHO. So I will compare this and this. Both are having similar configuration. And what about this? S and S. Both are having similar configuration. That means 1 and 3, they are having same molecular formula, they are stereoisomers, they are having similar configuration. Such type of compounds are known as homomers. They are homomers with respect to each other. Similarly, this is S, and this is R. Have a look. This is S and this is R. This is S, this is R. Similarly, this is R, this is S. We have to, check similar type of chiral centers. That chiral center to which CH2OH is attached is R. That chiral center to which CH2OH is attached is S. So here they are enantiomers. These two are chiral centers. They are also enantiomers of each other. So remember, 1 and 2 enantiomers, 2 and 3 enantiomers, but 1 and 3 are homomers with respect to each other. Now, After that, my dear lovely students, we are having another type, that is diastereomers. Diastereomers are also stereoisomers, but remember, they are not mirror images of each other. They are not mirror images of each other. Remember this. And they are having different physical and chemical properties. Hence, we can separate them easily by means of fractional distillation or fractional crystallization. And they may or may not be chiral, or they may or may not have any chiral center. Now, have a look. If I talk about this, you know, this is what we call a cis. This is a cis form, or a compound whose configuration is cis across carbon-carbon double bond. And this is what we call trans. This is what we call trans. Neither this is having any chiral center, nor this is having any chiral center. That means this is a chiral molecule, this is a chiral molecule. But both are stereoisomers, but which are not mirror images of each other. They are not mirror images of each other. We know both these are geometrical isomers, but these geometrical isomers are not mirror images of each other. So we can simply say they are also diastereomers of each other. They are also diastereomers of each other. That means diastereomers may contain or may not contain chiral center. Here there are no chiral center. But if two compounds have chiral center, then they must contain at least two chiral centers. Have a look. So first of all, two compounds are diastereomers. If they are stereoisomers, they may or may not have chiral center. But if they have chiral center, if chiral center is present in each of these compounds, then this compound must contain at least two chiral center. This compound must contain at least two chiral center, and configuration at one chiral center in both these cases must be same, and at least at one chiral center their configuration should be same, and at least at one chiral center their configuration should be different. What is meant by that? Have a look. If I write like this, CH3ClH, and then this is, say for example, BRH and CH3, and I will write down like this. It is CH3, then it is H, it is Cl, like this, and then it is Br, and it is H, it is CH3. Have a look, my dear lovely students. If I check, I mean to say the configuration of this, it is 1, 2, and 3, R changes to S, and what about this? It is S changes to R. After this, have a look. This is 1, 2, 3, that means S changes to R. So its configuration has been changed. But what about this? This is 1, 2, 3. That means it is S changes to R. So if it is having more, it's having, say more than one chiral center. Whenever chiral center is present, but it must have two chiral centers at least. It must have two chiral centers at least if we check whether they are diastereomers or not. After that, one chiral center must contain different configuration, and another chiral center must have similar configuration at least. Hence, these are simply what we call diastereomers of each other. If this is having different configuration, this is having different configuration, then we cannot call that as diastereomers. So, remember, two compounds can be diastereomers, not only one. Similarly, two compounds can be, say enantiomers, not only one. So, this is the relation between two compounds. So, enantiomerism is a relation between two compounds, diastereomerism is a relation between two compounds. But whenever you have to check whether the compound is meso or not, this is only one compound. You don't have to check relation between two compounds at that time. First of all, if you want to check whether the compound is meso or not, what you have to do is you have to check whether that compound must contain at least two chiral center. That means meso compound must contain at least two chiral center. But those chiral centers must have different configuration. Those chiral centers must have different configuration, but atoms or groups attached to one chiral center and atoms and groups attached to another chiral center must be similar, so that there will be internal compensation and overall molecule becomes optically inactive due to internal compensation or due to plane of symmetry or center of symmetry. That means such compound is basically a chiral. So have a look. Compounds which contain at least two chiral centers but are still achiral are called meso compounds. After that, such compounds are always superimposable with their mirror image. Obviously, because they are achiral molecules, and meso compounds and their mirror image are homomers. Remember, if there is a meso compound and you will draw its mirror image, that will also be a meso compound, and that will be identical homomer with respect to this. So mirror image of a meso compound is also a meso compound. Meso compound are achiral, hence optically inactive, and its optical inactivity is due to internal compensation or presence of plane of symmetry. So what is meant by this? Have a look. Have a look. We have to find out the relationship. Now, what is the configuration of this chiral center? What is the configuration of this chiral center? Have a look. This is 1, this is 2, this is 3. So 1, 2, 3. It seems to be R, but it has to change from R to S because least priority is present on what we call horizontal line. After that, this is 1, this is 2, and this is 3. Now, it is 1, 2, 3 means clockwise, and it remain as it is. Why? Because fourth priority is present on what we call vertical line. Here, fourth priority was present on horizontal line. They are stereoisomers, they are chiral centers, they are molecules, and both are having different configuration at chiral center. Hence, these are simply enantiomers. As only one chiral center is there, they can never be a meso compound, they can never be what we call diastereomers. They can either be enantiomers or homomers. If they are having same configuration, then homomers. If they are having different configuration, having same molecular formula, then enantiomers. So this is question number 1. Question number 2 is, this is 1, this is 2, this is 3. And this is 4. Fourth priority is present on dash. So you have to check only direction 1, 2, 3. 1, 2, 3 is anti-clockwise. So this is S. What we have to do over here, we have to, rearrange this. Now, this is 1, this is 2, this is 3, this is 4. So, fourth priority is not present on dash. So, you have to, first of all, interchange it. So, interchange this, and you can see simply like this. Here it will be H. Now I will not write down OH, H, I will write down priority only. So this is first priority, second priority. You have to interchange 4 and 3. So here it is 4, here it is 3. Now 1, 2, 3, 1, 2, 3. It is anti-clockwise. So this is anti-clockwise, but our question is R. So R and S, once again, they are enantiomers of each other. After that, my dear lovely students, have a look. This is having two chiral centers, and you know here it's a plane of symmetry. Plane of symmetry is present. Plane of symmetry is present. That means this is the molecule having two chiral centers, but still it becomes achiral due to presence of symmetry. So it becomes achiral. And a chiral molecule having at least two chiral centers is meso. So this is a meso compound. So this is a meso compound. Similarly, this is also a meso compound. Have a look. This is also a meso compound, a chiral compound, a meso compound. So this is a meso compound. Now, you have to tell what is the relation between these two. This is meso, this is meso. They are mirror images of each other. Hence, they are homomers. Hence, they are homomers because we know mirror image of what we call a meso compound is also a meso compound. That means it's a homomer. Now, listen carefully. Listen carefully. This chiral center, the groups present at this chiral center are similar as compared to groups present on this chiral center. That means any rotation caused by this chiral center towards plane polarized light will be exactly cancelled and compensated by this one within the same molecule. This is known as internal compensation. This is having configuration. This is having configuration what we call R. And this is having configuration what we call S. Have a look. As configuration is different, but groups present are same. That means when light is passed, plane polarized light is passed, suppose this chiral center rotates plane polarized light towards 50 degrees, suppose towards right, this will rotate 50 degrees towards left. That means rotation caused by one molecule is exactly cancelled and compensated by rotation caused by another molecule. Hence, this becomes what we call meso compound. This becomes achiral due to internal compensation. After that, my dear lovely students, have a look. Have a look. This is 1, this is 2, then we can simply say it's S changes to R. This is having configuration R. What about this? 1, 2, and 3. This is once again R. So this is RR. Now, here, this is, S changes to R. Now, S changes to R. This is S changes to R. What about this? This is S changes to R. Now have a look. We will compare this with this because it is CHO which was attached to this. CHO and CHO are configuration. CH3 and CH3 are configuration. So this is homomer. Okay. Have a look. Have a look. What about this? What about this? What about this? What about this? Have a look. This chiral center is having Cl behind the plane, but same chiral center in second molecule is having Cl above the plane. That means there is one interchange at chiral center. Above becomes below, below becomes above. When only one or odd number of interchange takes place at one chiral center, its configuration will be different. That means these two are having different configurations. You can check. You can assign configuration, you can assign priority, and you can check. So these two will be having different configuration. Similarly, what about this? This is having below the plane, above the plane. That means one interchange has been taken place. So different configuration. Even number of interchanges, if takes place at one chiral center, configuration remains same. But odd number of interchanges will change configuration. Here, configuration is once again changed. So everywhere configuration is changed. Hence, they are enantiomers. Here, configuration is changed. Here, configuration remains same. What about this? Configuration remains same. So at least at one position configuration is same. At least at one position configuration is different. Hence, these two are what we call diastereomers of each other. Now, after that, we will be having another term, that is epimer. What is meant by epimer? Stereoisomers which have basically different configuration, which differ from each other, and but in configuration only at one chiral center. Only at one chiral center. Have a look. If this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. This is 1, this is 2, this is 3, this is 4, 5 and 6. This is 1, 2, 3, 4, 5 and 6. My dear lovely students, have a look, have a look, have a look. This carbon chiral center 2 with respect to this, they are having different configuration. OH was on right side, here OH is on left side. That means one interchange has been taken place between H and OH. So this is having different configuration at this chiral center. After that, every chiral center is having, similar configuration. So I will say 1 and 2 are C2 epimers, because their configuration is different at chiral center or that carbon center, carbon number 2. Now, after that, what about 2 and 3? What about 2 and 3 and what about 1 and 3? Have a look. Have a look. Have a look. What about 2 and 3? 2 and 3. 2 are having, different configuration at 2. Listen carefully. Different configuration at 2. Yes. After that, they are also having different configuration at 5. That means 2 and 3 are not epimers. Because what are epimers? Epimer means which are having different configuration but only at one chiral center. They are having different configuration at two chiral centers. OH on right, OH on left. OH on left, OH on right. That means they are having different configuration at two chiral centers. So these can be simply diastereomers. Why diastereomers? Because diastereomer means they are having, different configuration at these two and they are having similar configuration at these two. That means they are having at least same configuration at one chiral center, at least different configuration at one chiral center. Hence, they are diastereomers. After that, what about 1 and 3? What about 1 and 3? 1 and 3. 2 having similar configuration, 3 similar configuration, 4 similar configuration, 5 different configuration. That means they are C5 epimers. But my dear lovely students, as epimers have different configuration at one chiral center and similar at others, so we can also call them as diastereomers. So they are C2 epimers or diastereomers. This is C5 epimer or diastereomer. But this is diastereomer, it is not an epimer. So can we say all epimers are diastereomers? All epimers are diastereomers. But all diastereomers are not epimers. Remember this. After that, my dear lovely students, calculation of stereoisomerism. So stereoisomers. If you have to calculate, first of all here, we will write down this as optical isomer because we are talking about optical isomer here only. We have already talked about geometrical isomerism in last or previous session. Now, so it's calculation of optical isomers. Calculation of optical isomers. Let us write calculation of optical isomers only. Calculation of optical isomers. Have a look, have a look. Let me write down calculation of optical isomers. Have a look, my dear students. For calculation of optical isomers, you have to check whether the compound is, whether the molecule is unsymmetrical or symmetrical. If molecule is unsymmetrical, then optically active forms, that means enantiomers, E forms is 2 raised power n. Optically inactive, that means mesoforms are what we call 0. At that time, total forms are 2 raised power n. And enantiomeric pairs will be obviously number of enantiomers divided by 2. So what is n? N means number of optical isomer area. That means that position, that area due to which optical isomerism occurs. Similarly, if molecule is symmetrical, then case 1 is if n is even, case 2 is if n is odd. If n is even, E is 2 raised to the power p minus 1, and what we call E is equal to 2 raised power n minus 1, and this m is equal to 2 raised power p minus 1, and total enantiomer and mesoforms will be 2 raised power n minus 1 plus 2 raised power p minus 1. But remember, n here is even, then p is equal to n by 2. If n is odd, then I mean to say p is equal to n plus 1 divided by 2. Here total forms will be 2 raised power n minus 1. That means enantiomer will be 2 raised power n minus 1 minus 2 raised power p minus 1, and m is equal to 2 raised power p minus 1. So this is the total formula, and enantiomeric pairs will be always E by 2. Now have a look. If we want to use this over here, this is 1, 2, 3, and this is 4. Here molecule is unsymmetrical, n is equal to 4, so I will write down n is 4 and molecule is what we call unsymmetrical. Molecule is unsymmetrical. Now you will simply write down formula and calculate the answer. Similar. This is 1, 2, and 3. 3 chiral centers are there. That means 3 optical centers, optical isomer areas are there. So n is equal to 3. So this is also an unsymmetrical. So you just write down formula 2 raised power 3. That means 8. Here 2 raised power 4 is 16. Now here 1, 2, 3, and 4. So you can write down n is equal to 4. Once again, this is an unsymmetrical species. So 2 raised power n, because you have to find out total optical isomers only. Now, this is the 1 OI area. This is 1 OI area. That means n is equal to 1. No need to write down the formula directly. You can write down, as this is the formula, so there will be simply 2 isomers in total. 2 isomers will be in total. 2 isomers will be total. Now, after that, have a look. This is n is equal to 1, this is n is equal to 2. So n is equal to 2, but this molecule is unsymmetrical. So you can write down 2 raised to the power 2, that means 4. Now here, this is one area, this is another, because chiral center is an optical isomer area. This is optical isomer area, this is optical isomer area, and this is optical isomer area. So 1, 2, 3, 4, 5, 6. So n is equal to 6. 1, 2, 3, 4, 5, 6. N is equal to 6. Once again, this is an unsymmetrical species. For example, you are having a question like this. Symmetrical one. Suppose CH3, CHOH, then CHOH, and then CH3. This is the symmetrical species, but here n is equal to 2. So n is equal to 2. That means n is even. When n is even, you have to find out p. P is n by 2. That means p is 2 by 2. That means it is 1. Now after that, you have to write down, as this is, say n is even. So you have to write down, and this is molecule is symmetrical first of all. You have to write down the formula, and formula is total isomers is E plus M. E plus M is 2 raised power n minus 1 plus 2 raised power p minus 1. Now, have a look. This is 2 raised power n minus 1. That means 2 raised power 2 minus 1 plus 2 raised power 1 minus 1. This is 2 raised to the power 1, and this is 2 raised power 0. And you know 2 raised power 0 means 1. That means it is 2 plus 1. Answer is 3. Similarly, if you are having a structure like this, CH3, CH double bond C, then after that you are having CH, then it is OH, then it is C, double bond CH, single bond CH3. Have a look. This is one OI area, this is another, 3 OI areas are there, but molecule is symmetrical. Symmetrical molecule, n is 3, 3 means it is odd. And in case of odd, P is equal to n plus 1 divided by 2. You know that. But for total isomers, we don't need P, because we know it is 2 raised power n minus 1. So what is n? N is 3. So it is 2 raised power 3 minus 1. Answer is 2 raised power 2 means 4. I hope this is clear till now. Let me know quickly. Is this clear till now? Is this clear till now? Am I clear till now? Let me know quickly. Let me know quickly, my dear lovely students. Let me know quickly. Am I clear till now? Am I clear till now? Let me know quickly. Okay, that is great. That is great. That is great. Now, after that, we will be having racemization. So, what is racemization? Racemization is basically the process during which racemic mixture is obtained. What is racemic mixture? Optically inactive mixture which is obtained by mixing two optically active enantiomers in equal proportions. Have a look. Have a look. So, any optically inactive mixture which is obtained by mixing of two optically active enantiomers in equal proportions is called racemic mixture. And it is denoted by plus minus DL or RS. But it is optically inactive because of external compensation. And the process of formation of this racemic mixture is called racemization. What is meant by this? Have a look. If you are having a structure like this, this is Br, this is F, this is Cl, we know this is what we call R. This is having one chiral center. That means this molecule is chiral, this is optically active. If a plane polarized light is passed through it, and that plane polarized light will be, deflected either towards right or towards left. Similarly, if I take its enantiomer, say for example like this is Cl, this is Br, and this is F. Its configuration is S. Light passed through it will also be deflected, but both are enantiomers, and enantiomers have same magnitude of rotation. That means if light is passed through it and it will rotate, suppose this will rotate light towards right 50 degree, then this will rotate 50 degree but left, because they are enantiomers. They are having same magnitude of rotation, but they differ in sign of rotation. One will rotate plane polarized light towards right, another towards left. If it will rotate towards left, it will rotate towards right. Suppose both are together in a container in equal proportions. That means we form a mixture of two optically active enantiomers. We form this mixture. This mixture is known as the racemic mixture because this mixture is optically inactive. Why? Because when light is passed now, if light is passed now, what will happen over here? If plane polarized light is passed now, it will pass without any deflection. Why? Net deviation will be zero. Why? Because this will rotate light towards, suppose, right 50 degree. This will rotate light towards left 50 degree. That means rotation caused by this rotation of light or rotation of plane polarized light caused by one molecule is compensated or cancelled by rotation of plane polarized light caused by another molecule. Not within the same molecule. This is different molecule. Hence, this is external compensation. That's why as light is passed without any deflection, we can call this mixture as optically inactive mixture. This is optically inactive mixture. Now, have a look. Now, the method with the help of which we can separate this and this, that means with the help of which we can separate two optically active enantiomers, is known as resolution. That means our another topic is resolution. So resolution is simply the process with the help of which we can separate two optically active enantiomers from its racemic mixture. Then remember that enantiomer which is separated out is known as a resolvable compound, and as we know, when it is separated out, it is optically active. Hence, resolvable compounds are always optically active. I hope this is clear till now. I hope this is clear. I hope first chapter is done and dusted, and I hope this is clear to you all. Let me know quickly. Let me know quickly. Am I clear till now? Let me know in the chats. Let me know in the chats quickly. Am I clear? Let me know in the chats. Am I clear till now? Am I clear till now? Let me know quickly. Okay, that is great. That is great. So let us finish. I mean to say haloalkanes. Let's finish haloalkanes and haloarenes. But before that, give me a second. Now, are you ready for this chapter? Let me know quickly. Are you ready for this chapter? Are you ready for this chapter? Should we start? 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 Come on, let me know quickly. At the rate of a savage medic, I have to take care of organic chemistry only, my dear lovely student. So I will be finishing your organic chemistry today. Whatever will be remaining there, I will record that. So don't worry, I will upload that as well. So don't worry about that. So should we start? Should we start? Should we start? No, we have a lot of, say syllabus over here. We have haloalkane, haloarene, then alcohols, phenols, ethers, then aldehydes, ketones, carboxylic acids, then amines, diazonium salts, and if time permits, we will be discussing previous year questions as well. So, come on. Whatever is possible in one shot, I will be discussing each and everything. Don't worry about that. Okay. Come on. Let's start. I will give a short break after this chapter. I will give you a short break after this chapter. Okay, don't worry at the rate of King. I will make video of biomolecules. I will record that for you people. Don't worry about that. And each and everything, I will record each and everything related to biomolecules, and I will try to complete that biomolecule within 10 to 20 minutes or maximum half an hour. So don't worry about that. So that everything will be clear and your question will be directly from that if asked. Okay. So, come on. Okay, my dear lovely students, come on. Let's begin. First of all, methods of preparation of haloalkanes from alcohols. Remember, whenever you are having an alcohol and you want to prepare haloalkane from that. Remember, such reactions are examples of. So I can simply say such reactions are examples of substitution nucleophilic, or you can say nucleophilic substitution reactions. So these are basically nucleophilic substitution reactions. Now, what we have to do in these reactions is we have to replace OH by X. How? Let's see that. First of all, reaction of alcohol with HX. Have a look. Reaction of alcohol with HX. Have a look. What we have to do is we have to remove this OH and H, and instead of OH we have to replace OH by X. So this is the reaction. And remember, this type of reaction is once again SN reaction, that means nucleophilic substitution reaction, but this reaction generally takes place via SN1 mechanism. This reaction generally takes place via SN1 mechanism. How? Have a look. This is ROH. It will react with HX, and protonation of alcohol takes place in first step. That means it will become ROHH. Now, have a look, listen carefully. This is poor leaving group. Now, when it gets protonated, when oxygen is having a positive charge, it becomes a good leaving group. Now, if it undergoes via SN1 mechanism, then what will happen? This O will abstract, electrons will attract electrons from this carbon, and it will be lost in the form of water. This step is the slowest step, and hence rate determining step of the reaction. So we will get a carbocation over here. Now, whenever carbocation is there, you have to rearrange if possible. So rearrange if possible. You have to rearrange it if possible. Then After that, my dear lovely students, in next step, last step, X minus will attack as a nucleophile, and this is fast step, rate independent step, and we will get, I mean say, alkyl halide. But you have to remember this very, very important point over here. Have a look. This R is not equal to 1 degree. What does that mean? What does that mean? What does that mean? Have a look. That means primary alcohols, I will write down except, say for example, neopentyl alcohol, except neopentyl alcohol, because neopentyl alcohol can show this reaction. So this R is not equal to 1 degree, but it can be neopentyl alcohol. Okay. So 1 degree alcohols generally show this reaction via SN2 mechanism. Now have a look. Have a look. How? First of all, alcohol will react with HX, but this alcohol here is 1 degree. Now reacts with HX and it will simply undergo protonation. And it becomes once again a good leaving group. But now it is not that good leaving group that it will leave first and forms a carbocation, because 1 degree cannot form that much stable carbocation. Hence, nucleophile first came, nucleophile, which is lost over here. This nucleophile will come and it will attack to electron deficient site. Nucleophile will attack electron deficient site on one side and water will leave on another side. That means water will be left. So it will be simply one step mechanism. So it will result in the formation of alkyl halide. But as the reaction generally takes place like this, so we can simply say that rate of this reaction depends on carbocation, and as it depends on carbocation, so among alcohols, 3 degree alcohol, after that 2 degree alcohol, after that 1 degree alcohol, that will be the reactivity order towards this reaction among alcohols. So I will write down among alcohols, reactivity order will be 3 degree, greater than 2 degree, greater than 1 degree. And among halogen acids, order will be simply HI, then HBr, then HCl, and no need to write HF. Now, after this, we will be having reaction of alcohol with HCl first. As we know, among halogen acids, HCl is the least reactive. That is why. What will happen? Have a look. If you are having a primary alcohol, primary alcohol generally does not react generally with HCl. Similarly, if we talk about secondary alcohols are more reactive as compared to 1 degree alcohol. So it can react, but rate will be slow. But if we talk about tertiary alcohols are the most reactive alcohols among 1 degree, 2 degree and 3 degree. So these tertiary alcohols react immediately with, I mean to say, HCl and forms a product. Now, that means this tertiary alcohol, as it is very reactive, it does not need any catalyst, but generally primary and secondary needs catalyst. So suppose I will write down anhydrous zinc chloride over here, and let us suppose I will write down zinc chloride over here, but this reaction can be taken place without zinc chloride. And if reaction takes place at room temperature, what will happen over here? Listen carefully. Mixture of HCl and zinc chloride. I will write down over here. Mixture of HCl and zinc chloride in the ratio of 1:1. This is known as Lucas reagent. So with the help of Lucas reagent, we can distinguish whether our alcohol is primary, secondary or tertiary. How? Have a look. We know this alcohol will react with this very, very immediately, and it will result in the formation of CH3, CH3, and it results in the formation of first a carbocation. After that, Cl- will attack and it will form this alkyl chloride. Now, we know this alkyl chloride once formed, there will be a turbidity, whiteness, milkiness or cloudiness, white color cloudiness will be there. That means this product will be formed immediately. That means turbidity will be formed, but immediate turbidity. So turbidity appears due to formation of this immediately. Immediately means within seconds, turbidity appears. But here, reaction will be slow. This will be reacting with this, but it will take some time. That means this product is obtained over here. But my dear lovely students, product formation will take some time. That means turbidity appears here also, but after some time. That means turbidity appears, but this appears after few minutes. After, let us suppose 5 to 10 minutes. That means after few minutes, this is after few seconds, or in seconds, in minutes. Here, I will say no turbidity appears at all. Why there is no turbidity here? Why no turbidity appears here? Because primary alcohol generally does not react with HCl at room temperature. But yes, if temperature is increased, that means if we heat this, say condition is at high temperature, then it will react with this. That means CH3, CH2, Cl will be formed. That means turbidity will appear. So, with the help of this Lucas reagent, or with the help of this turbidity, we can simply say whether our test tube contains primary alcohol, secondary or tertiary. Because suppose we have a doubt that our test tube contains primary alcohol, secondary or tertiary, we will put simply Lucas reagent over here. If turbidity appears immediately, we will say that it is tertiary alcohol. If turbidity does not appear at all, we will say primary alcohol. If turbidity appears, but after some time, we will say it's a secondary alcohol. So this test, with the help of which we can distinguish primary, secondary and tertiary alcohol by using Lucas reagent, is known as Lucas test. And reaction of alcohol with HCl in presence of zinc chloride, that means reaction of alcohol with Lucas reagent, is known as Gru's reaction or Gru's process. So we can say that process as Gru's process. So we can say Gru's process. So this is simply a Gru's process, because here alcohol reacts with Lucas reagent and forms what we call alkyl chloride. But remember, this can also show reaction, but phenol does not show this reaction with Lucas reagent. Why? Because if we take phenol with this, we have to break, have a look, we have to break this CO bond, but we know this CO bond is very strong due to partial double bond character as a result of resonance. So it is not, phenol never shows what we call reaction with Lucas reagent, or even not even on heating. This can show on heating, but this cannot show turbidity even on heating. Remember this is a very important point. After that, my dear lovely students, we will be having another reaction, that is reaction with PCl5. Simple. You have to remember this reaction in this fashion. Very, very, very simple. This is Cl. After that, this is having PCl3, and then this is Cl. What you have to remember is simple. When these two react, they will form HCl, they will form RCl, and they will form what we call POCl3. Very, 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 very simple reaction. That means whenever you react alcohol with PCl5, OH of alcohol will be replaced by Cl. That means you will get RCl, and other products will be POCl3 and HCl. And remember, this product formation takes place via SN2 mechanism, as well as this can be formed by SNI mechanism, but SNI is not in our syllabus. So this can be formed with the help of SN2 reaction. And remember, during SN2, if reaction takes place, remember, if reaction takes place at that carbon which is chiral, that means if OH is attached to chiral carbon, finally Cl goes to chiral carbon. So if reaction SN2 takes place at chiral carbon, then configuration of chiral carbon in reactant, I mean say substrate, and product will be different. If it is configuration is S, in product it will be R. But in not general, whether it is chiral center or not, in overall, we can say during SN2, inversion takes place. After that, reaction with PX3. Suppose you have ROH and you have PX3. I will write down PX3 like this. P, X and X. And I will write down alcohol 3 moles. 3 moles of alcohol. To balance the reaction, have a look what we will do. What we will do is very, very simple. Remove 3 times HX, then, sorry, I will write down like this. I will erase this. Let me draw it in this fashion. Have a look. Let me draw it in this fashion. Have a look. If you are having an alcohol and alcohol, very, very simple reaction, and this alcohol is treated with what we call PX3. What we have to do is, we will simply write down like this. X, then it's P, then it's X, and then it is P. We will form 3 times RX simply. That means you have to replace OH by X, OH by X, OH by X. That means we will get 3 times RX. That means alkyl halide is obtained, and then H3, then P, and then O3. That means H3PO3, phosphorus acid. So this is the product. This is the product. But sometimes same reaction is given because PBr3 and PI3, they are, I mean say they can be generated in situ. They can be generated in situ. What is meant by that? That means sometimes you have given like this, Br2 and red phosphorus, or Br2 and phosphorus. Remember, that means PBr3 whenever it is given. Similarly, if it is given I2 and red phosphorus, whenever it is given, you have to consider it as PI3. I mean to say, for example, if reaction is like this, alcohol on treatment with iodine and red phosphorus, what you have to do? You have to consider it as PI3. Then what will PI3 do? That will simply replace OH by halogen. And what is the halogen in PI3? It's iodine. So it will result in the formation of Ri. And H3PO3 if you, I mean say, balance the reaction as well. So simply what you have to do in this reaction is replace X by OH. Replace OH by X. That means this is once again an SN2 reaction. Once again an SN2 reaction. After that, reaction with SOCl2. Reaction with SOCl2. It is like this. Remember, SOCl2, you can write down SOCl2 in this fashion. After that, one of the products will be HCl, RCl, and another will be SO2. That means whenever reaction of RCl takes place with ROH takes place with SOCl2, thionyl chloride, what will be the product? Product will be RCl. That means you have to replace OH by Cl. After that, side products are gases. That means one is sulfur dioxide, another is HCl. Both are gaseous products. Gases will, I mean say, evaporate. That means we will get RCl in pure form. So if we want to prepare RCl from alcohol, this is considered as best method to prepare alkyl chloride from alcohol. And remember, this is the reaction where you have to remember whether reaction takes place in presence of pyridine or in absence of pyridine. Remember, in presence of pyridine, as base, RCl is obtained with a phenomenon known as SN2, and in absence of pyridine, RCl will be formed. That means product will be same, only there will be difference in stereochemistry. This is what we call SNI mechanism. That means here inversion will take place. Here inversion will take place, but here retention will take place. This is the only difference, otherwise product formation will be same. And this reaction is known as Darzon's procedure. This is known as Darzon's procedure, or you can say Darzon's halogenation reaction. Now, this is clear. After that, and this is considered as best method to prepare alkyl chloride from alcohols. After that, my dear lovely students, we have another reaction that is from hydrocarbons, but from alkane first by free radical halogenation. I have already shown this reaction in 11th. Let me show you once again. Suppose we have alkane and we have halogen. What we have to do is we have to simply replace this H by X. That means our product will be Rx plus Hx. And this reaction is an example of free radical substitution reaction, and this reaction takes place either in presence of heat or light or heat, at high temperature or in presence of light. Now, intermediate of this reaction is radical, and remember, among halogens, among X2, the most reactive halogen is F2, after that it is Cl2, after that it is Br2, after that it is I2. But among hydrogens, as this is the free radical reaction, among hydrogens, remember forever, it is actually 3-degree hydrogen, which is more reactive than 2-degree hydrogen, is more reactive than 1-degree hydrogen. What you have to do is, you have to replace hydrogen by halogen. You have to replace hydrogen by halogen. For example, if I write a reaction like this, CH4Cl2, suppose Cl2 is taken in excess, then what will happen? First, it will replace one hydrogen and results in the formation of CH3Cl. Then another hydrogen forms CH2Cl2. Then another hydrogen and forms CHCl3. Then another hydrogen and forms CCl4, and this CCl4 will be the major product at that time. You can have question like this. In this, you have a question which can be asked like this. You will be having an alkane, and question will be, how many monochlorinated products will be formed? How many monochloroderivatives will be obtained during this reaction? Now, how to do this reaction? Very, very simple. First of all, find out different types of hydrogens. You know, this is having 4 different types of hydrogens. After that, remove one hydrogen by one Cl and form monochlorinated product like this. You can form a monochlorinated product like this. This is formed from A. Similarly, from B, you can form like this, CH3, then it is CH3, then here it will be Cl, and then it is CH3. So this is product formed from B. Similarly, from C, you can form like this. And we know here, this is the major product. After that, from D, product is like this. But remember, during chlorination, you cannot say that if we remove this hydrogen, tertiary hydrogen, it forms more stable radical, and product formed from more stable radical is, say, major product. Why can't we say? Because chlorination is not selective reaction. We can say that in bromination, because bromination is a selective reaction. So this is the major product. So if we talk about how many, products are formed, excluding stereoisomers, then we will be having 4 products. But including stereoisomerism, we will say that this is having a chiral center, this is having a chiral center, this is having a chiral center, no, this is not having any chiral center, this is having a chiral center, no, this is not having, yes, this is having a chiral center, this one. This is CH3, this is CH2Cl, this is CH2CH3 and H, this is having a chiral center, and this is having a chiral center. So whenever chiral center is there, that means optical isomer area is there. So 2 raised power n, because this is unsymmetrical, that means it forms 2, optical isomers. One is R, another is S. That means similarly R and S, 2 and 2, 4, 5, 6. So including stereoisomers, we will say 6 isomers are formed. But remember, chlorination is not, selective. So after that, remember, among hydrogens, what will be the reactivity order? Have a look. Reactivity order will be like this. 3-degree hydrogen will be always more reactive than 2-degree, will be more reactive than, 1 degree. But reactivity among these hydrogens is like this. 3-degree hydrogen is more reactive than 1 degree 5 times, and 2 degree is more reactive than 1 degree 3.8 times with respect to chlorine. But if we talk about bromine, then it is 1600 times more reactive than 1 degree, and this is 82 times more reactive than 1 degree. This is with respect to bromine. This is with respect to bromine. This is with respect to bromine. Now, after that, if same reaction is given, with bromine, now what will happen over here? What will happen over here? How many monobrominated products will be formed? Same type of products will be obtained. Same types of products will be obtained like this. This will be A, then it will be B, it will be B like this. So this is B, then C will be like this, then D will be like this, D will be like this. So this is D. But here major will be this one. That clearly indicates, note down this point, that clearly indicates that bromination is a selective reaction. Bromination is more selective than chlorination, which means that whenever bromination of alkane takes place, major product will be formed from more stable carbon free radical. After that, my dear lovely students, we will be having another reaction that is from alkenes. How? By addition of HX. Remember, first of all, this reaction is an electrophilic addition reaction, and intermediate of this reaction is carbocation. And products formed will be Markovnikov's product if this HX is added to an unsymmetrical alkene. For example, our alkene is like this: CH3, CH, or let me write down R over here. If we are having an alkene, RCH double bond CH2 plus HX, then what will happen over here? First of all, X minus will be lost. This will be the rate determining step, and carbocation will be obtained. Now, rearrange this carbocation. Rearrange if possible. After that, what will happen? After that, you have to simply attack by this X. This will be a very fast reaction, and product formed will be this one. This will be a Markovnikov's product. What is Markovnikov's rule? That negative part of this goes to that carbon-carbon double bond which is having lesser number of hydrogen. But this Markovnikov's product, this will be the major product. Other product will be X will go to this and H to this. That means one more product will be RCH2 CH2X. That will be the minor product. But Markovnikov's product is failed if there is rearrangement. If there is rearrangement, then at that time Markovnikov's rule or statement is failed. Why that is failed? Have a look. Because according to Markovnikov's statement, this negative part should go to this, but it will not go to this. Have a look. What will happen? What will happen over here? Have a look. It will result in the formation of CH3, CCH3, then CH3, then CH positive, and then it will be, here CH3. After that, this methyl carbanion shift will take place. That means there will be a rearrangement. Why rearrangement takes place? So as to form more stable carbocation. So when more stable carbocation is formed, it will result in the formation of this. And finally, my dear lovely students, finally what will happen? This X minus will attack this one. When X minus attacks this, have a look. This is the rearranged product. This is not the product which is formed according to the statement of Markovnikov's rule. So Markovnikov's rule is not applicable over here. Remember this. After that, remember if this HX is HF, HCl, HBr, HI, then rate of reactivity among HX will be, it will be among HX, reactivity order will be simply HI, HBr, HCl and HF. And among alkenes, what will be the rate? Rate is simply directly proportional to stability of carbocation formed in RDS. But you have to remember this point. This is very important point, that if you have to add HX instead of that, if it is HBr. But now this HBr is added to unsymmetrical alkene in presence of peroxide. At that time, my dear lovely students, product will be anti-Markovnikov product. Now Br will go to this and H to this. At that time, it will be anti-Markovnikov product. So anti-Markovnikov product, peroxide effect has been taken place, also known as Kharash effect. It takes place only if peroxide is there, HBr is there, and unsymmetrical alkene is there. All these three should be present. If HBr without peroxide, then reaction takes place according to Markovnikov's product via more stable carbocation. I mean to say reaction will be at that time electrophilic addition. But this is not electrophilic addition. This is free radical addition reaction. Similarly, if it is HF, HCl, HI, whether in presence of peroxide, in absence of peroxide, it is electrophilic addition. But HBr in presence of peroxide, free radical addition. HBr in absence of peroxide, electrophilic addition reaction. I hope this is clear to all. Now, after that, addition of X2. Once again, this addition can be taken place in two ways. X2 in presence of, say for example, non-polar solvent. Then what will happen over here? What will happen over here, my dear students? Simple. Reaction is very simple. In CCl4, what you have to do is you break just pi bond and then add X. But addition of X should be anti. That means anti-addition takes place. And remember, if X2 is Br2, its color is reddish brown. Its color is reddish brown color. And during this reaction, that color is decolorized. I mean, say reddish brown color is decolorized during this reaction, and this reaction can be used as a test for unsaturation. Similarly, if it is X2 in presence of water, or we can say HOX, at that time this is negative part, this is positive part, then what will happen? What will happen? No rearrangement takes place, neither in this nor in this. What will happen over here? You have to add now negative part and positive part like this. This results in the formation of halohydrin. This is vicinal dihalide but anti-addition. Here halohydrin but anti-addition. After this, halogen exchange reaction. Number one is like this. If you are having Rx in which X is either Cl or Br, when it is treated with, remember my dear students, with NaI or Ki in presence of dry acetone, here simple halogen exchange reaction will take place and it will result in the formation of NaI. Here it will result in the formation of NaCl or NaBr, but this is insoluble in this, I mean say solvent, and it is precipitated out. That's why reaction will be favored by what we call Le-Chatelain's principle, and this reaction is an example of SN2 reaction, and this reaction is called Finkelstein reaction. This is called Finkelstein reaction. After that, we will be having second reaction. Similar alkyl halide, whether it is alkyl chloride or alkyl bromide, this is treated now with heavy metal fluorides, say for example AgF, not necessary AgF, you can use AgF2, you can use Ag2F2, COF2, COF3, SbF3, AsF3, you can use any heavy metal. Now, what will happen over here? This fluorine will replace chlorine or bromine. That means halogen exchange will take place and NaX will be precipitated out. Now, this is known as what we call Schwartz process. This is called Schwartz process. After that, methods of preparation of haloarene but from aromatic hydrocarbons by direct halogenation. Number one is nuclear halogenation. Have a look. If you are having a hydrocarbon, say for example benzene, and you want to perform its halogenation, It's halogenation. Let's suppose either chlorination or bromination, not iodination, not fluorination, similarly that of alkane. Why? I will tell you that. Now, reaction takes place in presence of Lewis acid. That means in absence of light, remember that means in darkness. Both these will form an electrophile as Cl positive. But if it is Br2, then Br positive. That electrophile will go to the ring at any place because electrophile loves electron-rich sites, but benzene is having, say similar electron density, so it will result in the formation of chlorobenzene. Now, if you use bromine, then bromobenzene will be there plus HBr. But we cannot use iodine because Hi is there, that will direct a reaction backwards, that is a reversible reaction. And we cannot use F2 because that is too violent to be controlled. Now, so this is what we call nuclear halogenation, because nucleus is this one, halogen is introduced to the nucleus. This is known as nuclear halogenation. So this reaction is simply an example of electrophilic substitution reaction. Similarly, my dear lovely students, if your hydrocarbon is like this, toluene is there, and you want to perform chlorination or bromination, and bromination takes place in presence of Lewis acid and in absence of light. Once again, Cl positive will be the electrophile, and that electrophile will go to that position of the ring which is having much more electron density, and we know this is what we call ortho-para directing due to hyperconjugation. CH3 donates electron due to hyperconjugation and increases electron density of a ring at ortho and para position. Hence, Cl will go to either ortho position or to para position. But here Cl and CH3 are very closer to each other, so there will be more steric repulsion. Hence, this will be minor and this will become the major product. So this is what we call nuclear halogenation. After that, we will be having side chain halogenation. Suppose you are having a hydrocarbon like this, in which you have hydrogen present at nucleus as well as in ring. Then reaction takes place like this. Suppose we are having chlorination or bromination once again, but reaction takes place in presence of light or at high temperature. In absence of sunlight, then at that time, remember, this reaction is also known as benzylic halogenation and is an example of free radical substitution reaction. That means intermediate here are free radicals. Now, so free radical will simply, Cl and Cl will form Cl radical. That Cl radical will replace H from benzylic position, and we will get this one. But if Cl2 is in excess, then it will replace another H by Cl. If Cl2 is in excess, another H will be replaced by Cl. So reaction will be carried out till all these benzylic hydrogens will be replaced. But remember, when we do side chain halogenation and when we do nuclear halogenation of toluene, that depends on if takes place in presence of Lewis acid, then nuclear halogenation. In absence of Lewis acid and presence of light, then side chain halogenation. After that, from aromatic amines. Have a look, my dear lovely students. We will be having an aromatic amine, suppose aniline. If this is treated, remember this forever. If this is treated with sodium nitrite and acid, say for example HCl, H and NO2 will be formed. That means nitrous acid will be formed within the reaction, and acid is taken in excess at a temperature of 0 to 5 degrees Celsius. What will happen? Here benzene diazonium salt will be obtained. This reaction is known as diazotization. This is known as diazotization reaction. So whenever aniline, primary aromatic amine, reacts with this at 0 to 5 degrees Celsius, we get diazonium salt. But remember, if temperature is higher than this, then this is, say less stable, unstable at higher temperature. That's why we have to keep temperature at this if we want to perform this, if we want to form this. After that, my dear lovely students, have a look. Now, if we have like this, if we treat it with Cu2X2, or you can say CuXHX, where X is either Cl or Br, what will happen? Now this N2 will be replaced by X, but that X which is with copper, that means we will get haloarene, either chlorobenzene or bromobenzene. And this reaction is known as Sandmeyer's reaction. This is known as Sandmeyer's reaction. Remember this. And if this is treated with copper powder in presence of HX, once again X is Cl or Br. Once again we will get chlorobenzene or bromobenzene, but this reaction is known as Gattermann reaction. This is known as Gattermann reaction. And remember, yield of haloarene is like this. It is Sandmeyer reaction, where yield will be more than Gattermann reaction. Gattermann's reaction. So we can simply say this method is preferred to form chlorobenzene or bromobenzene from benzene diazonium salts. If we treat it with Ki, aqueous Ki, and we will warm it. Now what will happen? Here we will get simply iodobenzene. Similarly, if this is treated with HBF4, then this negative part is exchanged. We will get benzene diazonium tetrafluoroborate, and this upon heating will simply form fluorobenzene plus N2 here, N2 here, N2 here, and N2 will be also formed over here. This reaction is known as Bals-Schumann reaction. Remember this. After that, we have chemical reactions of haloalkanes, that means nucleophilic substitution reactions of haloalkanes. Say for example, this is haloalkane. This is our haloalkane. And we want to perform its nucleophilic substitution reactions. Say for example, we are having few examples of nucleophilic substitution reactions over here. Have a look. Very important reactions are these. Now, suppose you are having reaction number 1, suppose you are having with water. What will happen with water? Generally, if it is tertiary alkyl halide, it prefers SN1 reaction, then it will result in the formation of a carbocation first, then water will be attacked, nucleophile will attack. That means instead of OH, instead of X, OH will be there. After that, if you react it with either NaOH or KOH or AgOH, this reaction will be simply SN2 reaction, because it's having OH minus is a strong nucleophile. It will be SN2 reaction, but here R should be either primary or secondary. Tertiary will not show this reaction. Once again, X will be replaced by OH. Similarly, if reagent is like RONA, obviously this is positive, this is negative. Let me write a prime over here so that to differentiate. So this nucleophile will attack and SN2 reaction will be obtained and we will get an ether. Similarly, if sodium phenoxide is there, once again, what will be the product over here? Product will be simply ROPH. That means we will get ether. This reaction is known as Williamson synthesis. So what is Williamson synthesis? Simple. This is an SN2 reaction taking place between alkoxide and alkyl halide and phenoxide and what we call alkyl halide. After that, my dear students, if I take NaSH as nucleophile, what will happen? Nucleophile will replace this X. So we will say RSH thioalcohol will be obtained. Similarly, if I take NaSR, so this is having negative part, this is positive part, nucleophile will replace X. So we will get RSR plus NaX. So let me write down as RSR, that means thioether only. After that, if I take NaN3, sodium azide, Na positive N3 minus, then Rn3 means alkyl azide will be obtained. If I take this one, Na positive, then C triple bond Cr, this C is having a negative charge, this C is having a negative charge, so it will act as a nucleophile. So simply, this R and this C will form a bond and then higher alkyne will be obtained. I hope this is clear. These are very simple reactions, but you have to revise these because this time this is all about revisions. That's why I want to show each and every reaction so that you will, revise each and everything in organic chemistry. Now, have a look. Another will be like this. Another will be like this. If you are having R prime, C double bond O, O and Ag. Suppose this is negative, this is positive. Negative part will attack this and X will be lost. That means we will get R prime COOR. That means ester will be obtained. Similarly, if you are having KCN, you know K positive CN minus, and CN minus is an ambidentate nucleophile. C can attack, N can attack, but what will be the major product? Major product will be RCN. RNC will be the minor product. So this is ionic compound. But if you use AgCN, AgCN is a covalent compound. N will attack. So major product here will be RNC, not RCN. RNC will be the major product here. Here isocyanide will be the major product. Remember that, because this is the covalent compound. Similarly, if you use KNO2, it is basically an ionic compound. So major product will be alkyl nitrite. And if you use AgNO2, then what will happen? This is a covalent compound. Then nitroalkane will be the major product. Nitroalkane will be the major product, my dear lovely students. Now here, if you use NH3, and suppose this is 1 degree alkyl halide, it prefers to go via SN2 mechanism. Then what will be the product? First, it will be RNH2, that means primary amine. If ammonia is taken in excess, then this will be the major product. But if alkyl halide is taken in excess, then it will react with further alkyl halide and form secondary amine first. Then it will react with another alkyl halide and forms what? And forms tertiary amine. It will react with further alkyl halide and forms what? Forms a quaternary ammonium salt. Then this quaternary ammonium salt will be the major product if alkyl halide is taken in excess. But if ammonia is taken in excess, then primary amine is the major product. And remember, reaction of alkyl halide with ammonia to form quaternary ammonium salt via primary amine, secondary amine, tertiary amine. This is known as Hoffmann ammonolysis of alkyl halide. So this is Hoffmann's ammonolysis of alkyl halide. After that, if this is treated with, say for example RMGX, say Grignard's reagent, this is having negative part, this is having positive part. So this R will attack this and X will be lost. That means RR will be formed. Say any organometallic compound in which R is attached to metal, always RR will be formed. I hope this is clear. After that, my dear lovely students, we will be having elimination reactions. For example, we will be having dehydrohalogenation like this. Say for example, you are having this one. You are having this one. What you have to remember is very simple. Very simple reaction. Whenever you are having alcoholic potassium hydroxide, whenever this is there, reaction is always E2 reaction. And during E2, what you have to remember is you have to find out alpha and beta. Remove halogen leaving group from alpha and hydrogen from beta. So you will get two products over here. One is like this. This is known as Hoffmann product because it is formed from that beta which is having more hydrogens. This is having beta having less hydrogens, 2 and 3. This is having 3 hydrogen, more hydrogen, so this is rich. This is having 2 hydrogen, that means this is poor. After that, my dear students, another product will be like this. This will be a ZZ product. And here ZZ will be major product. And this will be minor. But if you are having same reaction like this, and this X is not equal to F here, here it is F. Whenever it is F, you have to check. What you have to check is whether Hoffmann is major or ZF is major. But if it is ClBrI, in this reaction, always major will be ZF. But here you have to check. How to check? Have a look. First of all, this is alpha, this is beta, this is beta. Form a carbanion over this beta and this beta. If this beta is more stable carbanion, then the product formed from this will be major. If this beta forms more stable carbanion, then product formed from this will be major. And in this example, we know this is more stable carbanion. As this is more stable carbanion, so the product formed from this will be always major product. So here, in this example, Hoffman will be the major product. But it is not necessary that Hoffman is major. It depends on the stability of carbanion. This is true. Basically, it depends on stability of transition state. Now, have a look. So this is SATZ product. This will be the minor product in this reaction. After that, reaction with metals. Remember, first, if reaction of alkyl halide takes place with magnesium, then magnesium comes in between C and X and it will form RMgX. This is Grignard's reagent, and in Grignard reagent, this is negative part, this is positive part. Whenever it is treated with acidic hydrogen containing compounds, say for example this one, what will happen? It will abstract H. That means it will act as a base. So it will result in the formation of alkane, and then it is Mg, X and OH. So this is reaction with, metal. Similarly, if reaction of alkyl halide takes place with sodium, then what we have to do is break this one, form a radical, and then combination of this radical takes place. So we will get alkane. After that, if this reaction takes place with zinc, you can have similar type of trick. Basically, reaction takes place in different manner, but you can say a trick like that it results in the formation of symmetrical alkane once again. So after that, my dear students, we have reduction reactions. That means if you are having alkyl halide and it is treated with suppose zinc HCl, suppose it is treated with zinc acetic acid, suppose it is treated with zinc copper couple in alcohol, suppose it is treated with zinc in NaOH, or it is treated with lithium aluminium hydride, it is treated with sodium borohydride, or it is treated with what we call triphenyl tin hydride, or it is treated with HI in red phosphorus. Remember, you have to replace this X by H, but only you have to remember is that 1 degree alkyl halide, or let me write down like this, RH if R is 1 degree, Rx, not RH, Rx if R is 1 degree, then sodium borohydride is there. If sodium borohydride is there, no alkane formation. No alkane is formed. Similarly, if you are having alkyl halide and R is equal to 3 degree, that means if it is tertiary, then if it is reacted with lithium aluminium hydride, no alkane is formed. Instead, form alkene at that time. I hope this is clear. After that, you have nucleophilic substitution reactions of haloarene. Remember, haloarenes generally do not show SN reactions under normal conditions. Why is it so? Very, very simple. Reason number one is resonance. Have a look. Reason number one is resonance. This bond is strong. Because of partial double bond character as a result of resonance. So it is difficult to cleave. So this bond is very, very difficult to cleave because this bond is very strong. If this bond is difficult to cleave, so nucleophilic substitution at this place is difficult. Second, this bond is sp2 hybridized. If we compare this with haloalkane, this is sp3 hybridized. We know bond strength is directly proportional to S character So this is having more S character. More S character means once again bond is strong, so difficult to cleave. So one reason is resonance. Another is difference in hybridization of that carbon to which X is attached. Number third reason, this is first reason, this is second reason. Third reason is that we cannot form a carbocation from that. Why? Because if we break CX bond, it results in the formation of unstable carbocation. Phenyl carbocation is unstable. That means this is not formed. There will be no reaction. SN1 will be not there. SN2 will not be there. So after that, similarly, nucleophile cannot attack this position because there will be electronic repulsion will be there. So in nutshell, there will be no reaction as per nucleophilic substitution reaction of haloarene is concerned under normal conditions. That means if we want to perform nucleophilic substitution reactions of haloarene, we have to perform that under drastic conditions but not under normal conditions. That's why reaction first is Dow's process. What is meant by this? Have a look. If you are having a chlorobenzene and you want to perform a nucleophilic substitution reaction in this, we treat this with NaOH, but at a temperature of 623 Kelvin, 300 atmospheric pressure. That means a very drastic condition. Number one. Number second, after that, after acidification, it will give us what we call phenol. So this is what we call a Dow's process. But remember, if electron withdrawing groups attached at ortho and para position will be added to para or ortho position, rate of this reaction will be increased. That means drastic, we don't need much more drastic condition at that time. Have a look. So we can perform this reaction at lower temperature than this. We can perform this reaction at lower temperature due to presence of electron withdrawing group at para position. So it will form this one, it will form this one, it will form this one. Similarly, if another electron withdrawing group is attached to ortho position, then what will happen? Reaction will be much more faster now. That is why reaction can take place at lower temperature than this, and product formation will be like this. And even if we increase another electron withdrawing group, what will happen, my dear lovely students? What will happen? Reaction will take place very fast now. And even no need of strong, I mean to say this NaOH, no need to use strong base or nucleophile. You can use simply water. You can simply use water and you will simply warm it, and we will get 2,4,6 trinitrophenol means picric acid over here. So have a look. So if I say this is known as picric acid, so if I say what has happened here, I mean to say if this is the reaction whose rate is, say for example, R1 here, if its rate is R2, if its rate is R3, its rate is R4, we will simply say that R4 will be faster as R3 as compared to R2 as compared to R1. In nutshell, more the presence of electron withdrawing groups, more faster will be nucleophilic substitution reaction. Then electrophilic substitution reactions. Have a look. Electrophilic substitution reaction of, say for example, haloarene. We know this chlorine or halogen is ortho-para directing because it donates electron because of resonance and increases electron density at ortho and para position. So it is ortho-para directing. So if we want to perform halogenation, say for example chlorination, what is the electrophile of the reaction? Electrophile is Cl positive. That electrophile will go to either ortho or to para position. So we will get dichlorobenzene, ortho dichlorobenzene and para dichlorobenzene over here. But major product will be always para 1. This will be the major product. This will be the minor product because of repulsion between Cl and Cl. Similarly, my dear lovely students, have a look. If we treat it with HNO3, H2SO4, that means we treat it with nitrating mixture, then what will happen? Here, NO2 positive is the electrophile, you know that. NO2 positive, here it was Cl positive. Now, electrophile will go to either ortho or to para position. So, it will go to either ortho or to para position. So this will be the product. After that, if you want to perform sulfonation, what is the electrophile? SO3, neutral SO3, or you can say if H2SO4 is taken in excess, then SO3 can combine with H positive as well, I mean say sulfuric acid, and it can form SO3H. So finally it is SO3H, sulfonic acid, which is introduced into the ring at ortho and para position. But remember, sulfonation is always a reversible reaction. Sulfonation is always a reversible reaction. It's a reversible reaction. After that, if we want to perform two more reactions, that means one is alkyl chloride AlCl3, that means alkylation, because here carbocation will be formed and you have to check whether rearrangement takes place or not. So then product formation will be like this. This alkyl part will be introduced at ortho as well as para. It will be introduced at ortho and para, and then HCl will be the side product. Here what will happen over here? Acid chloride or acid anhydride, reacts in presence of AlCl3 and results in the formation of acylium ion. No rearrangement will take place here because this is the carbocation, which is, I mean say, stable because of back bonding. So this acyl group will be introduced to chlorobenzene at ortho or para position. But major will be always para. Because in ortho there will be repulsion. So this is minor, this is major. Similarly, this is major, obviously this is minor. Similarly, this is major and ortho one is minor. And my dear lovely students, this is minor and this is major. Sometimes chlorobenzene reacts like this. This is also an electrophilic substitution reaction. Chlorobenzene reacts with this. This is known as trichloroethanol or trichloroacetaldehyde, commonly known as chloral, in presence of H2SO4, and it acts as a dehydrating agent as well. So there will be loss of water will take place. So water will be lost and it will result in the formation of this structure, and this structure is known as, you know that, this is known as diphenyl. This is known as diphenyl trichloroethane. So this is known as DDT, diphenyl trichloro and then ethane, and this DDT is used as an insecticide and is very effective against Anopheles mosquito, very effective against Anopheles mosquitoes, which causes, I mean say, malaria, and very effective against lice that may carry typhus. And two more points of this is that it is fat soluble, and number second is that it is non-biodegradable. So this is all about haloalkanes and haloarenes. Let me know in the chats if these all things is clear to you. Let me know quickly. Now after that we will be having reaction with metal. This will be the last part, and after that we will take a short break. But before that, let me know quickly. Is this clear? Okay, yes, obviously this is the revision. Thank you very much at the rate of Mystic. Exactly, this is for you. This is only for those students who are very sincere and who want to revise, I mean say, whole organic chemistry. Now lastly, it will be reaction in metal. In this we will be having two reactions. One is Fittig reaction, and Fittig reaction is like this. Whenever you are having aryl halide, and it is treated with it is treated with, say for example, sodium in dry ether. What you have to do is, in presence of sodium, break this CX bond and form a radical. Form a radical. This is the trick. Now combine this radical with another radical and we will get a biphenyl over here. We will get a biphenyl over here. This is known as fatigue reaction. Another reaction is known as Wurtz-Fittig reaction. Wurtz-Fittig reaction. Another is known as Wurtz-Fittig reaction. Now, what we have to do is, during Wurtz-Fittig reaction, what we have to do is, have a look. We have to combine aryl halide and alkyl halide in presence of, I mean say sodium in dry ether. Form a radical over here, and the major product is these different radicals will combine. This is the major product. So this is known as Wurtz-Fittig, because Wurtz is alkyl halide and sodium, Fittig is aryl halide and sodium. Wurtz-Fittig is alkyl halide as well as aryl halide with sodium is Fittig reaction. Now, after that, third one is this reaction. If you are having, say for example, iodobenzene, and it is heated with copper. Now, break this one and form a radical. Combine this radical with similar type of radical. You will get this one. This is known as Ullmann. This is known as Ullmann biaryl synthesis. This is known as Ullmann biaryl synthesis. Now, after that, we will be having another chapter, but time is exactly 4:52. Let's meet at 5:05. Let's meet at 5:05. Break till 5:05 p.m. Come on. This will be the break for you. This will be the break for you. You can have some tea or a coffee. 2 hours break. Very good. Arey wah, Datta. At the rate of Datta. 2 hours break. Give 2 hours break to Datta. You can take 2 hours, you can take 3 hours, you can take 4 hours, but those students who are sincere, they will be with me till end of this session. Okay, take care. We'll meet after few minutes. That means we'll meet exactly at 5:05. Welcome back everyone. Let me know quickly, am I audible and visible to everyone? Let me know quickly, am I audible and visible to everyone? Let me know quickly. Am I audible and visible to everyone? Let me know quickly. Come on. Let me know, am I audible and visible to everyone? Let me know quickly without wasting time. Okay, at the rate of Supriya, thank you. Thank you. Okay, let's get started. So, next chapter is alcohols, phenols and ethers. Very important chapter, have a look. First is methods of preparation of alcohols from alkenes. Now, have a look. By acid catalyzed hydration, that means you have to form an alcohol, but from alkenes by acid catalyzed hydration. That means, what is meant by acid catalyzed hydration? That means you have to add water, but in presence of acid. So both H2 and H positive, what will happen over here? They will result in the formation of H3O positive like this. So reaction takes place in this fashion. It is H3O positive. So first protonation of alkene takes place. And it results in the formation of a carbocation first. So it will result in the formation of a carbocation first. And this step is the rate determining step of the reaction. After that, have a look. After that, carbocation has been formed, then water will attack. This water will act as a nucleophile. Nucleophilic attack will take place on a carbocation. But first, rearrange if possible. If carbocation is the intermediate, you have to check whether rearrangement takes place or not. That means rearrange if possible. Now, after that, it will result in the formation of this one, OHH with a positive charge. Finally, deprotonation will take place. So, deprotonation will take place and it will result in the formation of an alcohol. So, remember, rate of this reaction is directly proportional to stability of, carbocation formed in RDS. That means, which alcohol can form this reaction much faster, which can show this reaction much faster, which alkene can show this reaction much faster is that alkene which simply, can form more stable carbocation. So this is the reaction which is known as acid catalyzed hydration. After that, oxymercuration, demercuration, very simple reaction. Whenever you are having an alkene and oxymercuration, demercuration means mercuric acetate will be there and water. After that, you will be having NaBH4 OH minus. Whenever you saw these types of reagents, remember, you have to remember this. Whenever this reagent is there, you have to add water across the substrate. What is the substrate? Alkene. So across carbon-carbon double bond, but according to Markovnikov's rule. That means you have to add water. So this is indirect hydration simply, but without rearrangement. That means you have to add water, but according to Markovnikov's rule, that means negative part will go here and positive part will go here. So this is the product of this reaction. Simple reaction. After that, hydroboration oxidation. It is this one. Whenever you are having an alkene and you want to perform hydroboration oxidation, that means there must be either diborane or borane, and after that H2O2 OH, hydrogen peroxide in basic medium. When you saw this type of reagent, you have to add water. That means once again this is indirect hydration. Add water across carbon-carbon double bond once again. But according to anti-Markovnikov's rule, no need of mechanism, mechanism means there is no carbocation formation, no rearrangement. So what will we do is, we will add water, but according to anti-Markovnikov's product. So it is like this. But I can show this in this fashion, so that you will remember that OH here and H here, they should be added from the same side. That means if it is added above the plane, this is also, this should add above the plane, below the plane, because this is syn addition reaction actually. After that, from carbonyl compounds, reduction of aldehydes and ketones. Have a look, my dear lovely student. This is aldehyde or a ketone. Whenever you want to perform, you want to form, I mean say alcohol, what you have to do? What you have to do is simple. Break one bond between carbon and oxygen, give hydrogen to carbon as well as oxygen. That means product will be simply like this. It will be C, then here it will be H, here it will be OH. That means we will get alcohol. Now the question is, what are the, I mean say reagents over here with the help of which we can perform this reaction? Number one, H2 in presence of catalyst. Catalyst can be either nickel, platinum, palladium, generally nickel, platinum, palladium, or it can be lithium, aluminium hydride. If it is written lithium, aluminium hydride, it's okay. But if it is written lithium, aluminium hydride followed by hydrolysis, that can also be the correct option. Okay. After that, sodium borohydride. After that, sodium in alcohol, my dear lovely students. But remember, aldehyde in this reaction. I mean say aldehyde in this reaction. Aldehyde during this reaction. Aldehyde during this reaction gives primary alcohol. Primary alcohol. And ketone during this reaction gives secondary alcohol. Ketone during this reaction gives secondary alcohol. Gives secondary alcohol. Remember this as well. Remember this as well. After that, have a look. Reduction of ester. Ester is this one. Ester is this one. And what happened over here is you have to break. You have to break. What? Have a look. Have a look. You have to break this bond and this bond. When you break this bond, add H to this and H to this. When you break this bond, add H to this, add H to this. That means after breaking bond, you have to add hydrogen. So it will result in the formation of RCH2OH. This will become RCH2OH and this part will become R prime OH. But remember, this reaction takes place either with the help of lithium aluminium hydride or sodium in alcohol or H2 in presence of catalyst. Nickel, platinum, palladium you can use copper chromite as well. Now, after this, but remember, sodium borohydride cannot reduce. Sodium borohydride cannot reduce, I mean to say ester. Cannot reduce ester. After that, reduction of carboxylic acid. This is carboxylic acid. This is carboxylic acid. What you have to do is very simple. Break this bond, add H to this, add H to this. Break this bond, give H to this, give H to this. So what will be the product? Product will be simply RCH2OH plus water. No need of no need to write water there. So this is lithium aluminium hydride. Either followed by hydrolysis. Number second, diborane followed by hydrolysis. Remember. Now, you must know this one, that sodium borohydride and H2 in presence of catalyst and sodium in alcohol are not generally used After that, now from Grignard's reagent, have a look. If you have an aldehyde or a ketone and Grignard's reagent is there, very simple reaction. Reaction takes place in presence of dry ether. This is negative part, this is positive part. This will act as a nucleophile. It will attack this and this will be broken. Now, it will be R, this will become O minus. To this O minus, MgX will be, showing the attraction. Now, after this will undergo hydrolysis, my dear lovely students. Whenever hydrolysis is there, so this O becomes OH, so it will result in the formation of an alcohol. If it is formaldehyde, we will get primary alcohol. If it is, aldehyde other than formaldehyde, we will get secondary alcohol. If it is ketone, we will get tertiary alcohol. Remember that. Remember that. And with this alcohol is having more number of carbons as that of aldehyde or ketone depending upon the value of R. After that, if it is ester like this, R C double bond O R. Let me draw a line over here, that means R prime, to distinguish this R and this R. After that, let me distinguish this with another R double prime MgX, that means Grignard reagent. This is having a negative part, this is having a positive part. Now what will happen over here? Very, very simple reaction. Very, very simple reaction. This R will act as a nucleophile, it will attack this and it will form this addition product, that means adduct. Very, very simple. Here R double prime has attacked, forms a bond. Then it is OR prime. Now have a look. It will form a pi bond once again. Why? Because this is a good leaving group. In this case, there was no good leaving group. That's why in this case, there was no good leaving group. That's why it has not formed a pi bond. It undergoes hydrolysis. Here, it first forms a pi bond. Then what will happen? What will happen, my dear lovely students? This R prime, this O having a negative charge and this MgX, they will be lost. Now, what will be the result of this? It will be RC double bond O and then this will be R double prime. What is this R double prime? This means that is that alkyl which came from, say Grignard's reagent. Now, another mole of Grignard reagent, another mole of Grignard reagent can react. Another mole of this Grignard reagent can react in presence of dry ether. Once again, it will act as a nucleophile. It will attack this and it will result in the formation of RCO minus MgX with a positive charge, then R double prime. Here it will be once again a R double prime, but it will not form now a pi bond as there is no good leaving group. So hence hydrolysis will take place. Once hydrolysis takes place, it results in the formation of an alcohol like this. It will result in the formation of an alcohol like this. Simple trick is that remove OR and C double bond O is converted to C single bond OH, then give 2R of Grignard reagent from, say 2 R's from Grignard reagent to this carbon. So this is an alcohol. Now remember, if this R is H, that means formic ester. That means if it is formic ester, then we get secondary alcohol. But if this is not H, that means if it is not formic acid, we will get tertiary alcohol during this reaction. After this, we have another reaction, that is Tau's process. This is done in haloalkane haloarene. Done in haloalkane haloarene few minutes back. In arenes or haloalkane haloarene chapter, I will write down in haloarenes. Haloarenes. Have a look. This is already done. This is already done. Have a look. I will show you. My dear lovely students, I will show you. This is already done. This is already done. This is what we call Tau's process. This is Tau's process. This is already done. Few minutes before we have completed this reaction. We have completed this reaction few minutes before. So this is done. After that, we will be having preparation of phenol from what we call benzene sulfonic acid. Have a look, my dear lovely student. This is benzene sulfonic acid. That means this is an acid. On treatment with base, say for example NaOH, what will happen? Acid and base will form salt. Base will abstract H positive and will form salt of benzene sulfonic acid known as benzene sulfonate. Sodium benzene sulfonate will be obtained. But this upon treatment with NaOH. Suppose twice NaOH, I will write down over here. So it will form Na2SO3. It will lose Na2SO3 and it will form sodium phenoxide first at high temperature. Now, after that, this will undergo acidification. This will undergo acidification and it will result in the formation of phenol. Very, very simple reaction. Very, very simple reactions. Now, after that, from benzene diazonium salts, very simple, because we know benzene diazonium salt is stable only up to 0 to 5 degrees Celsius. That means up to 5 degrees Celsius. But if this is treated with water and warm, that means greater than 5 degrees Celsius will be there. This bond will be broken and we will get phenol. We will get phenol and nitrogen gas will be evolved. So very, very simple reaction. After that, from isopropyl benzene, that means from cumene. Isopropyl benzene means cumene. Very important reaction. Have a look. This is isopropyl benzene. This is isopropyl benzene. This can be prepared from benzene by Friedel-Crafts reaction. Now, if it is oxidized, if oxidation takes place at a temperature of 368 to 408 Kelvin, remember, we will get cumene hydroperoxide. We will get cumene hydroperoxide. That means O and O linkage is incorporated between C and H. This is known as cumene hydroperoxide. Cumene hydroperoxide will be obtained. Cumene hydroperoxide will be obtained. After that, if this is treated, I'm sorry, give me a second. If this is treated with dilute H2SO4, I mean say acidification, at a temperature of 323 to 363 Kelvin, what will happen? Just break this bond and break this bond. This OH will form a bond with this. That means we will get phenol. That means we will get phenol. And this O and C form double bond. That means we will get acetone like this. So acetone and phenol is obtained here. Acetone and phenol is obtained here. I hope this is clear. After that, we will be having chemical reactions of alcohol. Have a look. During this, chemical reactions, alcohol and phenol can act as what we call nucleophiles. If alcohol acts as a nucleophile, it will attack electron deficient site, and then oxygen is having a positive charge, then it will lose H positive and it will form a product. But as electrophile, only alcohol can act as electrophile, because when alcohol acts as electrophile, it acts as electrophile in protonated state. First it gets protonated, and after that nucleophile attacks electron deficient site and this water will be lost. That means C and O bond will be cleaved, but phenol do not show this reaction, because in case of phenol, CO bond is difficult to break because that bond is strong due to partial double bond character as a result of resonance. After that, we will be having few reactions. First, we will be having reactions involving OH bond cleavage of, alcohols and phenols. So let me show alcohol, phenols you can do your own, or let me show both. Now have a look. This is alcohol, this is phenol. When treated with active metal, say for example sodium, what will happen? Hydrogen gas will be evolved, remember that, and hydrogen gas will be evolved. That means this OH bond will be broken, H positive will be lost, then it will gain electron from this, becomes hydrogen atom, then it will combine with another hydrogen atom. In nutshell, hydrogen gas will be obtained. But to balance the reaction, I will write down half of H2, or I will simply write down this twice and then hydrogen gas will be evolved. Similarly over here, similar type of reaction is this. During both the reactions, whenever alcohol or phenol reacts with active metal, hydrogen gas is evolved, remember that, and alkoxide or phenoxide of that metal is obtained with which it has reacted. Now, so here it will result in the formation of sodium alkoxide, and here it results in the formation of sodium phenoxide. If we take potassium, then potassium alkoxide, potassium phenoxide, magnesium alkoxide, magnesium phenoxide, aluminium alkoxide, aluminium phenoxide. So this is the reaction. But remember, one, hydrogen gas is evolved, and alkoxide of metal or phenoxide of metal is obtained depending upon which metal is basically to which metal this alcohol or phenol is reacted. After that, esterification. Remember, whether it is aromatic, whether it is aliphatic, whether it is alcohol or phenol, whether it is phenol or alcohol, what we have to do is remember forever. We simply treat it with carboxylic acid. Reaction takes place in presence of acidic medium, say for example H2SO4, HCl. Now, what will happen? From carboxylic acid, OH is lost, and from alcohol or phenol, H is lost. In nutshell, instead of H of alcohol or phenol, we will introduce COR, means acyl. That means we will do acylation reaction. We will do acylation of either alcohol or phenol. So it will result in the formation of this one. Have a look. This is RCOOR or RCOOAR. That means ester is formed. So as ester is formed, this reaction is known as esterification reaction. So this is when alcohol or phenol is treated with ester. This is one. Another esterification is like this. If it is treated with acid chloride or acyl chloride, now what will happen? Have a look. Here H is replaced by COR. Once again, same type of reaction. So we will get OCOR. Once again, an ester is obtained. ester is obtained, here water. But remember, here you have to remember that this water contains oxygen from, say carboxylic acid, or this ester contains oxygen from alcohol. So remember that. Okay. So here HCl will be obtained. Bus. That acid, that is an acid that will, say convert reaction back. That's why we use pyridine, because this base will neutralize that acid. Similarly, if we use alcohol or phenol, we can use anhydride as well. RCO, O, C double bond, O and R. Now, instead of this H, acyl group is introduced. That means these reactions are basically acylation reactions. These are actually acylation reactions. So once again, ester is obtained. And at the very same time, carboxylic acid is obtained over here. So this is acylation of alcohol or phenol, acylation of alcohol and phenol, acylation of alcohol or phenol. But as esters are formed, hence this is also known as esterification reaction. After that, reaction of alcohol or phenol with Grignard's reagent. Have a look. This is Grignard reagent. This is having negative part, this is having positive part. When this is treated with alcohol, in alcohol this is negative part, this is positive part. And in phenol, this is negative part and this is positive part. What will happen? This Grignard's reagent, negative part of Grignard reagent will act as base and these will act as acid. So normal acid base reaction will take place and alkane will be obtained. Here, this Mg X is attached to this OR prime now. Here it will be attached to OPH. And these types of reactions are known as Zarivatanov reaction. What is Zarivatanov reaction? We know that. What is Zarivatanov reaction? We know that. What is Zarivatanov? Reaction of Grignard reagent with any acidic hydrogen containing compound resulting in the formation of alkane. After that, we will be having reactions involving cleavage of carbon-oxygen bond. Reaction with HX already done in haloalkane. Few minutes before, or we can say 1 hour before. Reaction done in haloalkane. Once again, reaction done in haloalkane. I will show you. This is done in haloalkane. Then this is also done in haloalkane. After that, my dear lovely student, this is also done in haloalkane. Let me show you. Have a look. This is reaction of alcohol with HX already done. Reaction with PCl5 done, with PCl3 or PX3 done, with SOCl2 done. So we have already done these types of reactions in haloalkane. Now, after that, we will be having other reactions, like we will be having dehydration of alcohol. Have a look. If you are having alcohol like this, a monohydric alcohol like this, if it is treated with acid, say for example H2SO4 or what we call H3PO4, at a temperature of 443 Kelvin, intramolecular dehydration will take place. That means it will result in the formation of this. But this is primary alcohol. If secondary alcohol is treated, we will treat it with, let us suppose, 85% H3PO4 or H2SO4 and at slightly lower temperature, so I will say less than 443 Kelvin temperature, then what will happen? It will result in the formation of an alkene. That means once again intramolecular dehydration reaction will take place. Similarly, if we take now tertiary alcohol, what will happen? Only 20% of H3PO4. That means drastic, reactions will be, faster. If this is having R1, R2, R3, R3 will be very, faster. So this reaction takes place approximately lesser than this. That means 368, approximately 368 Kelvin. It's not necessary that temperature is this, but I have shown this so that you can understand that this reaction takes place at much higher temperature and this reaction takes place at lower temperature. So what will happen over here? Once again, an intramolecular dehydration reaction takes place and it will result in the formation of, alkene. But what I mean to say over here is, why I have shown, different temperature over here, because I want to make you understand that whenever reaction goes from primary to secondary to tertiary, that means reactivity order increases. And remember, reactivity among alcohols depends on, actually, it is directly proportional to stability of carbocation. That means during this reaction, actually, carbocation formation takes place. How? Have a look. So it is very important that you must know which alcohol can form carbocation and which alcohol can form, much more stable carbocation. We know when OH is removed, it forms more stable carbocation as compared to this, That's why reaction in case of tertiary will be faster. So that's why reactivity order among 3 degree, 2 degree, 1 degree will be 3 degree, 2 degree and 1 degree. That will be reactivity order among 3 degree, 2 degree and 1 degree alcohols. I hope this is clear. Now, have a look how this reaction actually takes place. Let me show you an example of a tertiary alcohol. So among alcohols, it is tertiary alcohol which reacts much faster as compared to secondary, which reacts much faster as compared to primary. Now have a look. First, protonation of alcohol takes place. So that it becomes a very good leaving group. Here, what will happen? It becomes a good leaving group and it will leave. It will leave in the form of water and it will result in the formation of a carbocation. Can I write carbocation like this? Can I write CH3 as CH2H? So this is the carbocation. So this is the rate determining step of the reaction. So any alcohol which can form more stable carbocation can, show this reaction much faster. After this, what will happen? First, protonation, then loss of water, and lastly, deprotonation. That means this will be lost in this form. Deprotonation. Now, deprotonation takes place and alkene formation takes place. So, this is the mechanism of the reaction. This is very simple reaction. But reaction takes place as this is an elimination reaction, and that elimination which takes place via formation of carbocation, that means this is an even reaction. And remember, elimination reactions are favored at high temperature. You know that. That's why we have to take high temperature over here. After that, oxidation of alcohol. Have a look, my dear lovely student. This is an alcohol. Have a look. What we have to do is, during oxidation, we have to break this bond. That means we have to break, bond of OH bond of functional group, and we have to break alpha carbon and hydrogen. That means hydrogen attached to alpha carbon, that bond. Then after that, we have to remove hydrogen. Removal of hydrogen is known as oxidation. So it will result in the formation of C double bond O then. That means it will result in the formation of this one. Now, so this is basically the way with the help of which you have to do oxidation. But you know, here hydrogen can be off. Here, at least you need one alpha hydrogen, and you know one alpha hydrogen is present either in what we call primary alcohol or in secondary alcohol. That means we basically can oxidize easily primary alcohol or secondary alcohol. Tertiary alcohols are not generally oxidized easily. Now, have a look. Now, if you are having a primary alcohol, listen carefully. If you are having a primary alcohol and you want to oxidize it by using strong oxidizing agents, remember, I will write down over here. Let me write down over here. Strong oxidizing agents which we use generally in organic chemistry is number 1, KMnO4. either neutral or alkaline, that means in presence of base, say for example KMnO4 OH minus, or acidic, say for example KMnO4 H positive. Number one is this. Number second, you have to remember is K2Cr2O7, that means potassium dichromate in acidic medium, say for example H positive. Number third, you have to remember is that is CrO3 aqueous, which means you can say it is equal to CrO3 plus H2O. That means H2CrO4. This is known as chromic acid. Number 4, CrO3 plus H2SO4. This is known as Jones reagent. Jones reagent. Remember. Number 5, you have to remember this. KMnO4, hot. K2Cr2O7, hot. Whenever you saw these types of oxidizing agents, they are what we call strong oxidizing agents. So you can use any strong oxidizing agent. What we have to do is we have to break this bond and one bond and one bond at alpha position. Now what will happen? It will result in the formation of an aldehyde like this. Because this is CH3CHO, but this aldehyde is not obtained. Once this is formed, as oxidizing agent is strong oxidizing agent, it will convert. Strong oxidizing agent will convert this CHO into COH. That means they will result in the formation of a carboxylic acid. So remember, primary alcohol upon oxidation by using strong oxidizing agent gives carboxylic acid having same number of carbon atoms. Then, if you are having a secondary alcohol, have a look. If you are having a secondary alcohol like this, what is the trick? You have to break this one and you have to break alpha carbon and alpha hydrogen bond. This is secondary alcohol. Now, what will happen? Using strong oxidizing agents, it will result in the formation of ketone and reaction will stop. Now, tell me, this gives carboxylic acid, it gives ketone. So, different products are obtained. Hence, we can distinguish primary alcohol and secondary alcohol on the basis of products by using strong oxidizing agents. Now, remember, here no reaction will take place until and unless drastic conditions are used. That means secondary alcohol will give ketone and reaction will stop, but under drastic conditions only, ketones can undergo further oxidation. Otherwise, there will be no oxidation at all. Can undergo further oxidation. Now, suppose our ketone is this one. This is symmetrical ketone. And this is an unsymmetrical ketone. So ketone can be symmetrical, ketone can be unsymmetrical. Listen carefully. If drastic conditions are there, that means if strong oxidizing agents are there and under drastic conditions we want to oxidize, in presence of strong oxidizing agents, then what will happen? You have to break one alkyl and carbonyl bond, either this one or this one, then because this is symmetrical. Then this results in the formation of one carbon fragment. This results in the formation of two carbon fragment. So this can form acid, this can form acid. So it will form two carbon acid and it will finally form one carbon acid. But one carbon acid is methanoic acid. Whenever you have methanoic acid in presence of strong oxidizing agents, it always gives us carbon dioxide and water. That means it is further oxidized. That means the product of this reaction is CH3COH and CO2 water, because this has been converted to carbon dioxide and water. But if you have unsymmetrical ketone, then major product generally forms according to Popoff's rule. What is Popoff's rule? Popoff's rule says that in case of unsymmetrical ketone, cleavage is done, because this is cleavage, breaking a bond. Cleavage is done in such a way so that smaller alkyl group among these stays with C double bond O. Smaller is this one, it stays with C double bond O. That means you have to break C and larger alkyl bond. That means larger alkyl and C double bond O bond has to be broken, because this smaller has to be stayed with this. That means 2 carbon fragment, 2 carbon fragment. That means 2 carbon fragment means 2 carbon acid will be obtained here, 2 carbon acid will be obtained finally here. So this will be the product. But this takes place only and only under drastic conditions. Next point is tertiary alcohols. Tertiary alcohols. Let me write down directly tertiary alcohols. Tertiary alcohols in presence of strong oxidizing agents, no oxidation, but my dear students, if tertiary alcohol, remember, normally conditions, it cannot show oxidation, but if tertiary alcohol is first treated with acid, that means in acidic medium, what will happen first? You know, alcohol in acidic medium will simply lose this water molecule and finally it will be dehydration. That means from alpha position, OH will be lost, from beta position, H will be lost. That means first it will result in the formation of an alkene. Now, if this alkene is treated with strong oxidizing agent, directly we cannot oxidize it, but indirectly we can oxidize it, and that too under drastic conditions. What will happen? Now this bond will be broken, and this carbon double bond, which contains hydrogen, 2 hydrogens, will be converted to carbon dioxide and water. So this will result in the formation of carbon dioxide and water. And this, which is not having any hydrogen, will result in the formation of ketone. Similarly, if you are having this type of alcohol, CH3CH2, CCH3, and then CH3, and then OH, and if it is treated with H positive, now once again water will be lost, alpha will lose OH, and from beta H will be lost. But there are 2 types of beta, one containing 3 hydrogens, another containing 2 hydrogens. This is having lesser number of hydrogens, so poor hydrogen, it will form ZZ product. Major product will be this one, CH3CH double bond C, CH3 and CH3. This will be the major product. Now this, under drastic condition in presence of strong oxidizing agents, what will happen? This bond will be broken. This carbon contains 1 H. This CH is converted to COH and CH3 is there, so it will result in the formation of CH3COH. Plus this will form a ketone. That means it will result in the formation of this. So in this way we can oxidize alcohols, but generally it's primary alcohol and secondary alcohol which got oxidized. Tertiary does not undergo oxidation because of absence of alpha hydrogen, but it can undergo oxidation, but first in acidic medium to convert it into alkene, and after that, otherwise it will not. After that we can convert, my dear lovely students, we can convert primary alcohol and secondary alcohol. We can convert primary alcohol and secondary alcohol to, this bond will be broken, this bond will be broken, similarly this bond will be broken, this bond will be broken to aldehyde, and this to ketone, if we use mild oxidizing agent, and then reaction will stop. Otherwise, by using strong oxidizing agent, it can form acid, but by using mild oxidizing agent, it forms aldehyde. And By using strong as well as a mild oxidizing agent, secondary alcohol give ketone, but under drastic conditions, that ketone in presence of strong oxidizing agent can further oxidize, but here it cannot further oxidize. Tertiary alcohol cannot show this reaction. Tertiary alcohol do not oxidize over here as well. Mild oxidizing agents, no reaction, no oxidation. Now the question is, what are the mild oxidizing agents? Let me write down that over here. Whenever you saw these types of oxidizing agents, say for example, first is Serret's reagent. Serret's reagent, this is first one. Remember, it is CrO3 and I mean to say twice C5H5N. That means it is chromium trioxide and pyridine complex, but solvent here is pyridine. That means C5H5N is the solvent as well. Then we have Colin's reagent, second one. Colin's reagent. Colin's reagent and Serret's reagent, same CrO3, 1:2 complex of CrO3 and pyridine. But the only difference is here solvent is CH2Cl2. Third one is Corey's reagent. Corey's reagent, or my dear lovely students, pyridinium chlorochromate. You can say pyridinium chlorochromate, shortly PCC. Its formula is CrO3 basically, and pyridine and HCl in the ratio of 1:1:1, or you can write down that in this fashion. C5NH positive, then ClCrO3 having a negative charge. You can write down like this. Next is pyridinium dichromate. Pyridinium dichromate. We write that in this form, PDC, and that is like this, C5H5NH with a positive charge, that's why whole twice, and then Cr2O7 having two negative charges. This is pyridinium dichromate, or CrO3 anhydrous. But if it is aqueous, then it is strong oxidizing agent. Anhydrous, then it is, I mean say, weak, mild oxidizing agent. One more mild oxidizing agent is there, that is MnO2. What is its function? Its function is only, it oxidizes, remember, it oxidizes what? Have a look. It oxidizes primary allylic or primary benzylic alcohols. Allylic or primary benzylic. Similarly, primary, secondary, but allylic and benzylic alcohols, not other alcohols at all. Now, so specifically, this can be used specifically for conversion of primary allylic and primary benzylic. So this is primary allylic, secondary allylic, primary benzylic, secondary benzylic. So MnO2, what will happen over here? H from this and H from alpha. Alpha is this one, alpha is this one, alpha is this one. So it will result in the formation of this. It will result in the formation of this. So here it will be a double bond. Similarly, it will result in the formation of this one. Benzaldehyde over here and acetophenone over here. So this is what we call about oxidation of this. After that, action of hot copper on alcohols. Once again a very simple reaction. Once again, same trick. You can use same trick in case of primary alcohol and secondary alcohol. Once again, you can use same trick in primary alcohol and secondary alcohol. What was the trick? Have a look. This is primary alcohol, this is secondary alcohol, and this is tertiary alcohol. Let me write down tertiary like this, because we have to remove hydrogen from beta position. That's why I write, a value of R here. Here and here, dehydrogenation takes place if it is treated with hot copper. That means dehydrogenation in first two cases. That means remove hydrogen and hydrogen in first two cases, and you have to remove water. That means dehydration in third case. So you have to break this bond, you have to break this bond and this bond. Here you have to break alpha bond, and let me show beta bond, beta carbon hydrogen bond. Now, what will be the product over here? Product here will be aldehyde, here it will be ketone, here it will be an alkene. It will be an alkene. I hope this is clear. After that, my dear lovely students, it is reactions of phenol, and that too electrophilic substitution reaction. First, halogenation. You remember this is very important reaction. Whenever you are having phenol and its halogenation takes place, it is solvent dependent. Suppose it's Br2 in CS2. Then we will get product where obviously you know this is ortho and para directing group. So halogen will come to ortho position and to para position. That means normal products monohalogenation, monobromination will take place, in which para 1 will be the major and this will be the minor product. So normal reaction takes place. So this is major. Normal monohalogenation or monobromination takes place. But whenever this phenol is treated with bromine water, when it is treated with bromine water, that means water is a solvent over here. What will this water do? It will simply ionize this one. It will form phenoxide ion. That means instead of phenol, it will become O minus. And O minus will donate more electron towards ring, and it will activate ring or increase electron density of ring much more as compared to phenol. That's why electrophile goes to, as it has increased electron density of the ring, that's why electrophile goes to 2, that means ortho, 4, that means para, and another ortho, that means 6 position. That is why 2,4,6 tribromophenol is obtained over here. That means here tribromination takes place or polybromination takes place. And this gives a white precipitate. Remember, my dear student, we can distinguish with the help of this reaction, we can distinguish phenol from alcohol, because alcohol do not show white precipitate, do not show this reaction. Phenol gives white precipitate, hence we can distinguish alcohols and phenols with the help of this reaction. After that, we will be having sulfonation. Remember. When phenol is treated with H2SO4, if it is treated with H2SO4, what you have to remember is very simple. SO3H will be introduced, H2SO4. When it is treated with H2SO4, SO3H, that means sulfonation, takes place at ortho as well as para position. But remember, this ortho product is having low activation energy. It's having low activation energy. That means it can be formed at low temperature. So this is kinetically controlled product. But this product is having high activation energy. That means this para product is having high activation energy. It cannot be formed. It cannot be formed at low temperature. That is why at low temperature, say for example 298 Kelvin, this will be formed. This will be the major product. But this is formed at high temperature. And remember, sulfonation is actually a what we call reversible reaction. That is why as this is formed, this is having activation energy is high, but this is more stable because of less repulsion as compared to this. This is more stable. That means this is thermodynamically controlled product. Now listen carefully. If we increase temperature, this can be formed, both can be formed, but it preferred to form this. Why? Because this is more stable, as they are in equilibrium with respect to each other. That is why, my dear lovely student, at high temperature it prefers to go from this place to this place. That means this will be the major product at high temperature, this will be the major product at low temperature. After that, we will be having nitration, and we know this phenol can undergo nitration. This phenol can undergo nitration by using dilute HNO3 as well as concentrated HNO3. By using dilute HNO3, orthonitrophenol and paranitrophenol will be the products. But here ortho will be major because of chelation or intramolecular hydrogen bonding. This is major and this is minor. But if we use concentrated HNO3, or we use concentrated HNO3 plus concentrated H2SO4, here product will be simply picric acid. That means 2,4,6 trinitrophenol. That means here trinitration will take place. Trinitration will take place because here concentration of nitronium ion will be more, and second, we know this will increase basically the electron density of the ring, as well as nitronium ion, say electrophile, will be present in much more concentration. That's why polynitration will take place, as well as this HNO3 acts as an oxidizing agent. It acts as an oxidizing agent. It can form benzoquinone, that means oxidation product, as well as few TARI products will be also obtained. That clearly indicates if these products are also obtained, that means percentage of this product will be less. That means it is obtained but in low yield. It is obtained in low yield. If we want to increase its yield, then we have to, this reaction will be taken place like this. That means indirectly we have to convert this into this. How? Have a look. Then first of all, we have to treat this with say sulfuric acid. Suppose I will treat it with sulfuric acid. Nowadays what we do is we take say this with sulfuric acid, and we form first of all phenol 2,4 disulfonic acid first, and then we treat it with HNO3. Now we know HNO3 is an oxidizing agent, but in this reaction, during this reaction, what will happen? It will first replace SO3H, as well as it helps in nitration of these positions. That is why ring oxidation does not take place. Because of that, ring oxidation does not take place. Because of that, we will get this 2,4,6 trinitrophenol, say picric acid, but here picric acid will be present in high yield. Picric acid will be present in high yield. Why? Here ring oxidation has not been taken place, because here we have already introduced electron withdrawing group to the benzene ring. Because of that, electron density of benzene ring has been decreased. Here electron density of benzene ring was very high, due to which it undergoes oxidation as well. Because we know oxidation means loss of electron, and loss of electron can be taken place easily if electron density is more. Now, after that, we have Kolb's reaction. We have Kolbe's reaction or Kolb's reaction, whatever. Now, whenever you are having phenol and this is treated with NaOH. If phenol is treated with NaOH, my dear lovely students, what will happen? First of all, it will result in the formation of a sodium salt of, say this phenol. This on treatment with carbon dioxide, and carbon dioxide here acts as an electrophile. Now, number second, followed by acidification, it results in the formation of salicylic acid. Orthohydroxybenzoic acid as the major product. Otherwise, minor product can be what we call parahydroxybenzoic acid as well. But it has few applications. Say for example, if we are having this salicylic acid, and if this salicylic acid is treated with, either acid chloride or acetic anhydride, or say acetyl chloride, you can use anything. Now, what will happen? It will simply undergo acetylation. That means instead of H, this COCH3 will come. It will undergo acetylation simply, and after acetylation, it will result in the formation of acetyl salicylic acid. This is acetyl, and overall it was salicylic acid. So I can say this is acetyl salicylic acid. Its another name is 2-acetoxy or orthoacetoxy benzoic acid. And that is commonly known as aspirin. And this aspirin can be used as an analgesic, say pain reliever, or antipyretic or febrifuge. This antipyretic or febrifuge is simply, say that which brings down the temperature during fever. So this is one application. Another application of this is this salicylic acid on treatment with, say for example, C6H5OH, I mean say phenol, it can undergo dehydration in presence of, say for example, POCl3, water will be lost, phenol H and OH of this, then it will result in the formation of phenyl salicylate. It will result in the formation of phenyl salicylate. Phenyl salicylate. This phenyl salicylate is commonly known as Haloal. It's commonly known as Haloal, and it is used as an intestinal antiseptic. It's used as an intestinal antiseptic. Remember this. Remember this. After that, we will be having its third application like this, that whenever this is treated with, the salicylic acid is treated with, I mean say methanol, methyl alcohol. Once again, it undergoes dehydration in presence of, say for example, H2SO4, concentrated H2SO4. Water will be lost, and it will give us methyl salicylate. Methyl salicylate. And this methyl salicylate is basically the major constituent, chief constituent of what we call oil of wintergreen. That's why you can call this as oil of wintergreen. And it can be used as a flavoring agent in perfumery, in perfumes, वगैरह, in perfumery. After that, we will be having a very important reaction, that is Raymer-Tiemann reaction or Raymer-Tiemann reaction. Now, it is reaction of phenol with chloroform at a temperature of, say for example, I mean say 340 Kelvin and base, followed by, or let me write down first, it results in the formation of this intermediate, that is ONA and then CHCl2. This upon treatment with, I mean to say water, it results in the formation of ONA and CHO, followed by acidification. It results in the formation of orthohydroxybenzaldehyde, commonly known as salicylaldehyde, as major product. So salicylaldehyde here is the major product. But remember, electrophile of this reaction is dichlorocarbene. Dichlorocarbene is the electrophile of the reaction, and in coal-base reaction, electrophile was carbon dioxide. So this is an intermediate of the reaction. This is the intermediate which is formed over here, and this is an electrophile of this reaction. And remember one more thing. If CCl4 is used instead of CHCl3, then major product will be salicylic acid instead of salicylaldehyde. That means there parahydroxybenzaldehyde instead of this orthohydroxybenzaldehyde, acid will be the major product. After that, we will be having coupling reaction. This is simple reaction. This is actually this one. Benzene diazonium chloride undergoes electrophilic substitution reaction with phenol at para position. It undergoes electrophilic substitution reaction with phenol at para position of the phenol. And reaction takes place in basic medium. Then what will happen over here? This electrophile will be introduced to para position of the phenol. This electrophile, this benzene diazonium ion, acts as an electrophile, and it will be introduced to phenol at para position, and we will get 4-hydroxyazobenzene. 4-hydroxyazobenzene. Sometimes phenol does not have any para hydrogen. There will be some group. Then at that time, join this N at ortho position. Then coupling takes place at ortho position. That means at that time, electrophilic substitution takes place at ortho position. Okay. Now, listen carefully, as this is electrophilic substitution reaction. So, more electron rich is this, more will be the donation of its electron towards this, and whenever it's more electron rich, electrophile will prefer to go there. That's why in case of aniline, reaction will be much faster as compared to phenol. So, this is an dye, azo dye, and its color is orange. So, we can say this is an orange dye. And with the help of which we can distinguish phenol from alcohol, because alcohol does not show this reaction, phenol shows. After that, condensation. Condensation with phenol. But condensation with what? Condensation with phthalic anhydride. I mean, say this one. This is phthalic anhydride. Now, condensation of phenol. This condensation takes place at para position of the phenol. At para position of the phenol. Let me write down 2 moles of phenol so that reaction will be balanced. What will happen over here? Water will be lost. Simply water will be lost because here reaction takes place in presence of H2SO4, and this concentrated H2SO4 acts as a dehydrating agent, and it will result in the formation of this one. It will result in the formation of this one. Have a look. Have a look. This is known as phenolphthalein, which is used as an indicator during acid-base titration. So this is phenolphthalein, and it can be used as an indicator during acid-base titration. After that, we will be having another reaction, that is reaction with ferric chloride. Suppose this is phenol. C6H5OH is phenol. We will be having FeCl3. It is Cl minus, Cl minus, Cl minus. Cl minus will accept H positive from this. After that, second will be accepted by second, Cl minus, third will by third. That means we will take 3 times Fe, this phenol. Then it will result in the formation of C6H5O minus, but it will be thrice. And then it will be, say, attracted towards Fe tripositive. So this is known as ferric phenoxide. This is ferric phenoxide, and its color is generally violet. Its color is generally violet. It's violet in color generally. Now, with the help of this color, we can distinguish alcohol and phenol. So we can distinguish phenol from alcohol with the help of this test. This will be known as ferric chloride test. After that, reaction with zinc, dust. Whenever phenol is treated with zinc dust, it results in the formation of benzene. After that, my dear lovely students, oxidation of phenol, very, very simple. Whenever phenol is oxidized, oxidation takes place by using strong oxidizing agents. Say for example, Na2, Cr2O7, H2SO4, sodium dichromate or potassium dichromate, or you can say chromic acid. Then what will happen? Parabenzoquinone or benzoquinone will be obtained. Remember this as well. After that, distinction between this. We have done this oxidation. We have done action of hot copper. We have done Lucas test. This is not Lucas test. It is Lucas test. AS. It is A. It's A over here. Then lastly, it is Victor Meyer's test. What you have to remember is that if we have an alcohol in a test tube and we don't know what is, say, the alcohol in test tube, which type of alcohol is present in test tube, so we can distinguish alcohols. That means with the help of this Victor Meyer test, we can distinguish 1 degree, 2 degree and 3 degree alcohols. How? First, we will add iodine in presence of red phosphorus. Then we will add second thing, that is AgNO2. Third, we will add HNO2, nitrous acid, and fourthly, we will add NaOH. Then we will check which color will be obtained. If blood coloration takes place, blood red coloration takes place, remember it is a 1 degree alcohol at that time. If blue coloration takes place, it is 2 degree alcohol. If it is colorless, then at that time it is 3 degree alcohol. That's why as red, blue and colorless is there, that's why this is known as red, blue, colorless test as well. Okay. After that, we will be having distinguishing tests between alcohols and this. Orange dye test, coupling reaction has done, ferric chloride test done, bromine water test done, all are shown by phenols. Alcohol does not show these. But litmus test, remember, phenol turns blue litmus to red. As phenol is more acidic, turns blue litmus to red, because more acidic species turn blue litmus to red, turns blue litmus to red. Alcohol does not affect blue litmus at all. So with the help of these, we can distinguish alcohols and phenols. After that, Lieberman's nitroso test. Have a look. This is what we call a phenol. Phenol on treatment with NaNO2 H2SO4. That means you can say HNO2. What will happen over here? Nitroso group will be introduced at para position of phenol. That means it will result in the formation of this. Have a look. Para-nitrosophenol will be obtained. And this para-nitrosophenol can undergo hydrogen migration like this. And it can form this one. This is known as quinone oxime. This is known as quinone oxime. Now, this quinone oxime can react with phenol. It can react with phenol. Let me write down phenol like this. It can react with phenol once again. In presence of H2SO4, once again a dehydrating agent H2SO4 will act as a dehydrating agent. Water will be lost once again. And it will result in the formation of this. It will result in the formation of this one. It is double bond N, single bond, and then phenol. That means at para position, reaction takes place. This is known as indophenol. This is known as indophenol. After that, my dear students, if base is there, this base will abstract this H. That means water will be lost. OH will abstract this H. Water will be lost, and we will get sodium salt of indophenol. Its color is blue. Its color is blue. So this blue coloration only takes place if sodium salt of indophenol is formed. That means this reaction is shown by phenol, not by alcohol. So with the help of this, we can distinguish alcohol and phenol as well. After that, methods of preparation of ethers by dehydration of alcohol. Remember, if you are having an alcohol like primary alcohol, it undergoes, remember, it undergoes, let me write down, alcohol in excess. Whenever you are having an alcohol, it's not necessary that it is written twice. I have written it twice so that you will understand this. Whenever it is written there and temperature is 413 Kelvin, that means lesser temperature as compared to intramolecular dehydration when alkene was formed. So here intermolecular dehydration reaction will take place and we will get ether. And remember, rate of this reaction will be among alcohols, reactivity order will be simply reactivity order, because this reaction generally takes place via SN2, and reactivity order is 1 degree, 2 degree and 3 degree among alcohols. Remember this. After this, Williamson synthesis. What is Williamson synthesis? Oxide or reaction of phenoxide with alkyl halide. Say for example, alkyl halide. Let me erase this. I will show only alkoxide. You have to try phenoxide at home. You have to only replace this R by pH. That means by phenyl group. Similarly, if it is 1 degree alkyl halide, it's a normal SN2 reaction. What will happen? Normal SN2 reaction will take place. That means this alkoxide will act as a nucleophile. X minus will be lost. So simply it will be NaX which will be lost. NaX will be lost and we will get ether. Here we will get RO. Here we will get ROCH3. Here we will get ROCH2CH3. Normal SN2 reaction. And remember, as this is SN2, rate of SN2 is inversely proportional to steric crowding. It is inversely proportional to steric crowding. More steric crowding at alpha position. This alpha position is having only hydrogen. This alpha is having alkyl. That means rate of this reaction will be much more faster as compared to this. Similarly, whenever we talk about tertiary alkyl halide, remember, tertiary alkyl halide cannot show this reaction. tertiary alkyl halide do not show SN2 reaction. So no reaction, no Williamson synthesis, I mean to say. No Williamson synthesis. Remember this, very, very important point. So then what will happen over here? When you are having a tertiary alkyl halide, this will act at that time as base and it will remove hydrogen from beta position. It will remove hydrogen from beta position and a normal E2 reaction will take place. It will remove hydrogen from this and this will form an alkene, alcohol and NaX. I will show only this product. That means an alkene will be obtained at that time. Alkene will be obtained at that time. That means this cannot act as a nucleophile. It will act as a base at that time. Similarly, if you are having a reaction of alkoxide with secondary alkyl halide, remember my dear lovely students, it can act as a nucleophile. When it acts as a nucleophile, it will attack alpha position and X will leave. That means it will form like this. It will form CH3, then nucleophile will come, OR will come. This will be SN2 product. But at alpha, there will be two alkyl groups. That means it can feel steric crowding as nucleophile. That's why it can act also as base. It will abstract hydrogen from beta position. When it abstracts hydrogen from beta alpha will form double bond. That means it will form double bond like this. So this will be the E2 product. But by acting as base, there will be no repulsion. Hence, this will be the major product. This will be the minor product. Now tell me, among 1 degree, 2 degree and 3 degree alkyl halide, can I say 1 degree alkyl halide is better alkyl halide to form ether as compared to 2 degree, as compared to 3 degree. So reactivity order towards Williamson synthesis, I mean say SN2 reaction will be simply among alcohols, among alkyl halides will be 1 degree, 2 degree and after that it will be 3 degree. And remember, aryl halides do not show this reaction. Aryl halide do not show this reaction. Do not show this reaction. Do not show this reaction. Remember this, very, very important point. Remember this, aryl halides do not show this reaction. So tertiary alkyl halide do not show this reaction and as what we call Williamson synthesis, aryl halides do not show Williamson synthesis. After that, reaction of ether with HX. Have a look. Ether can be of two types. One is symmetrical. What you have to do is simple. Break one oxygen carbon bond. Which one? Because both are symmetrical. As this is symmetrical, both are identical. Anyone. Give H to this, give X to this. So what will be the product? ROH plus RX. But if you have an unsymmetrical ether, at that time, what will happen? What will happen if you have an unsymmetrical aliphatic ether? Because these are aliphatic ethers, open chain ethers, unsymmetrical ether. What we have to do is, listen carefully. What we have to do is, let me tell you what you have to do is, you have to check point number 1. If R is not equal to 3 degree and R prime is also not equal to 3 degree. That means neither this is 3 degree nor this is 3 degree in case of aliphatic unsymmetrical ether, then reaction proceeds via SN2 and X minus goes to smaller alkyl group, and number second point, if R is tertiary or R prime is tertiary or both are tertiary, then reaction proceeds reaction proceeds via SN1 and X minus goes to larger alkyl group. Larger alkyl group. What is meant by that? Have a look. Have a look. If you are having CH3O, CH2, CH3, no one is tertiary. If you are having this one, no one is tertiary. Have a look. If you are having this one, this is an aliphatic unsymmetrical ether in which one of the groups is tertiary. So when this is treated with HX, this is treated with HX, this is treated with HX, then what will happen? This will proceed via SN2, this will proceed via SN2, and this will proceed via SN1. What is meant by that? That means here X minus will go to this. That means this bond will break and H will go to this. Similarly, X minus goes to this, break this bond, give hydrogen to this. Here X minus goes to larger alkyl group, break this bond and give H to this. Have a look, have a look, have a look. Now, what will be the product? Product here will be CH3X and then CH3CH2OH. Here it will be CH3X and then CH3 and then here it will be OH. Here it will be CH3OH and here CH3 and here it will be what we call X. X goes to larger alkyl group at this time. So this was all about aliphatic unsymmetrical and aliphatic symmetrical ether. Now, if you are having aliphatic symmetrical or aliphatic unsymmetrical ether, and if HI or HX is taken in excess, then a very simple trick is there. Very simple trick is there. Very simple trick is there. Listen carefully. Listen carefully. I mean, say oxygen should be attached to sp3 hybridized carbons, sp3 hybridized carbons, single bonded carbons. Then break this, give X to this, H to this. Break this, give H to this, X to this. Break this, give X to this, H to this. Break this, give H to this, X to this. That means here Rx similar. That means twice Rx plus water. Here Rx and Rx, they are different. So here we will form Rx plus R prime X plus water. Very simple. Very simple. But if you are having an ether in which, listen carefully, if you are having an ether in which O is attached to that carbon which forms a double bond, whether it is carbon-carbon double bond of alkene or aromatic ring, then there will be no reaction. Remember, with HX, no reaction. No reaction. If you are having oxygen attached to aromatic ring directly on one side and on another side you have an alkyl group, say for example like this, then one of the products will be always, whether HX is taken in excess or not, one of the products will be always phenol. Because you cannot break this bond, as this bond is very strong bond because of partial double bond character as a result of resonance. That's why this bond cannot be broken, there will be no reaction. But here, this bond can be broken, this cannot be broken. That's why X goes to this. So remember, whenever oxygen is directly attached to benzene ring, directly, one of the products is phenol and another will be this alkyl halide. But if this is taken in excess, phenol remain as such. But if it's taken in excess, CH3X remain as such. That means there will be no, difference in the product. Now, if you are having O, which is not directly attached to ring, then if it is not directly attached to ring, then what will happen? Break this bond and give X to this, because it forms more stable carbocation. Form carbocation over here, benzyl carbocation, very stable. Give X minus to this and H to this, then product will be like this. Product will be like this. I hope this is clear. So this is done. This is, done. Now, after that, electrophilic substitution reactions of ether. This is ether And we know ether is electron donating. This is ortho-para directing group. Ortho-para directing group. So halogenation can take place at ortho and para. Nitration can take place at ortho and para. Friedel-Crafts alkylation or acylation can take place at ortho and para. Generally, it does not show sulfonation reaction. So I hope you can do this type of reaction at home easily. So let me give you such type of reaction as an assignment, because both can form Cl positive. Give Cl positive to ortho and para. That's it. After that, nitration. What will happen? Electrophile of this reaction will be NO2 positive. NO2 positive will go to ortho and para. Para 1 will be the major product. Then alkyl chloride AlCl3. R positive will be the electrophile. R positive will go to ortho and para. Simple. Then RCOCl AlCl3. This is the electrophile. This electrophile will go to either ortho and para, but para 1 will be the major product. So this was all about ethers. I hope this is clear till now. Let me know quickly. Can we say that with the help of this, revision of alcohol phenol ether is done? Let me know quickly. Can I say revision of alcohol phenol ether is done? Let me know quickly. Can we say what happened? Where is lag? But I'm seeing at the very same time I am checking my mobile as well. There is no problem at all. What are you saying? Okay. So we are done with alcohol, phenol and ether. We are done with alcohol, phenol and ether, my dear lovely students. My video is lagging. But I have mobile in front of me. I have, screen in front of me as well. Am I audible and visible? Is everything clear now? Okay, my voice was continuous but screen was not. Now, is my screen continuous now? Is it continuous now? Let me know quickly. Okay, now it's fine. Now. Okay. Maybe there may be some, technical glitch. I don't know that. Okay, so should we start? A very important chapter, aldehydes, ketones and carboxylic acids, from which most of the questions will be there in your NEET. So should we revise this quickly? After that, we will take 10 minutes break. And then we will do, amines. And if time permits, then we will go for few PYQs as well. Let me know quickly. Should we revise aldehydes, ketones, carboxylic acids quickly? Are you there? Let me know. Okay, so let's start. Let's get started without wasting time. As we have to finish, we have to revise each and everything. Now, methods of preparation of aldehydes and ketones by oxidation of alcohols done in alcohols. It is done in alcohols, my dear lovely students. After that, by dehydrogenation of alcohol, means action of hot copper on alcohol. Action of hot copper on 1 degree and 2 degree alcohol. It's already done. 1 degree alcohol undergoes dehydrogenation resulting in the formation of aldehyde. 2 degree alcohol this undergoes dehydrogenation and results in the formation of ketone done in alcohols. It is done in alcohols. After that, by hydration of alkyne means Koch-Arrows reaction. It is Koch-Arrows reaction. It is Koch-Arrows reaction. Let's start Koch-Arrows reaction. Have a look. It is simply a reaction of alkyne. It is simply a reaction of alkyne. It is simply a reaction of alkyne in which we add water. That means it is hydration simply of alkyne taking place in presence of H2SO4 dilute or HgSO4 at a temperature of 333 Kelvin. Now, water will be added across carbon-carbon double bond according to Markovnikov's rule. So we will get like this. We will get first an enol. This is an enol. Now this enol will undergo tautomerization as its keto form is more stable. So we will get this one, RC double bond O CH3. Now we will get either aldehyde or ketone depending upon the value of this R. If this R is H, we will get aldehyde. If this R is other than, say H, that means if it is alkyl or aryl, we will get ketone. So this is hydration of alkynes. After that, hydroboration oxidation of alkyne. Very simple. This is indirect hydration of alkyne. This is indirect hydration of alkyne. What are the reagents? Reagents are B2H6, THF, followed by, say H2O2, OH minus. So whenever you are having this, add water across carbon-carbon triple bond according to anti-Markovnikov's rule. That means you have to add water according to anti-Markovnikov rule like this. That means once again an enol is formed, and this enol forms much more stable keto. It forms this RCH2CHO. Is this clear? Is this clear? Let me know. Let me know quickly. Let me take my mobile in my hand and let me know quickly. Is this clear? Is this clear? Yes, exactly. At the rate of mystic, there will be, tautomerization. Yes. Is this clear till now? No, another R of lagging. No, but I can see myself. I can see there is no lagging at all. Is it clear? Is it clear now? Is it lagging still or not? Is it lagging? Is it lagging now? Is it lagging? Give me a moment. Give me a moment. Just a moment. Just a moment. Just a moment. Is it clear now? Is it clear now? Is it clear now? Now fine. Okay. I don't know. Actually, the speed of my internet is very high. It's more than 300 Mbps. I don't know what happened over here. Okay. Give me a second. Just I will check whether everything is okay or not. Okay. Okay. Now, is it okay now? Is it okay now? Should we start? Should we start? Should we start, as this is very, very important chapter, should we start? Should we start? Okay, this is clear. Now, after this, as this is what we call addition of water but anti-Markovnikov. Hydroboration means anti-Markovnikov. That means OH negative goes to that carbon-carbon triple bond which is having more number of hydrogens. After that, we will be having reductive ozonolysis of alkenes. We will be having reductive ozonolysis of alkenes. Very, very simple, my dear lovely students. This is alkene. When you have O3, whenever you have O3 and you have zinc water, what you have to do is just break this, give oxygen to this, give oxygen to this. Very simple. Very, very, very simple. Suppose if I give few examples to you, can you say me the product? Can you say me what will be the product? Can you say me the product of these reactions? Let me know in the chats quickly. Can you show me, can you say what will be the products of these reactions? As these are very, very simple reactions. You can form many examples. So what we have to do is simple. Just break this, give oxygen to this, give oxygen to this. That means we have to break it like this. Here it will be H. Here it will be, in nutshell, this will be CHO. This will be C double bond O and H. And this will be C double bond O and H. Like this. Break this, give double bond O to this, double bond O to this. That means it is twice HCHO. That means formaldehyde. Break this, give oxygen to this, oxygen to this. So they are very, very simple reactions. One is acetaldehyde, another is formaldehyde. What about this? Break this, give oxygen to both. Give oxygen to both these. Give oxygen to this, oxygen to this. That means it will result in the formation of this one. A very, very simple reaction. Is this clear? Is this clear? No need to waste time or ozonolysis. I know this is very, very important, but this is very easy. This is very easy. But remember one thing only. Remember one thing only in ozonolysis. That is, if products are given and you have to check the reactant, then form products in such a way that oxygen and oxygen come closer. Remove oxygen, form a double bond. You will get your reactant. You will get your reactant. After that, from acyl chloride, whether it is aliphatic, whether it is aromatic, hardly matters. What you have to do is, this is Rosenmund reduction. Simply, you have to treat it with H2. You have to treat it with H2 in presence of Rosenmund's catalyst. And Rosenmund's catalyst is palladium barium sulfate with small amounts of sulfur or quinoline. What you have to do is replace this Cl by H. You will get an aldehyde simply. You will get an aldehyde simply. No ketone formation takes place with the help of Rosenmund reduction. This is very, very, very simple, my dear lovely students. Am I clear? Am I clear till now? Am I clear till now? Am I clear till now? Now, you can use, no, this is not Lindlar's catalyst, this is Rosenmund catalyst. Lindlar's catalyst is PDCaCO3. You can use that also. You can use that also. But that is basically Lindlar's catalyst. At the rate of mistake, this is Rosenmund catalyst. Lindlar's catalyst is if it is PDCaCO3. Listen carefully. Okay. Now after that, we will be having another, that is from nitriles. Listen carefully. This is nitrile, means cyanide. Whenever you are having nitrile, Then on treatment with SnCl2HCl, this will act as a reducing agent and it will reduce this. How? Just break one pi bond, give H to this, break, say 1 pi bond and give H and H, you will get imine. First, you will get imine. This imine upon hydrolysis will result in the formation of, break this, give H to this, OH to this, give H to this, OH to this, and 2 OH at 1 carbon will lose water and it will result in the formation of aldehyde. This reaction is known as Stephen's reduction. After that, if you are having cyanide, you can use, instead of SnCl2HCl, you can use dibyl H as well. The function of dibyl H followed by hydrolysis is same. That means it will convert the cyanide to aldehyde group. That means we will get an aldehyde. So dibyl H followed by hydrolysis converts cyanide to aldehyde. It can convert cyanide to aldehyde, but remember, it cannot convert double bond to single bond. It will convert cyanide to aldehyde, but it will not reduce this double bond. So dibyl H followed by hydrolysis will result in the formation of CH3CH double bond CH, CH2, but CHO now. That means cyanide is reduced to aldehyde. It can also reduce, say for example like this, ester. It can also reduce ester. Dibyl H can also reduce ester to aldehyde. Diisobutyl aluminium hydride can reduce this ester to aldehyde. Remember. So remember the function. So it can reduce this to aldehyde. Now, am I clear till now? After that, we will be having another reaction, that is from aromatic hydrocarbons by oxidation of methyl benzene with chromyl chloride. Remember, my dear lovely students, whenever you are having methyl benzene and it is treated with CrO2Cl2, say chromyl chloride, in presence of CS2, say non-polar solvents, then it will first result in the formation of a chromium complex like this, CH, then it is OCr OHCl2 whole 2. It's a chromium complex. It's a brown complex formation taking place. It's a brown complex which will form first. You can write down this in this fashion as well if you want. It is like this. It is CH to which OCr OHCl OCr is attached. So this or this. After that, this undergoes hydrolysis. My dear lovely students, listen carefully. After hydrolysis, it will result in the formation of benzaldehyde. And this reaction is known as Ethers reaction. This reaction is known as Ethers oxidation or Ethers reaction. After that, this is Ethers reaction or Ethers oxidation. After that, we will be having another reaction, that is a reaction of toluene or methyl benzene with chromium trioxide in presence of acetic anhydride. That means CH3CO whole 2O. What will happen over here? It will result in the formation of CHOCOCH3, geminal diacetate. Geminal diacetate will be obtained. Which upon hydrolysis which upon hydrolysis, you can use H3O positive, you can use H2O, you can use H2OH positive. Now, it will result in the formation of benzaldehyde. Actually, first OH will be present over here instead of this. After that, OH will lose water molecule and it will result in the formation of benzaldehyde. Next reaction is by controlled chain chlorination followed by hydrolysis. That means when you are having toluene, this toluene on treatment with twice chlorine first undergoes, side chain halogenation, and it will result in the formation of CH, Cl and Cl, which upon hydrolysis will replace this Cl by OH, and after that 2 OH groups on same position will lose water molecule and will result in the formation of benzaldehyde. After that, Gattermann-Koch reaction. What is Gattermann-Koch reaction? It is reaction of benzene with COHCl in presence of AlCl3 and CuCl acting as a catalyst. Now, here, this is the electrophile of the reaction. This electrophile goes to the benzene ring, and in nutshell, electrophile on attack of benzene ring will result in the formation of benzaldehyde. That means this formyl group has been introduced. So we can say Gattermann-Koch reaction, Gattermann-Koch formylation reaction, or Gattermann-Koch aldehyde synthesis. After that, Gattermann formylation reaction or Gattermann aldehyde synthesis is this one. Benzene on treatment with HCN, HCl, and instead of CO it is HCN and AlCl3. Then what will be the electrophile over here? Electrophile will be simply like this. So first it will result in the formation of this one. This imine will be formed. This imine upon hydrolysis will result in the formation of, hydrolysis takes place in this fashion. HH from this has to be added to this and OH to this, and finally it will lose water molecule and it will result in the formation of once again a benzaldehyde. So this is what we call Gattermann formylation, because formyl group has been introduced or aldehyde group has been introduced. So Gattermann aldehyde synthesis or Gattermann formylation or Gattermann aldehyde synthesis. Then methods of preparation of ketones only. Now from acid chloride or acyl chloride, this is acyl chloride or acid chloride. Let me take 2 moles or 2 molecules of this acid chloride or acyl chloride, and it takes place, a reaction takes place with dialkyl cadmium. When reaction takes place with dialkyl cadmium, let me differentiate these R from this by putting a dash over here. Then it will result in the formation of CdCl2 will be lost, and we will get ketone RC double bond O R prime and RC double bond O R prime. So let me write down twice. So we will get ketone. From nitriles, that means from cyanides, when these nitriles are treated with Grignard's reagent RMGX. So to differentiate this from this, let me put over a dash over here. So this is partial negative, partial positive. Now in presence of dry ether, what will happen? This Grignard reagent will act as a nucleophile. Negative part of this nucleophile will attack this carbon, obviously electron deficient site, and it will result first in the formation of this adduct. Have a look. This adduct will be formed first. After that, my dear lovely students, here hydrolysis will take place, and after hydrolysis this bond will be broken and OH will be added to this, and we will get a ketone over here. We will get a ketone over here. So ketone is formed. But remember, if RCN, if HCN is used instead of RCN, then we get aldehydes. Then we get aldehyde instead of ketone. After that, from benzene by Friedel-Crafts reaction. So this is benzene, on treatment with acetyl chloride in presence of AlCl3, we will get acetophenone simply. That means acetylation, Friedel-Crafts acetylation will take place. And similarly, if we use acetylating agent as acetic anhydride in presence of AlCl3, then you can replace simply H of benzene by C double bond O CH3. That means once again an acetylation reaction is taking place over here. This will give CH3COH and this will give HCl as side product. Or you can use this benzene and on treatment with what we call phosgene or carbonyl chloride, reaction takes place in presence of AlCl3. Let me show you the trick like this. Remove this HNCl, remove this HNCl. So finally you will get benzophenone. You will get benzophenone as the product plus twice HCl. In this case, you will get either acetophenone, benzophenone. That means you will get ketones. After that, chemical reactions of aldehydes and ketones, nucleophilic addition reactions. Remember, it is aldehyde whose rate is faster. Aldehyde shows much more faster nucleophilic addition reaction as compared to ketones. So this is a reactivity order. This is reactivity order, my dear lovely students, towards nucleophilic addition reactions. Remember this. And among aldehydes, first it is formaldehyde, then it is aldehyde other than formaldehyde, then you can say aromatic aldehyde, then you can say ketone, say for example aliphatic ketone first, and then aromatic ketone like this, and after that you can say this aromatic ketone. This order is basically depending on two factors. One is electronic factor, another is steric factor. In case of ketones, steric repulsion will be more because more crowding is there. Two groups are there as compared to aldehydes. And second, these are much more electron donating groups are attached to C double bond O. Lesser will be the rate of nucleophilic addition. That means if this C double bond O of aldehyde or ketone is attached to electron withdrawing group, rate of nucleophilic addition reaction will be faster. And if C double bond O of aldehyde or ketone is attached to what we call electron donating groups, rate of nucleophilic addition will be slower. After that, we will be having few nucleophilic addition reactions. For example, we will be having this one, addition of HCN. Addition of HCN. What you have to do is simple. What you have to do is, this is very, very simple. Have a look. This is a reversible reaction. In simple way, you just put a positive and negative over here, positive and negative over here, give negative to positive, positive to negative, and convert double bond into single bond. So it will form cyanohydrin simply. This is known as cyanohydrin of either aldehyde or ketone, and this is a reversible reaction. After that, this is aldehyde or a ketone, remember. Then on treatment with, as this is a reversible reaction once again, on treatment with sodium hydrogen sulfite or sodium bisulfite, it is like this, OSO2 and H. This is having Na positive and OSO3H having a negative charge. So you can write down O minus SO2H like this. So here it is positive part, here it is negative part. It's very simple. Give positive to negative, negative to positive, and convert, double into single. So it will become O minus Na positive first. So this will become addition product. So this is what we call, this addition product is also known as adduct. So first adduct will be formed. After that there will be protonation. There will be simple proton transfer. Proton transfer takes place so as to form more stable product like this. Proton transfer will take place like this. Proton transfer will take place like this. OSO2 Na. because now this becomes more stable negative charge as it can be stabilized by resonance. But remember, aromatic ketones do not show this reaction. Aromatic ketones do not show this reaction. Do not show this reaction, as this is considered OSO2H minus or HSO3H, SO3H minus is considered bulky nucleophile. So aromatic ketones do not show this reaction. Among aliphatic ketones, less sterically crowded ketones. For example, methyl ketones show this reaction. So among aliphatic ketones, methyl ketones show this reaction. Remember this as well. After that, we will be having another reaction, that is addition of Grignard reagent. This is already done in alcohol. So let me write down done in alcohols. After that, we will be having another reaction, that is addition of alcohol. Have a look. This is an aldehyde. When this aldehyde reacts with monohydric alcohol, remember, monohydric alcohol is not a stronger nucleophile. That is why reaction takes place in acidic medium. Then what will happen? It will result first in the formation of this. Negative part goes to this one. Negative part of alcohol is OR and this becomes OH. That means first it will form hemiacetal. After that, another molecule of alcohol in presence of acid simply increases the rate of reaction. It catalyzes the rate of reaction and it results in the formation of dialkoxy compound obtained from aldehyde. That means acetal. And acetal formation takes place. Now, this reaction is a reversible reaction. You can write down. So, whenever aldehyde reacts with monohydric alcohol, it gives you an acetal if alcohol is taken in excess. If alcohol is not taken in excess, then hemiacetal will be obtained. But if you have an aldehyde or a ketone, say for example like this, and they will react with dihydric alcohol, say for example glycol, ethylene glycol, let us suppose ethylene glycol, what will happen? Simple water will be lost. And finally reaction takes place in presence of benzene and paratoluene sulfonic acid, say for example, and we will get cyclic acetal or cyclic ketal, depending upon reaction takes place from aldehyde or ketone. If reaction takes place from aldehyde, then we will get cyclic acetal, and if reaction takes place from ketone, then we will get cyclic ketal. Come on my dear lovely students, come on quickly. After that, nucleophilic addition reactions followed by elimination of water molecule. What you have to remember is that whenever we have, ammonia, whenever you have ammonia or derivative of ammonia, say for example like this G, value of G can be H, it can be NH2, it can be OH, it can be R, it can be NHCO, NH2, it can be NHPH, it can be NH, and then phenyl ring. To that phenyl ring, a nitro group should be attached at 2 or 4 positions. So it can be different values. So remember, they are basically poor nucleophiles. First of all, what will happen? This reaction generally takes place at a pH of 3.5, that means an acidic medium. First of all, this will attack at a nucleophile and it will result in the formation of this. It will be OH and it will be NH and then it will be G. First, nucleophilic addition takes place, and after that, After that, my dear lovely students, water will be lost. Water will be lost. So dehydration takes place, and finally we will get this one. We will get this one. So this reaction can be, you can remember this reaction by simple this way, that if you have ammonia or derivative of ammonia, you will get this one. And remember these values, these are very, very important. Remember this table. Question can be asked directly from this table. Question can be asked directly from this table. Question can be asked directly from this table. You can remember this table. You can remember this table. Have a look. You have to remember the value of G only. If value is H, put H over here, put H over here. Product and substrate you can form. But you have to remember this one, that whenever you use 2,4-DNP, 2,4-dinitrophenyl hydrazine, known as Brady's reagent, you will get 2,4-dinitrophenyl hydrazone that is having yellow, orange or red color. That means that coloration can distinguish aldehyde or ketone from rest of the compounds. And remember, this can be used as a 2,4-DNP test. Let me write down over here that this 2,4-DNP test is shown by, 2,4-DNP test is shown by, we know, 1. Aldehydes, number 2, ketones, and remember one more, that is formic acid, HCOOH, formic acid. Now remember this, please. Try to remember this, because question can be asked directly from this. After that, we have reduction of reduction of aldehydes and ketones to alcohols. It is done in methods of preparation of alcohols. Now after that, second is reduction to hydrocarbon. First, Clemmensen reduction. Let me show you. This is C double bond O. It can be aldehyde or it can be ketone. When it is treated with zinc amalgam in acidic medium, say for example HCl, what you have to do is convert C double bond O of aldehyde or ketone to CH2. That's it. But remember, this reaction is preferred only if aldehyde or ketone is not acid sensitive. If it is acid sensitive, then in acidic medium, this reaction cannot take place like this. Then this is not preferred. So this reaction is preferred if this aldehyde or ketone is not acid sensitive, because this medium is acidic. So it should not be acid sensitive. After that, another is Wolff-Kishner reduction. What is Wolff-Kishner reduction? Have a look. Whenever this is treated with NH2NH2, that means hydrazine, or you can write down N2H4, in presence of basic medium and at high temperature, you have to convert C double bond O of aldehyde or ketone to CH2, and N2 will be lost over here. But remember, this is preferred if aldehyde or ketone is not base sensitive, as this is base. If aldehyde or ketone is base sensitive, then this is better method. If aldehyde or ketone is base sensitive, then Clemmensen reduction is best method. If aldehyde or ketone is acid sensitive, then Wolff-Kishner reduction is better method. After that, if C double bond O, that means of aldehyde or ketone, is treated with HI in presence of red phosphorus, remember this is a very, very, very strong reducing agent. It will reduce C double bond O, it will remove O, and instead of O, H2 will be there. After that, oxidation of aldehydes or ketones. Number one, first of all, if it is an aldehyde, we have to oxidize it into carboxylic acid. That means we have to break which bond? We have to break CH bond. Number second, if you are having a ketone, its oxidation is very difficult. But it can be done by using strong oxidizing agents, and that too under drastic conditions. I have already told you that in, oxidation of secondary alcohol when ketone was formed there. So under drastic conditions. Why is it so? Why it resists oxidation? Because here we have to break CC bond. CC bond is very strong. That's why it does not undergo oxidation easily. So that's why if it undergoes oxidation by using strong oxidizing agents only. And it can undergo oxidation by using mild oxidizing agents or by using strong oxidizing agents. Now, have a look. First reaction is oxidation of aldehyde by using strong oxidizing agents done in alcohols. That means minutes, or you can say 1 hour ago we have done this reaction. Now, reduction, then oxidation, give me a second. Then it is oxidation of aldehydes by using mild oxidizing agents like Ag positive, Cu di positive. Now, these are mild oxidizing agents. So, we will simply reduce Tollens reagent. That means Tollens reagent will act here as an oxidizing agent. That means it is either oxidation of aldehyde by using Tollens reagent, or it is oxidation of aldehyde by using mild oxidizing agent, or we can simply say reduction of Tollens reagent. Have a look. Whether you have aromatic aldehyde, whether you have aliphatic aldehyde, when this is treated with Tollens reagent, have a look. Tollens reagent will oxidize this aldehyde and it will result in the formation of, sodium salt, or salt of what we call this carboxylic acid. Now, after that, silver will be deposited on the walls of a test tube and it will shine like that of a mirror. So this is known as what we call silver mirror. Now, the question is, what is meant by Tollens reagent? Tollens reagent is basically ammonical silver nitrate solution. Listen carefully, this is very important chapter. Now, what is meant by that? That means it is actually formed, it has been formed, it is like this, it is basically this one. It is Ag, NH3, whole 2 and OH. This is a coordination complex. This is what we call ammonical silver nitrate solution or Tollens reagent, and it is formed when AgNO3 and NH4OH, that means solution of ammonia and AgNO3, ammonical silver nitrate solution, gives this one Tollens reagent. Now, after that, what you have to remember is that whenever we talk about ketones do not show this reaction. Ketones do not show this reaction. Which means we can distinguish aldehydes from ketones with the help of this reaction, with the help of this test, with the help of Tollens test or silver mirror test, with the help of Tollens test, or you can say silver mirror test, because ketones do not show this reaction. We can distinguish aldehyde and ketones with the help of this, because aldehyde show, ketones do not show. Suppose we have a doubt whether our test tube contains aldehyde or a ketone. Put Tollens reagent into this. If silver mirror occurs, then it is simply aldehyde, otherwise it's a ketone. But remember a few more points. Over here. Just a moment. Now, listen carefully. All aldehydes, whether aliphatic or aromatic, they will show this test. Number second, alpha hydroxy ketones, not ketones, but alpha hydroxy ketones, for example fructose, can show this test. And reason is Lowry de Bruyn von Eckenstein rearrangement. No need to go there, but you just remember this. Number third, formic acid can also show this silver mirror test, Tollens test. Number four, Phenyl hydroxylamine can also show this test. Hemiacetals can also show this test. Terminal alkynes like this can also show this test. Terminal alkyne can show also this test. But these first 5 will give silver mirror test, will form silver mirror over here, will form silver mirror, but this cannot form silver mirror, it will give white precipitate. After that, we will be having another, that means oxidation of aldehyde by using Fehling solution or reduction of Fehling solution. Have a look. This reaction is shown by aliphatic aldehyde, not by aromatic aldehyde. Aromatic aldehyde do not show this reaction. Now, here I will write down Fehling solution. What will happen? It will oxidize this aldehyde and Cu2O red precipitate will be obtained. Now the question is, what is Fehling solution? Fehling solution is alkaline solution of copper sulfate containing some Rochelle salt, Rochelle salt means sodium potassium tartarate. Now, how is it obtained? It will be obtained by adding Fehling solution B to Fehling solution A. Now, what is Fehling solution A? Fehling solution A is aqueous, not alkaline, remember. Aqueous copper sulfate solution. And to this, we will add alkaline solution of Rochelle salt, and we will get Fehling solution. So remember, aromatic aldehydes and ketones do not show this reaction. What does that mean? That means this reaction can be used as a test to distinguish aliphatic aldehyde and aromatic aldehydes. Similarly, aliphatic aldehyde and ketones. Remember this. In addition to this, you have to remember one more point, that is, aliphatic aldehyde shows this test. Aliphatic aldehyde show this reaction. Number 2, alpha hydroxyketones can show this reaction. Number 3, what we call formic acid can also show this reaction. Remember. After that, reduction of Benedict solution or oxidation of aldehyde by using Benedict solution. It takes place in similar manner as that of Fehling solution. That means when aliphatic aldehyde is treated with Benedict solution, it will be oxidized to RCO negative. That means it is oxidized. Then it will form Cu2O red precipitate of that. Similarly, aromatic aldehydes do not show this reaction. Aromatic aldehydes and ketones do not show this reaction. Aromatic aldehydes and ketones do not show this reaction, my dear lovely students. Do not show this reaction at all. They do not show this reaction. What does that mean? That means this reaction can be used as a test to distinguish aliphatic aldehyde from aromatic aldehydes. Similarly, aliphatic aldehyde from ketones. Number 1. Number second, what is the difference? Difference is, what is Benedict solution? Benedict solution is basically formed from aqueous copper sulfate solution plus what we call sodium citrate. Sometimes we use Na2CO3 as well. So you can remember these two only. That means one is aqueous copper sulfate, another is sodium citrate. So what is the difference between Benedict solution and Fehling solution? Only difference. There we use sodium potassium tartarate. Here it is sodium citrate. That means Cu dipositive of this copper sulfate can form complex with citrate here, and it can form complex with tartrate in case of Fehling solution. So this is the difference. Otherwise everything is same. So you have to remember, number one, aliphatic aldehydes show this reaction. Aliphatic aldehydes show this reaction. Number second, alpha hydroxy ketones show this reaction. And number third, formic acid also shows this reaction. Remember. After that, oxidation of aldehydes and ketones by using sodium hypohalite. What is sodium hypohalite? It is NaOX, or you can say it is X2 in presence of NaOH. This reaction is also known as haloform reaction. This is also known as haloform reaction, my dear lovely students. Remember. This reaction can be used as a test if NaOX is equal to NaOI, or if X2 NaOH is, I mean to say, I2 NaOH. I mean, if iodine is used, then it can be used as a test, and that test is known as iodoform test. Iodoform test. So which can show iodoform test, or which aldehyde or ketone can show haloform reaction? Have a look. Any aldehyde or ketone which contains this group can show, I mean say, haloform or iodoform reaction or test. Similarly, if this alpha position is having one halogen, it can show test. If it contains two halogen, it can further show this reaction or test. If it contains three halogen, it can also show, I mean say, this test. So this is among aldehydes and ketones. But among alcohols, those alcohols which are having this group, that means that carbon to which alcohol OH group is attached, functional group is attached, is alpha. Alpha carbon must contain one OH, H, and one, I mean to say, CH3 group, one CH3 group, and after that it's R. R can be, it can be H, it can be any alkyl, it can be any aryl. So remember these groups. So these can show what we call this reaction or iodoform reaction. So among aldehydes, it's only CH3CHO, only one aldehyde can show this reaction, that is acetaldehyde. Or that acetaldehyde should be halogenated at alpha position. After that, among ketones, methyl ketone will show this reaction. Now, what will happen? Have a look. We can say this shows this test, but this cannot show this test. Have a look. So we can distinguish different aldehydes and different ketones and different alcohols with the help of this reaction. This will show, this will not show, because this is having C double bond O to that alpha, to that CH3 group is directly attached. This is having C double bond O, but at alpha it's not CH3, so it will not show. Similarly, this will show this reaction, because at least C double bond O and one alpha CH3 is there, but this will not show the reaction. This cannot show the reaction because no CH3 is present at alpha position, so it will not show, it will show. Similarly, it can show. This alcohol can show, ethanol can show, because it's having one H, one OH and one CH3, it can show. But if I write down this, it will not show. Why? Because it is having one OH and one H, but it is not having one CH3 directly attached, so it will not show. So with the help of this reaction, this test, we can distinguish different aldehydes, different ketones and different, alcohols. Suppose this is an aldehyde, or this is the ketone, or this is what we call an alcohol which can show this reaction. Now, what will happen? When it is treated with, say for example, I2, iodine, suppose, iodine, in presence of NaOH or NaOI, you can say NaOI. Now, what will happen? How to form product if this reaction is given? Very, very simple. Just break alpha CH3 in case of aldehyde or ketone, one alpha CH3 bond with C double bond O. Convert this alpha CH3, not two, only one alpha CH3. Here, two alpha CH3 groups were there, one. Convert that CH3 into CHI3. Depending upon what is this halogen. If it is I, then I3. This is iodoform, its color is yellow. So yellow precipitate will be obtained over here. Then give this ONA to this, ONA to this. Then it will become HCOONA, it will be CH3CONA. So these will be the products. HCOONA, side product, and CH3COONA will be the side product. Here what we have to do here is, this is alpha. CH3 attached to alpha, break that bond. Convert that CH3 into CHI3. It will be precipitated as yellow color precipitate will be obtained. Yellow precipitate will be obtained. Yellow precipitate will be obtained. Then at alpha, convert CHOH, not CH2, CHOH to COONA, and as one H is extra, so it will result in the formation of HCOONA. So this is what we call, this is known as iodoform test or haloform reaction. After that, we will be having a very, very, very important reaction, that is aldol condensation. What is aldol condensation? But before that, let me tell you that this aldol condensation is actually of two types. It is acid catalyzed as well as base catalyzed. But acid catalyzed is not in our syllabus. So our main focus should be on this, not on this. Base catalyzed is of two types. One is intermolecular. Another is intramolecular. Another is intramolecular. My dear lovely students, listen carefully. This intermolecular is further of two types. One is simple or self. Another is what we call mixed or crossed. So let us take these one by one. But before that, you have to remember substrate of this reaction. Substrate should be aldehyde or ketone, but for condensation containing at least 2 alpha hydrogen. I'm not talking about aldol reaction. For aldol reaction, only 1 alpha hydrogen is needed. But for aldol condensation, it's basically acidic hydrogens. But you just remember alpha hydrogens because your NCERT has, given examples of alpha hydrogens only. Now, containing at least 2 alpha hydrogens. I hope this is clear. Now, after that, reagents. Base. 10% NaOH or KOH. That means mild base is used. BaOH whole 2 can be used. CaOH whole 2 can be used. Aqueous Na2CO3 can be used. Mild bases can be used. Now, what will happen? Have a look. Whenever you are having simple or self intermolecular aldol condensation, then what will happen? Have a look. Suppose you are having an aldehyde like this. This is partial positive, this is partial negative. Now, take another aldehyde, because what is meant by self? Between the same molecules. Self means similar molecules. So, I will take another molecule similar to this and I will show its alpha hydrogen. And carbon and hydrogen, among carbon and hydrogen, carbon is partial negative, hydrogen is partial positive. Now, what you have to do is break this double bond, give negative part to positive part to negative part. Now tell me what will happen over here. If NaOH dilute is used, 10% is used, now what will happen? It will result in the formation of CH3, then CH, then it will become OH, because this negative part, positive will go to negative, then it is CH, then this negative will form bond with this, that means it is CH2, then CHO. This is alpha, this is beta, so beta hydroxyaldehyde is formed, this is known as aldol. That reaction during which aldol is formed, from aldehyde is known as aldol reaction. This is aldol reaction. Similarly, if we take an example of ketone, CH3, C double bond O, CH3. This is partial positive, this is partial negative. Take similar type of ketone, but show alpha hydrogen there. Similar type of ketone, because similar type of, say carbonyl compounds undergo self-intermolecular or simple intermolecular aldol reaction. Have a look. So without heat, aldol will be the product. Now, this is, say alpha carbon, partial negative, partial positive. Break this double bond into single bond. Give this H to negative part, say positive part to negative, negative to positive. So the product will be like this. CH3COH. Can I write this CH3 here? So that I will join these two. So it will be like this. CH2, C double bond O, and then CH3. This is alpha, this is beta. So this is beta hydroxy ketone known as ketol. Whether ketol is formed from ketone, whether aldol is formed from, say aldehydes, reaction is known as aldol reaction. After that, if this aldol is heated or this ketone is heated, medium is basic. If this is heated, what will happen? Water will be lost. From where? From which position? From alpha, hydrogen will be lost. From beta, OH will be lost. That means there will be formation of alpha beta double bond. There will be formation of a double bond between alpha and beta position. So alpha beta unsaturated aldehyde will be formed over here, and alpha beta unsaturated ketone will be formed over here. From this to this, remember, from this to this, reaction is aldol reaction. From this to this, reaction is known as aldol reaction. From this to this, it is known as dehydration of aldol. This is dehydration of aldol. This is simply dehydration of ketol. In nutshell, dehydration. From this to this, we need one alpha hydrogen here. From this to this, we need one alpha hydrogen here. From this to this, we need one more alpha hydrogen. From this to this, we need two alpha hydrogens. From this to this, we need two alpha hydrogen. In nutshell, aldol reaction plus dehydration. Aldol reaction plus dehydration is known as aldol condensation. Aldol reaction plus dehydration is known as aldol condensation. Now, I have shown you the trick of aldol reaction, how to form this, and then after that, remove hydrogen from alpha, remove OH from beta, form this. This is very easy. But if you want directly from this to that, now what is the trick? Have a look. You must have one aldehyde, form it like this. That means you have to remove oxygen from one aldehyde and two alpha hydrogens from similar type of aldehyde if it is self or simple aldol condensation. Now, we want to perform aldol condensation. Aldol condensation does not take place until and unless heat is there. Now, similarly, you have ketone like this. I will write down another ketone like this. we want to perform aldol condensation, we must remember there must be at least heat as well. Otherwise, there will be no aldol condensation, there will be aldol reaction. So this is the trick. Remove 2 alpha hydrogens from one and remove oxygen from another. That means water will be lost and we will get, this is CH3CH, then it will be double bond CH, then it will be double bond CHO plus water. So alpha beta unsaturated aldehyde is product. Here it will be like this, double bond CH, single bond C double bond O, CH3 plus water. This is alpha beta unsaturated ketone. So this was all about self intermolecular aldol condensation and self intermolecular aldol reaction. Let me know in the chats, am I clear till now? Let me know quickly. Let me know quickly, am I clear till now? Let me know quickly. Let me know quickly in the chats. Am I clear till now? Let me know quickly. I'm waiting for your response. Let me know quickly. I'm waiting. Come on, let me know. Am I clear till now? Okay, thank you and God bless you. So this was all about self. Now, let's talk about mixed or crossed. Mixed or cross. When this mix or cross takes place, listen carefully. If both aldehydes or both ketones or both carbonyl compounds contain alpha hydrogens, or one contain alpha hydrogen, another does not contain alpha hydrogen. Remember this. But at least one must contain alpha hydrogen, another does not contain alpha hydrogen. Suppose if you are having this one, it contains alpha hydrogen, and if you are having another, this one, this is different from this, it also contains alpha hydrogen. Both contains alpha hydrogen. When here aldol condensation or aldol reaction takes place, if I write down like this, then it will be aldol reaction. If I will write down heat, then it will be aldol condensation. Remember, 4 products will be obtained over here. How? First you react this with similar type, that will form one product. Then react this with similar type of aldehyde, that will be another product. Then react this with this, in which you remove 2 hydrogens from alpha and oxygen from this, third product. Then react this with this, but remove 2 alpha hydrogens from this and oxygen from this, form product, that will be the 4th one. After that, but here many products will be formed, that means 4 products will be formed. But if you are having this one is what we call benzaldehyde, it does not have any alpha hydrogen, and another is acetophenone. This is having one alpha this is having at least 2 alpha hydrogens. Now what will happen if reaction takes place in basic medium, and that too at low temperature, 293 Kelvin? That means there is no heat. So I have told you that if there is no heat, form aldol, that means form ketol, that means aldol reaction takes place. But here, whether heat is present or not, if heat is absent, if heat is given or not, remember here aldol condensation will be the final product. Why here aldol condensation takes place? Why not aldol reaction? Because answer is very simple. Because after condensation, you can have a look. Here, this alpha beta unsaturated product is such that here extended conjugation is there. That is why, as extended conjugation takes place, that is why we will form aldol condensation product, not aldol reaction product. So simple trick is when you form, say for example aldol, if temperature is not given, first form aldol and check if gamma position contains any double bond in aldol. If gamma position does not contain any double bond in aldol, and if heat is not given, just stop over here. If heat is given, lose water molecule and form aldol condensation product. Similarly, heat is not given over here. Just try to understand, try to form, I mean say aldol. Then this is alpha, it will react with this is beta, this is gamma. Gamma contains pi bond. Whenever gamma contains pi bond, gamma of aldol or ketol, I mean say gamma of the product formed during aldol reaction, if it contains pi bond, then you have to lose water molecule, you have to form alpha beta unsaturated carbonyl compound. Just that. That is the truth. But actual reason is that here, because of extended conjugation, it becomes very much stable. That's why it loses water molecule. No need of, I mean to say, heat over here. After that, this is the major product, major one. After that, we will be having intramolecular aldol condensation. Suppose you are having this one, aldehyde. You must know that we must have dicarbonyl compound, but such that dicarbonyl compound should be such that it should result either in the formation of 5-membered ring or 6-membered ring. Let's have a look. 1, 2, 3, then this is 4, this is 5, and this is, I mean say, CHO. Let us suppose I want to perform aldol condensation over here. That means this and heat. Let us suppose I will remove this C double bond O. That means this will become alpha, from which I have to remove hydrogens. So I will number it like this. Let me number this. 1, 2, 3, 4, 5 and 6. Now I have to join 1,5 bond. That means I have to form a 5-membered ring. Let me form first a 5-membered ring like this. Now I will number it. Let us suppose this is 1, this is, I mean say, 2, this is 3, this is 4, this is 5. Now at 5, what is this? This is CHO. At 5, we will be having CHO. So let me write down CHO at 5. Now, from 5th position, I have removed 2 hydrogens, and from 1 position, I have removed oxygen. That means between 5th and 1st, there will be a double bond. So this is, I mean to say, our aldol condensation product. After that, we will be having another reaction that is known as Kenny-Zorro's reaction. Once again, remember, this is of 2 types. One is intermolecular. This is of 2 types. One is intermolecular, another is intramolecular. One is intermolecular, another is intramolecular. Intermolecular is of 2 types, self or simple. Another is mixed or crossed. Now, substrate. This is shown by aldehydes, not by ketones, only by aldehydes, but without alpha hydrogen. There are many examples which does not have alpha hydrogen, but still they do not show Kenny-Zorro reaction. But we don't have to go there. We have to simply check what is, I mean say, what can be asked in your NEET 2026 or JEE mains. Now, have a look. This is, I mean say, aldehydes without alpha hydrogen, which can show this reaction. Base used over here or reagent used over here is concentrated KOH or concentrated NaOH. Or sometimes we will use 50% NaOH or KOH. 50% NaOH or KOH. Now, first of all, let us start intermolecular Kenny-Zorro reaction. Intermolecular Kenny-Zorro reaction, remember, is an example of disproportionation reaction. It's an example of disproportionation reaction. What is meant by that disproportionation? That means this is self-oxidation and reduction. What is meant by that, sir? Have a look. This is formaldehyde. Let's take another example. That means similar type of aldehyde. That's why simple or self. This is not having any alpha hydrogen. This is not having any alpha hydrogen. On treatment with concentrated NaOH, what we have to do is, we have to oxidize one, we have to reduce one. That means we have to convert CHO of 1 into COONA. That means we have to oxidize it and we have to reduce it. How to reduce? Convert C double bond O to C single bond O, give H to carbon as well as oxygen. That means it will result in the formation of CH3OH. So one is oxidized to carboxylic acid or its salt, another is reduced to alcohol. Similarly, this is benzaldehyde and benzaldehyde. What will happen over here? One benzaldehyde molecule is oxidized and another will be reduced. So it will form COONA, depending upon if it is NaOH then CONA, if it is KOH then COOK. Okay, now, and another will form an alcohol like this. So one is oxidized, one is reduced. Here, basically during mechanism, the rate determining step is hydride transfer step. Remember that as well. After that, we will be having another, say this was intermolecular, but let me write down over here. This is self or simple, not intermolecular. This is self or simple, which is disproportionation. Now after that, we will be having mixed or cross. That will be simply oxidation reduction. That will be simply an oxidation reduction reaction. That means one will oxidize and another different molecule will reduce. Now the question is, which one will oxidize and which one will reduce? Have a look. But remember, both the aldehydes must be such that there will be no alpha hydrogen neither with this aldehyde nor with this. That means aldehydes used in mixed or cross Kenies-Oro reaction should be such that neither of the aldehyde must contain alpha hydrogen. No one should have alpha hydrogen. If any one is having alpha hydrogen, then at that time it is cross aldol instead of cross Kenies-Oro. Now, what will happen now? You have to remember, this is aldehyde, this is aldehyde. You have to remember aldehyde, which is more reactive towards nucleophilic addition reaction. That is this one. More reactive towards nucleophilic addition reaction. You must know that is oxidized. That means another will be reduced. So this is more oxidized as compared to this because this is having electron donating group. Electron donating group attached to C double bond O decreases its reactivity towards nucleophilic addition reaction. So oxidize this, that means it will result in the formation of HCOONA, and reduce another one, that means it will result in the formation of CH2OH. That's it. Very, very, very simple. Similarly, if you are having one aldehyde like this, in which CH3 electron donating group is attached, and in another it's like this, electron withdrawing group is attached. Electron withdrawing group increases the rate of nucleophilic addition reaction and electron donating group decreases. Now, which one is more reactive now? This is more reactive, this is less reactive. So more reactive will be oxidized and less reactive will be reduced. So it will result in the formation of alcohol over here, and this will form an oxidation product over here like this. Very, very simple, very, very simple. Now after that we will be having intramolecular. For that we must have dicarbonyl compound, but among these C double bond O, 2 C double bond O, at least one must have hydrogen, otherwise reaction will not take place. Now this is both C double bond O are having H attached to it, that means they are similar. So convert one into alcohol, that means means it is CH2OH, one, and another will be oxidized to CONA. But if you are having different like this, now tell me which one will be oxidized now and which one will be reduced now. This is more reactive. This is electron donating. It will reduce its reactivity. So this is less reactive. This is more reactive. Less reactive will be converted. Sorry. Less reactive will be converted to alcohol and more reactive will be converted to salt, or it's oxidized. It's reduced. It's oxidized. So this was all about Cannizzaro reaction. After that, aromatic electrophilic substitution reactions of aldehydes and ketones. We have common in aldehyde and ketone, and that is this one. If H is here, so it's aldehyde. If it's R or any other group is there, say aryl, then it is ketone. So have a look. It's electron withdrawing group in nutshell. And electron withdrawing groups does not show Friedel-Crafts alkylation or acylation in general. That's why let me show halogenation. But remember, this must be in excess. And let's suppose this is nitration. And we know this electron withdrawing group decreases electron density at ortho and para position. Hence, such groups are meta-directing groups. Now, this is sulfonation. Here electrophile is SO3, here electrophile is NO2 positive, so electrophile goes to meta position. Here electrophile is Cl positive, so electrophile will go to meta position. In nutshell, electrophile will go to meta position. So this is the electrophile of the reaction and HCl will be the side product. Here electrophile of the reaction is NO2, so it will be introduced to meta position and H2O will be the side product. Here SO3H will be introduced to, meta position, and water will be lost in the form of a side product. After that, we will be having methods of preparation of carboxylic acids. First, from alcohols and aldehydes, it is done, already done. You can say in alcohols, you can say in, chemical reactions of aldehydes and ketones as well. Aldehydes and ketones as well. After that, from alkyl benzene, have a look. If you are having an alkyl benzene like this, which contains at least one benzylic hydrogen, it is oxidized. This contains at least one, benzylic hydrogen, this can be also oxidized. This contains one benzylic hydrogen, this is also oxidized. This does not contain any, let me show this over here. This does not contain any benzylic hydrogen. So this will not show the reaction. So remember that alkyl benzene shows this reaction which I am going to show you, which contains at least one benzylic hydrogen. So what is the reaction? First of all, let me show you the reaction. What is the reaction? Reaction is on treatment with strong oxidizing agent, say for example KMNO4 and KOH, let us suppose. What will happen? This strong oxidizing agent will oxidize that alkyl part which contains at least one, hydrogen, to carboxylic acid. But here it will form COH, but as basic medium is there, base will abstract H, it will form COOK. But after that, if this undergoes, acidification, now KCl will be lost and we will get, acid. Or if you use strong oxidizing agent directly in acidic medium, say for example K2Cr2O7 in acidic medium, K2Cr2O7 in acidic medium, K2Cr2O7 in acidic medium, then no need to form salt and after that acidification. Directly you can form. Convert alkyl, whether it contains 1 carbon, 2 carbon, 3 carbon, irrespective of its size. Convert one alkyl group to COH, that means benzoic acid will be obtained. But only thing you have to remember is that alkyl must contain one hydrogen at benzylic position. Similarly, convert this into, COOH. Have a look. It's methods of preparation of carboxylic acid. So, here we get carboxylic acid. Similarly, here no benzoic acid formation takes place. Why, sir? No benzoic acid formation takes place. Reason, what is the reason? As there is no benzylic hydrogen at all. Okay, but if I give you the reaction like this, this is orthoxylene, what will happen? There are two alkyl groups directly attached to, say this benzene ring. Convert this into COH, convert this into COH. So we will get phthalic acid over here. Phthalic acid will be obtained over here. Similarly, if you are having a group like this, now have a look. This is having one hydrogen. This carbon is having one hydrogen. Convert this CH into COH. Convert this CH into CH. That means similar product, phthalic acid will be obtained. Phthalic acid is obtained. That means you have to convert basically CH directly attached to, say that carbon which is directly attached to benzene ring. If it contains hydrogen, convert that into COH. That's it. That is it. Very, very simple reaction. After that, from nitriles and amides, my dear lovely students, have a look. When nitrile is there and the reaction is like this, H2OH positive or H2O, that means hydrolysis. What you have to do is break one bond, give H to this, OH to this. After that, break another bond, give H to this, OH to this. So you will get RC double bond ONH2. But if you break all these three bonds between cyanide, all these three bonds, add H, add OH, 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 then you will get carboxylic acid. This reaction is known as hydrolysis, or you can say complete hydrolysis. This reaction is partial hydrolysis. So if partial hydrolysis is written there, at that time you have to convert cyanide to amide. If hydrolysis is given, or if it is only H2OH positive, H2OH minus, convert cyanide to acid. This amide can also be converted to acid. Have a look. This amide can also be converted to acid if we use water molecule. How? Then add H over here, OH over here. Then it can also be converted to this. But from this to this is partial hydrolysis. From this to this is complete hydrolysis. Or from this to this is also complete hydrolysis. But hydrolysis give carboxylic acid from cyanide, but partial hydrolysis give amide from cyanides. After that, next reaction. From Grignard's reagent, have a look. This is Grignard reagent. When Grignard reagent is treated with carbon dioxide in presence of dry ether, this carbon dioxide will act as an electrophile and this Grignard reagent will act as a nucleophile. This will attack on this electrophilic site. Now, what will happen? It will form RC double bond O. C has formed bond with R, double bond O is there, single bond, O minus MgX is there. Finally, my dear lovely students, it will undergo hydrolysis. So give H to this, OH to this. So it will result in the formation of carboxylic acid and Mg, X and OH, hydroxy magnesium halide, and I mean to say carboxylic acid. After that, from acyl halide and acid anhydride, this is acyl halide. This is acyl halide. This on treatment with water, what will happen? And then anhydride, this on treatment with water, what will happen? Remember, this is acyl part, nucleophilic acyl substitution will take place. This will break, nucleophile goes to this. That means give OH to this. Water is the nucleophile, but finally give OH to this and give H to this. Similarly, give OH to this give H to this. That means this is nucleophilic acyl substitution. Nucleophilic acyl substitution reaction. Here it will be HCl, here it will be acid. Here it will be HCl, here it will be acid. RCOOH. Now if this R and R is same, then it is twice RCOH. After that, from esters, have a look. This is ester. This is ester. If you want to perform hydrolysis of ester, let us suppose in acidic medium, what will happen? This is acyl group, break this one, give OH to this, give H to this. Then we will get RCOOH and R prime OH. That means acid and alcohol. But my dear lovely students, have a look. If same ester is treated with, if it is treated with water, but in basic medium, suppose base is NaOH. Now what will happen? This bond will be broken. First of all, it will result in the formation of OH. It will, form alcohol and acid. But this base will abstract H positive from acid and will form sodium salt of acid. So acid will be converted to sodium salt, then alcohol. I hope this is clear to you. But this reaction, during this reaction, this can be soap if R is large. For example, if R is C17H35. So this is higher fatty acid. Sodium salt of higher fatty acid means soap. That is why this reaction is known as saponification reaction. This is known as saponification reaction. This is known as saponification reaction. Now, after that, if you are having an ester and this is treated with alcohol, now what will happen? What will happen, my dear students? This OR part will be replaced by this OR part. That means ester will form ester and alcohol. Ester and alcohol will form ester and alcohol. But the only difference is that this R and this OR, this OR and OR, they are, transferred from this place to this, from this to this. That means they have been exchanged. Only that has been formed. This reaction is known as transesterification. Transesterification. This is transesterification. After that, chemical reactions of carboxylic acids. Reaction with metal. Remember. Whenever you are having a carboxylic acid and it reacts with any metal, suppose sodium, potassium, magnesium, calcium, zinc. Now, what will happen? It will lose this water, it will lose this H positive. That means hydrogen gas will be obtained. Let us suppose H2 gas is obtained. And it will form a carboxylate ion, but it will be simply that metal carboxylate with which this carboxylic acid reacts. So metal carboxylate and hydrogen gas will be removed. After that, next reaction. Reaction with carbonates and bicarbonates. Very simple reaction. A reaction of carboxylic acid with, say for example, sodium bicarbonate. We know this is having negative charge, this is having positive charge. Negative charge will abstract this like this and O minus. So what we will get is, we will get RC double O negative Na positive and H2CO3. But remember, my dear students, this is known as carbonic acid. Once formed, it gives brisk effervescence. Brisk effervescence of carbon dioxide. Effervescence of carbon dioxide will be obtained over here. Similarly, if you use sodium bicarbonate, then what will happen? It is Na positive, CO3 2 minus. First CO3 2 minus will abstract one H from one acid, another H from another acid. Once again it will form carbonic acid first. It will form RCO Na positive and it will form carbonic acid. That carbonic acid is converted to carbon dioxide and H2O. Now, this reaction can be used as a test to distinguish carboxylic acid from phenol. Why? Because this brisk effervescence with sodium carbonate or sodium bicarbonate is only shown by those acids which are stronger acids than carbonic acid. And we know carboxylic acid is stronger acid than carbonic acid, but phenols are weaker acids in general than, say, carbonic acid. That's why phenol do not show this reaction, do not give brisk effervescence, but carboxylic acid can give. So this reaction can be used as a test under the name sodium bicarbonate test or sodium carbonate test, and can distinguish carboxylic acid from phenol. Next, reaction of carboxylic acid with alkali. Suppose NaOH. NaOH will abstract H, OH will abstract H from this. That means it will result in the formation of sodium salt of carboxylic acid and water. Similarly, carboxylic acid can react with ammonium hydroxide. It's also a base. OH minus will abstract H positive from this, and it will result in the formation of ammonium salt of carboxylic acid and water. Ammonium salt of carboxylic acid and water. After that, formation of anhydride. Have a look. This is carboxylic acid. This is another carboxylic acid. Carboxylic acid will lose water molecule in presence of a dehydrating agent. Suppose P2O5 upon heating. Similarly, carboxylic acid on treatment with H2SO4 upon heating will lose water molecule because these are the dehydrating agents, and they will result in the formation of anhydride. So acid derivative is this anhydride. It has been obtained from acid. After that, formation of acyl chloride. Have a look. If you are having a carboxylic acid, and if you treat it with PCl5 or PCl3 or what we call SOCl2, what will happen? Replace this OH by Cl, then it will result in the formation of RCOCl. In first case, side product will be POCl3 and HCl. In second case, side product will be H3PO3. In third case, side product will be SO2 plus HCl. So better method to prepare RCOCl from carboxylic acid is thionyl chloride, SOCl2. Now, after that, formation of ester, simple reaction, esterification reaction. Carboxylic acid plus alcohol in presence of acidic medium will simply lose water molecule, and if this is having O18, we will get an ester like this. In water, oxygen came from, say, carboxylic acid. Simple. Formation of amide. Have a look. Whenever carboxylic acid is heated with ammonia, if it is heated with ammonia, it results in the formation of amide and water molecule. Or you can simply say this reaction like this. When it is treated with ammonia, it first results in the formation of ammonium salt of carboxylic acid. Then this upon heating, have a look, will lose water molecule. Then it will result in the formation of CONH2, say amide. It's one and the same. After this, reactions involving COH group, that means reduction to alkane, from carboxylic acid to alkane. This is carboxylic acid. If you want to form alkane from this, you have to reduce it by HI red phosphorus. Remove oxygens and give hydrogen. So it will result in the formation of this. After that, reduction to alcohol. We know carboxylic acid is reduced to alcohol, already done in alcohols, by using lithium aluminium hydride followed by hydrolysis, or B2H6 followed by hydrolysis. What you have to do is break this bond, give H to this, break this bond, give H to carbon, H to oxygen. So we will get RCH2OH. Very, very simple reaction. After that, my dear students, it's decarboxylation. Decarboxylation means loss of carbon dioxide. That means you have to convert this into alkane and you have to lose carbon dioxide. Now the question is how this carbon dioxide is lost. Have a look. If you use RCOOH and if you treat it with sodium hydroxide first, it will form sodium salt of carboxylic acid. It will form sodium salt of carboxylic acid first. After that, if it is treated with soda lime, that means NaOH and CaO in the ratio of 3:1, it will lose carbon dioxide but in the form of Na2CO3. That means carbon dioxide is lost in the form of CO3 2-. Now, after that, it will result in the formation of alkane like this. Now, this is using soda lime. After that, Kolb's electrolysis. If you are having sodium salt or carboxylic or potassium salt of carboxylic acid, this one treatment with water undergoes electrolysis. And remember forever, this upon electrolysis will simply break this bond, form an radical over here and combine these radicals, will form RR at anode. Similarly, carbon dioxide gas is evolved at anode. Hydrogen gas is evolved at cathode. Remember this. And solution will be NaOH or KOH depending upon whether it is sodium salt or potassium salt. So solution is having pH greater than 7. But you have to note down this thing. If RCOONA is HCONA, I mean say if we take sodium salt of formic acid, sodium methanoate, sodium formate, then this R is H, this R is H. That means at anode and cathode, we will get H2H2 as well as carbon dioxide at anode. Remember that. After that, we will be having Haloalkanes reaction. This is HVZ, Haloalkanes reaction. What is this? This is nothing. First of all, this is shown by carboxylic acid containing at least one carboxylic acids. This is shown by carboxylic acids containing at least one alpha hydrogen. Now, what is the reaction? Have a look. So, formic acid cannot show this reaction. Because formic acid does not have any alpha hydrogen. So, it is halogenation, whether it is chlorination or it is bromination, taking place in presence of red phosphorus followed by hydrolysis. So what will happen? This halogen will replace alpha hydrogen, so it will form alpha halo acid. And if halogen is taken in excess, then all the alpha hydrogens will be replaced. So this is known as Haloalkanes reaction. After that, we will be having aromatic electrophilic substitution. This is substitution. This is substitution. Reactions. Okay. Have a look. We will be having C double bond OH. We know this is electron withdrawing group. So that means this will withdraw electron from this benzene ring and decreases electron density at ortho and para position. Hence, this is meta-directing. Now, this will not show Friedel-Crafts alkylation or acylation because those groups which are electron withdrawing attached to benzene ring, such compounds do not show, I mean to say, what we call Friedel-Crafts alkylation or Friedel-Crafts acylation reaction. Suppose we will do halogenation, let us suppose chlorination or bromination, whatever you like. Now, Cl positive will be the electrophile and Cl positive electrophile will go to meta position. So this will be the product of this reaction. Similarly, if you want to do what we call nitration of this compound, nitrating mixture is used. Now, NO2 positive will be the electrophile. Where electrophile go? electrophile will go to meta position. Electrophile will go to meta position, and this will be the product. Similarly, if we want to perform sulfonation, then sulfur trioxide acts as an electrophile, and finally it will go to meta position as SO3H. That means sulfonic acid will be introduced to meta position, and this will be the side product. So this was all about aldehydes, ketones, and carboxylic acids. Now, let me know in the chats, do you want a break of 10 to 15 minutes or not? Should we continue, or you want to break off 10 to 15 minutes? Let me know quickly in the chats. Let me know quickly in the chats, because we have last chapter now, that's amines. After that, if time permits, we will discuss few previous year questions as well. Let me know quickly in the chats. Let me know quickly in the chats. Should I continue, or should I stop over here for 10 to 15 minutes? Let me know quickly. Let me know quickly, my dear lovely students. Let me know quickly. Okay, you want break? Okay, let's meet at 8:30 then. Let's meet at 8:30 exactly. So break till 8:30. Come on. This is for you. This is for you. After that, after break, we will revise amines and diazonium salts. Okay, take care. We'll meet exactly at 8:30. We'll meet exactly at 8:30. Welcome back again. But before we move ahead, let me know quickly if I am audible and visible to each and everyone. If I am audible and visible to each and everyone, let me know in the chats quickly. Am I audible and visible? Let me know in the chats quickly. Let me know in the chats quickly. Okay, that's great. So let's complete this last chapter very quickly. Let's revise this chapter very quickly so that we can do few, PYQs as well. Let's get started without wasting time. Let's get started. Let's get started without wasting time. Let's get started without wasting the time. Now, first of all, it's Hoffman's ammonolysis method. It's already done in alkyl halides, done in nucleophilic substitution reactions of haloalkane. Now, after that, another is catalytic reduction. Have a look. If you are having an aromatic or aliphatic nitro compound, whenever you are having aromatic or aliphatic nitro compound, H2 in presence of catalyst will convert this nitro compound into amine. And catalyst used generally can be nickel, can be platinum, it can be palladium. Okay, after that, reduction by using active metal in HCl. Once again, if you are having aromatic or aliphatic nitro compound, and if it is treated with active metal, say for example tin in HCl or iron in HCl, or you can use zinc in HCl, and just what is the function of these reducing agents? They convert NO2 of aliphatic or aromatic nitro compound to amine. So aromatic nitro compounds will convert it to aromatic amine, and aliphatic nitro compounds will be converted to aliphatic amines. After that, reduction by using lithium aluminium hydride. Have a look, my dear lovely students. If you are having aliphatic nitro compound and if it is reduced with lithium aluminium hydride, this will convert NO2 to NH2. That's it. But if you are having an aromatic compound like nitrobenzene, remember, lithium aluminium hydride will not reduce it to amine, but it will reduce it to azobenzene. It will convert it to azobenzene. Remember this reaction. Here, reaction is different. Now, after that, reduction in neutral medium, whether it is aromatic, whether it is aliphatic nitro compound, if it is treated with zinc, ammonium chloride, then it will convert aromatic or aliphatic nitro compounds to hydroxyl amines. Say NHOH. Say for example, you are having nitrobenzene. If this nitrobenzene is treated with zinc NH4Cl, that means if it is reduced in neutral medium, it will result in the formation of N-phenyl hydroxyl amine. And we know this on treatment with Tollens reagent is reduced. It is basically oxidized and it reduced Tollens reagent to silver mirror. So it forms nitrosobenzene and it forms silver mirror. That means this can also give Tollens test. Now have a look. This reaction can be used as a test for nitro compound under the name Baker-Mulliken, or we can say Barker, because sometimes it is written as Barker-Mulliken test. So with the help of this, we can distinguish nitro compounds in neutral medium from rest of the others, because they will give silver mirror test over here. After that, reduction in this is electrolytic reduction. Have a look, but of nitrobenzene. When you have nitrobenzene and it undergoes electrolytic reduction, electrolytic reduction, if it undergoes electrolytic reduction in weakly acidic medium, if it undergoes reduction in a weakly acidic medium, it will form aniline. It will form aniline. So NO2 is reduced to NH2, but in strongly acidic medium, what will happen? What will happen? Have a look. In strongly acidic medium, it first forms hydroxylamine, but this will undergo rearrangement and it will result finally in the formation of para-aminophenol. It rearranges to para-aminophenol. That means nitrobenzene in strongly acidic medium gives us para-aminophenol. Then selective reduction. Say for example, if you are having more than one nitro group and you want to reduce only one nitro group, then we have to do selective reduction, and that can be done with the help of ammonium sulfide or sodium sulfide or sodium bisulfide. I mean to say that can be done by sulfides and polysulfides, and this reduction takes place in such a way that one is reduced, another is not affected at all. This reaction is known as Zenin reduction. This is known as Zenin reduction. After this, we will be having reduction of nitriles and isonitriles. Have a look. If you have nitrile, if it is reduced with, say for example, H2 in presence of catalyst, and let us suppose that catalyst is ranitol, or this is, say lithium aluminium hydride, or you can say sodium amalgam, or you can say sodium directly in ethanol, either sodium in ethanol or sodium amalgam in ethanol. What you have to do is convert CN into CH2NH2. That means primary amine is obtained. Primary amine is obtained. We have to add hydrogen across, to say this, hydrogen, 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 hydrogen. Very, very simple reaction. This reaction due to which cyanide is reduced to primary amine by using sodium amalgam, and this is known as Mendius prime. That means this is, say di-substituted amide or tertiary amide. Whether it is primary amide, secondary amide, tertiary amide, this upon reduction by using lithium aluminium hydride followed by hydrolysis will simply convert this C double bond O, C double bond O, C double bond O, but of amides gets converted to CH2. That means we will get primary amine from primary amide but containing same number of carbons, secondary amine from secondary amide with similar number of carbons, and tertiary amine from tertiary amide with similar number of carbons. So you have to convert only C double bond O to CH2, rest there is no change. After this, reduction of azide. This is azide, RN single bond N triple bond N. This is having a positive charge and this is having a negative charge. Now this is alkyl azide. This alkyl azide on treatment with lithium aluminium hydride or H2 in presence of PD with small amounts of carbon, this bond will be broken, and here this N will get hydrogen, so we will get primary amine once again. After that, reduction of oxime, whether it is aldoxime, whether it is say ketoxime, hardly matters. This is an oxime. This oxime upon reduction by using lithium aluminium hydride or sodium in alcohol, what will happen over here? You can break this bond, one bond give H to this, break this bond, give H to this. In nutshell, you will get an amine in which functional group is NH2. That means this is once again a primary amine because NH2 means functional group of primary amine. After that, Hoffman bromamide degradation reaction. Remember, this reaction is given by primary amide. First of all, primary amide on treatment with bromine in presence of NaOH or KOH, but 4 moles of NaOH or KOH should be there. After that, what will happen over here? Just remove this, and it will result in the formation of RNH2. That means we will get primary amine over here from primary amide, but with a lesser number of carbon. One carbon is less as compared to parent amide, plus it will give Na2CO3, it will give twice NaBr, and it will result in the formation of twice H2O. Now have a look. So during this reaction, it can be aliphatic, it can be aromatic, but this is the reaction of primary amide, whether aromatic or aliphatic, resulting in the formation of primary amine, whether aliphatic or aromatic, but one carbon should be less as compared to this. Now, second point, the intermediates of this reaction. Intermediates during this reaction, you have to remember, number one, first intermediate is RCONHBr. N-bromamide is the intermediate of the reaction. Second intermediate is acyl nitrene. That means RCO and then N. This is acyl nitrene. Third is what we call RN double bond C double bond O. This is known as alkyl isocyanate. Alkyl isocyanate. And remember, if this value R is equal to CH3, then we can call that as CH3N double bond C double bond O. This is known as methyl isocyanate, and this methyl isocyanate is used in Bhopal gas tragedy. It was used in Bhopal gas tragedy, which happened in 1984. So this was the gas which was used there, methyl isocyanate. Now after that, Gabriel thalamide reaction. Now the question is, what is meant by thalamide? Thalamide is this one. This is the thalamide. Now this thalamide upon treatment with potassium hydroxide, that means alcoholic potassium hydroxide here, will act as a base, and it will result in the formation of like this. It will form N-potassium thalamide. Now this upon treatment with RX, what will happen? Simple SN2 reaction will take place. So when it is the simple SN2 reaction, product will be like this. It will be C double bond O, and then N single bond R. But remember forever, this R can never be a tertiary group. It can never be, this RX can never be what we call aryl halide, or it can never be what we call vinyl halide. In nutshell, X should not be attached to this sp2 hybridized carbon. That means what happened over here will be now, finally, it will be hydrolysis. Say for example, I will simply hydrolyze it in acidic medium or in basic medium. Suppose I will hydrolyze it in acidic medium, then it will result in the formation of phthalic acid. Phthalic acid will be the product, and our main product will be RNH2. That means a primary amine will be obtained. So during, say Gabriel thalamide reaction, primary amine is obtained, but NH2 should be attached to that R which is over here. That means it can neither be, this R cannot be phenyl ring. That means aniline cannot be obtained during this reaction. So remember, aniline cannot be obtained. Aniline cannot be obtained during this reaction. We cannot get primary aromatic amine during this reaction. We cannot get primary aromatic amine, for example, aniline during this reaction. We cannot get, that amine in which NH2 is attached to carbon-carbon double bond. Remember that. We will get simply primary amine, or we can get secondary amine, but primary amine reaction rate will be much more faster. If you use H2 in presence of basic medium, then primary amine will be obtained, but base will remove this H positive. Suppose base is NaOH, then you will get sodium salt of this phthalic acid. Remember that. And one more thing. Say this one. C double bond O, NR, that means N-alkyl, this thalamide, if it is treated with hydrazine, then with the help of hydrazine, this bond will be broken, this bond and this bond will be broken. At that time, we will get like this. This is known as thalhydrazide. and we will also get primary amine. So primary amine can be obtained whether you use hydrazinolysis or you use hydrolysis. So this is Gabriel thalamide reaction. After that, my dear lovely students, we will be having chemical reaction of amine. Say for example, you are having an amine, it treats with acid. Say for example, if amine is treated with acid, let us suppose acid is HX, then this is base, this is acid, they will result in the formation of a salt. They will form RNH3 with a positive charge and X minus. Similarly, if it is aniline, it will give anilinium ion and X minus will be attached to that. That means that will be a salt of amine, say that. Salt formation will take place. Now, reaction with electrophile, reaction of amine or with alkyl halide. Remember. If this alkyl halide is taken in excess, first it will result in the formation of a secondary amine. HX will be lost. Then it will react with, once again, alkyl halide. As alkyl halide is taken in excess, HX will be lost and it will result in the formation of tertiary amine. Finally, this tertiary amine reacts with RX and we will get quaternary ammonium salt. So this will be the product when it is reacted with alkylation. So this is exhaustive alkylation if we take alkyl halide in excess and in presence of heat, reaction takes place. After that, acylation. Acylation can be done by two ways. Have a look. Either by using acid chloride or by using acid anhydride. Say for example, R C double bond O, then O C double bond O, and then R. Now what will happen? What will happen over here? Have a look. Now instead of HCOR, that means acylation will take place of amine. Similarly here, acylation of amine will take place. So what will be the product? Product will be RNH, C double bond O and R. That means this is acylation of amine with HCl will be the product. Here, once again, acylation of amine will take place. And here, side product or another product will be R prime COOH. And this reaction generally takes place in presence of pyridine. Now, after this, reaction with chloroform, carbylamine reaction. Have a look. This is the reaction of, first of all, you must know this is the reaction of primary amine. Whether that primary amine is aliphatic, whether that primary amine is aromatic, when it is treated with chloroform in presence of base, say for example KOH, alcoholic potassium hydroxide. Remember, my dear lovely students, product will be RNC. I mean, say isocyanide will be obtained. And this isocyanide is having a very bad smell. That means foul smell compound, unpleasant odor compound is obtained. Because of this smell, you can distinguish primary amine from rest of the amines under the name carbylamine test or isocyanide test. Because this is isocyanide, carbylamine, isonitrile. So this can be known as isocyanide, carbylamine or isonitrile test. But remember, electrophile of this reaction is dichlorocarbene. This is the electrophile of the reaction. Because here nucleophiles are amines, or these amines will react with electrophile, and electrophile is the dichlorocarbene. But this is shown by only primary amine, but that too aliphatic as well as aromatic. Rest of the amines do not show this reaction. Next, reaction with nitrous acid. Have a look. If you are having aromatic primary amine, and if it is treated with nitrous acid in presence of excess acid, or you can say NaNO2 in presence of acid at a temperature of 0 to 5 degrees Celsius. Remember, 0 to 5 degrees Celsius, because if temperature is increased, then this salt is not stable. So this is benzene diazonium salt. Reaction is known as diazotization reaction. But if temperature is increased, remember, if temperature is increased, then if temperature is greater than 5 degrees Celsius, then we will get phenol. So remember, primary aromatic amine will form diazonium salt, and this is stable up to 5 degrees Celsius. So this is known as diazotization reaction. But if you take say for example an amine like this, primary amine, but primary aliphatic amine, and if this is treated with nitrous acid, if this is treated with nitrous acid at a temperature of 0 to 5 degrees Celsius, it first results in the formation of a diazonium salt. But remember, this diazonium salt is not stable. This is unstable. This is very unstable. So it does not need any higher temperature. At a temperature of 0 to 5 degrees Celsius, 0 to 5 degrees Celsius with water, it will result in the formation of a carbocation first. If that carbocation undergoes rearrangement, so rearrange that carbocation, and finally OH will be attached to that. That means alcohol will be obtained over here. But if you have secondary amines, whether it is aromatic, whether it is aliphatic, whether it is aromatic secondary amine, whether it is aromatic amine, say secondary amine like this, whether it is aliphatic secondary amine, or it is what we call aromatic secondary amine like this. Any amine, whether it is aromatic or aliphatic, both amines on treatment with secondary amines, on treatment with nitrous acid will simply form this one. Have a look. It will form NH and OH will be lost. That means nitrosoamine will be obtained. Nitrosoamine will be obtained. Water will be lost over here. Nitrosoamine will be obtained, and yellow oily compound, nitrosoamines are yellow oily compounds are obtained. Yellow oily compounds, nitrosoamines are obtained. That means aliphatic primary amine and aromatic primary amine can be distinguished because they react with nitrous acid differently, and they can be distinguished from, say secondary amines, but secondary aliphatic and aromatic amines cannot be distinguished with the help of this reaction. After that, my dear lovely students, if you are having a tertiary amine and that too aliphatic, then what will happen? Have a look. That will react with HNO2 and results in the formation of nitrite salt. This is water soluble nitrite salt. Results in the formation of water soluble nitrite salt. It will result in the formation of water soluble nitrite salts. But if we have aromatic tertiary amine, then what will happen? If we have aromatic tertiary amine, then what will happen? There will be electrophilic substitution reaction taking place at para position. Water will be lost, and we will get nitroso compound, and these nitroso compounds are generally green in color. So with the help of this reaction, we can distinguish primary aliphatic amine from primary aromatic amine, tertiary aliphatic amine from tertiary aromatic amine, or primary amine from secondary amine from tertiary amines, because these give different products. Hence, this is green in color, so green color compound is obtained. So with the help of nitrous acid, we can distinguish primary, secondary and tertiary amines. After that, reaction with Grignard's reagent. Have a look. If you are having, say for example, an amine, whether aliphatic, aromatic, if it is treated with Grignard's reagent, what will happen? Grignard reagent will accept this hydrogen, because this is acidic hydrogen containing compound. This is having negative part and this is having a positive part. In presence of dry ether, whenever Grignard's reagent react with any acidic hydrogen containing compound resulting in the formation of alkane, we know that reaction is known as Zarivatanov reaction. So this is once again a Zarivatanov reaction. After that, my dear lovely students, have a look. Reaction with carbon disulfide. If aliphatic amine, remember, if aliphatic primary amine react with carbon disulfide, and we warm it and followed by HgCl2, then what will happen? It will result in the formation of alkyl isothiocyanate. And it's having mustard oil smell. This is having mustard oil smell. That is why this reaction is known as Hoffman's mustard oil reaction. This reaction is known as Hoffman mustard oil reaction and is used as a test. It is used as a test to distinguish aliphatic primary amine, because this reaction is shown only by aliphatic primary amine, to distinguish aliphatic primary amine from rest of the amines, Okay. After that, reaction with carbonyl chloride, or this is also known as phosgene. This is also known as phosgene, a poisonous gas. So if it reacts with primary amine, it results in the formation of, have a look, it results in the formation of, this HCl will be lost, this HCl will be lost, so it will result in the formation of this one, alkylated urea, but symmetrical disubstituted urea. If it reacts with secondary amine, then it will form tetraalkylated or tetrasubstituted urea. Symmetrical tetrasubstituted urea will be formed. Tertiary amine does not have any hydrogen, so that will not react with phosgene. After that, aromatic electrophilic substitution reactions of amines. Now, this is the aniline or aromatic amine, and we know this aniline will give, nitrogen will give electron towards ring, and it's a very strong activating group, and it will increase electron density at ortho and para. That means such groups are ortho-para directing groups. That means NH2 group is ortho-para directing with respect to electrophile. And it is a very strong activating group. So halogenation, have a look. If aniline is treated with bromine water, electrophile should go to ortho or para. But here, what will happen? Have a look. It will go to all ortho and para positions. The reason is because NH2 is very strong activating. It has increased electron density of the benzene ring a lot. That's why 2,4,6 tribromo aniline will be obtained. 2,4,6 tribromo aniline is obtained, and it is having a white precipitate. But if we want only monobromination, then its electron donating nature towards ring should be, decreased. How to decrease? That is known as protection of amino group. So we will do protection of amino group. Or simply we will do protection. How to protect? Have a look. We will treat it with that group which will show acetylation of this. Say for example acetic anhydride. We will do acetylation first. Of this aniline first. Now what will happen? One of the hydrogens of aniline will be replaced by COCH3. Then CH3COOH will be lost over here. Now what will happen? One of the nitrogens of aniline will be replaced by COCH3. Now COCH3 is electron withdrawing group. Now it's electron withdrawing group. It decreases electron density of this nitrogen. Now it will not donate that electron electrons to that. It will donate now electrons towards ring, but not to that much extent, because it's electron withdrawing. It decreases electron density of this ring. Now after that, we will perform now our reaction. Our reaction was bromination. Now we will perform bromination. When we perform bromination of this reaction, bromine, Br positive, will go to ortho as well as para. But remember, ortho product will be minor, para product will be always major because of repulsion. So this will be minor product, but our major product will be like this, NHCOCH3. This is the actual product formed. This is the major product formed. This is the actual product formed. After this, what will happen? Have a look. What will happen? Now, finally, we will hydrolyze it. We will hydrolyze it. This bond will be broken, give H to this, OH to this. This bond will be broken, give H to this, OH to this. That means CH3COH will be lost. And finally, we will get two products. One is orthobromoaniline, minor product, and our main product or major product is parabromoaniline. Okay, this is the major product. This is the major product of the reaction. After that, we will be having another, and another reaction is nitration. Have a look. When aniline undergoes nitration, when it undergoes nitration, have a look, my dear lovely students, have a look, very, very important reaction. When it undergoes nitration, NO2 positive is the electrophile, and that electrophile should go to ortho or para. But what will happen over here? Have a look. It will go to ortho, but that product is only 2%. It will go to meta as well, which is something unusual. So it will form 47% meta product. Then it will also go to para. Now the question is, why meta product is obtained? This is very, very simple. Have a look. So this is 51%. Meta product is obtained because aniline in acidic medium accepts H positive. It accepts H positive and forms anilinium ion. Now, when anilinium ion is formed, this is meta directing. This is meta directing. That is why this meta product is obtained. Now the question is, why ortho is obtained lesser, meta more, and this say much more? Because this NH3 will withdraw electron because of inductive effect and decreases electron density more at ortho and less at para. That's why, as electron density is very much decreased at ortho, that's why nitronium ion will not prefer to go to ortho. It will prefer to go para, after that meta, after that say ortho. That's why this is the percentage. Now the question is, why this has been formed? Because aniline has strong donating power. That's why it donates electron to H positive. Now the question is, we want to decrease its donating power. That's why we have to protect this. That means we have to do protection. We have to do protection. Now have a look. If we want to protect this NH2, what will happen? We will do acetylation first. Suppose by using acetic anhydride, by using acetyl chloride. Now, when you use protection, what will happen? Instead of this H, COCH3 will come. That means CH3COH will be lost over here. Here, it will be like this. It will be like this. It will be like this. NHCOCH3 will be there. NHCOCH3 will be there. Have a look. NHCOCH3 will be there. COCH3 is electron withdrawing because of resonance as well as inductive effect. Now, this is electron withdrawing much because of resonance, and it decreases electron density of this ring. Now, it will not donate electron to H positive. Now, if we want to perform nitration, NO2 positive will now go to ortho or para, because it will not form anilinium ion now. So it will go to ortho or para. So major product will be from para. Major product will be from para. That's why we generally do not show ortho product. But here I am showing ortho product so that you will understand what actually can take place. It can take place, say nitration at ortho as well as para, but para one will be the major product. And finally, we will do hydrolysis. Then we will break this bond, give H to this, OH to this. We will break this bond, give H to this, OH to this. Then finally, CH3COH will be lost, and we will get two products over here. One is NH2, to that NO2 is at para, that means orthonitroaniline and paranitroaniline. But my dear students, the major product will be this one. Paranitroaniline will be the major product. Okay, after that, we will be having sulfonation. Sulfonation of aniline once again takes place in acidic medium, but remember, sulfonation is actually the reversible reaction. So when it takes place in acidic medium, what will happen? It will once again form an anilinium ion, and OSO3H minus will be attracted to this. Now it will form anilinium ion. That means electrophile SO3 or SO3H will finally go to ortho, meta and para, but it can go to meta as well. But Para is the most stable product. Para is the most stable product, thermodynamically stable product. We know that because para is having least, what we call hindrance, steric repulsion. Now, at a temperature of 453 to 473, all products are in equilibrium, and high temperature always favor thermodynamically controlled product. That's why meta or ortho, they will prefer to form para product. That's why para is the major product over here, and that is why here reaction will form like this. Product formation will take place like this. So Zwitter ion will form, a dipolar ion will first form, or you can say a Zwitter ion is formed, which are basically in equilibrium with its para product. I mean to say, sometimes it will lose H positive, it will gain. When it loses H positive, it becomes NH2, and it gains H positive, it becomes SO3H. Now, it will lose, it becomes SO3 minus, it will gain, it becomes NH2, NH3 positive. So this is para-aminobenzene sulfonic acid, commonly known as sulfonilic acid. So this is the major product of this reaction. This is the major product. And why major product is this? Because of high temperature. We know at high temperature, thermodynamically controlled product is the major product. After that, Hinsberg's method. Have a look. We have Hinsberg's reagent like benzene sulfonyl chloride. We have a primary amine, say for example RNH2. We have Hinsberg's reagent benzene sulfonyl chloride like this. We have a secondary amine like this. Hinsberg's reagent means benzene sulfonyl chloride, and we will be having a tertiary amine. But as tertiary amine does not have any hydrogen, so that's why tertiary amine does not have any hydrogen, so it will not react. It will not react during this reaction, so there will be no reaction. So there will be no reaction. But what will happen over here? HCl will be lost because this will attack as a nucleophile. It will attack as a nucleophile, and Cl will be lost, and then it will take H, so HCl will be lost. First of all, when primary amine or secondary amine reacts with Hinsberg's reagent, I mean say benzene sulfonyl chloride, both can form solid. Both can form solid. This will form N-alkyl benzene sulfonamide, a solid. This will form N-dialkyl benzene sulfonamide, which is also a solid. But dear students, when this is treated with alkali and this is treated with alkali, suppose alkali is KOH, alcoholic KOH, aqueous KOH is there. Take it. Now, what will happen? This base will abstract hydrogen and it will result in the formation of this product. That means solid which has been formed from primary amine, it reacts. That means it is soluble. It is soluble in what we call alkali. So this solid is soluble in alkali because it reacts with alkali. It is soluble in alkali. But here is no acidic hydrogen, so base will not react. That means there will be no reaction. So it does not react with base. That means this solid is insoluble. This is insoluble in KOH. So whose solid is soluble in KOH? Primary amines. Whose solid is insoluble in KOH? Secondary amine. So with the help of this, we can distinguish. We can distinguish what? Primary, secondary and tertiary amine. Distinguish. We can distinguish primary, secondary and tertiary amines with the help of Hinsberg's reagent. That's why this is known as Hinsberg's test. But remember, this benzene sulfonyl chloride is nowadays replaced. It's replaced nowadays by this one, para-toluene sulfonyl chloride. Para-toluene sulfonyl chloride, also known as para-tosyl chloride. Para-toluene sulfonyl chloride or para-tosyl chloride. Remember. After that, we will be having a diazonium salts. We will be having diazonium salts. I mean, say, this is the last portion of your 12th organic chemistry. So, diazonium salts. Now, first of all, diazotization reaction is there. So once again, what is this? This is the reaction of aromatic primary amine. Aromatic primary amine which on treatment with NaNO2 and acid, let me write down acid as HA, not HCl. Then it will form nitrous acid within the reaction, and HA is taken in excess at a temperature of 0 to 5 degrees Celsius. What will be the product? Product will be benzene diazonium salt, like this. Benzene diazonium, and then negative part will be of salt. Negative part will be of that acid, plus it will be twice H2. This is known as diazotization reaction. This reaction is known as diazotization reaction. And remember, this is very, very important point, that above 5 degrees Celsius, this diazonium salt is not stable. Diazonium salt is not stable. It is not stable. Now the question is, what is this HA? This HA can be HCl, it can be HNO3, it can be HBF4, means tetrafluoroboric acid, it can be H2SO4, means sulfuric acid. Now, so if it is HCl, this is benzene diazonium chloride. If it is HNO3, this is benzene diazonium nitrate. If it is HBF4, this is benzene diazonium tetrafluoroborate. If it is H2SO4, then it is benzene diazonium hydrogen sulfate. So this is diazotization. After that, we will be having reactions involving displacement of nitrogen. Have a look. If you are having this benzene diazonium salt. Now, there are few reactions which will replace this N2. Have a look. Suppose we want to replace this N2 by H. We want to replace this N2 by H. Remember the reagents. Reagent at that time will be H3PO2, phosphenic acid and water, or it can be ethanol. It can be ethanol. Number second, if we want to replace this N2 by OH, then very, very simple reaction. Have a look. How to replace N2 by OH is simply use water and temperature greater than 5 degrees Celsius. That means warm it. After that, my dear students, have a look. If you want to replace this by, say for example, halogen. For example, that halogen is chlorine or bromine. That means you want to prepare chlorobenzene or bromobenzene. Now, what you have to do is cuprous halide, Cu2X2, or you will write CuXHX. But remember, this X here is either chlorine or bromine. Similarly, you can use CuHX. Remember, once again, H in this HX, X is either chlorine or bromine. You will get chlorobenzene once again, or bromobenzene once again. This reaction is known as Sandmeyer reaction. And yield of haloarene here will be more. This is Sandmeyer's reaction. And yield over here, this is known as Gattermann reaction, is less. So in Gattermann reaction, yield of haloarene is less. And in Sandmeyer's reaction, yield is more. So Sandmeyer reaction is preferred over Gattermann reaction. Sometimes we want to replace this by cyanide. This is also known as Sandmeyer reaction. That means with the help of Sandmeyer reaction, we can replace this N2 either by chlorine or by bromine or by cyanide. So benzonitrile. After that, if we want to replace it by fluorine, for that we first treat it with HBF4, and it will result in the formation of N2BF4 minus. And then, my dear students, we can do two reactions over here. If we heat it, we will get fluorobenzene. Have a look. We will get fluorobenzene. Am I clear? We will get fluorobenzene. But if the same reaction is treated with NaNO2, same reagent, substrate is treated with NaNO2, then this N2 will be replaced by NO2. That means we will get nitrobenzene at that time. N2 will be lost over here, N2 will be lost over here. This reaction is known as Bals-Schimmeln reaction. Sometimes, have a look, either by hydrogen or by hydroxyl, or by halogens, or by cyanide, or by nitro, or by Na3ASO3. Have a look. This is known as sodium arsenide followed by acidification. Now, what will happen? This N2 will be replaced by ASO3H2 group. This is known as arsenic acid group. ASO3H2 is known as arsenic acid group, and this reaction is known as Barth reaction. This reaction is known as Barth reaction. Sometimes we will replace this N2 by aryl group. For example, in presence of NaOH, what will happen? This C6H6 will lose H positive and C6H5 will replace, I mean to say, this one, and we will get a product like this. This reaction is known as, by the way, here N2 will be formed, N2 will be lost. This is known as Gomberg-Bachmann or Bachmann reaction. So, these are the reactions with the help of which you can replace N2 by any monovalent atom, whether it is H, OH, chlorobenzene, bromobenzene, cyanide, whether it is, fluorobenzene, whether it is fluorine, whether it is, NO2, whether it is ASO3, H2, that means arsenic acid, whether it is aryl, you can replace that. Now, there are few reactions where this nitrogen is retained. For example, you are having this one. N triple bond N with a positive charge on this and Cl having a negative charge, and you want to do those reactions in which this nitrogen is retained, then we will do simply reduction with SnCl2 HCl or Na2SO3. On treatment with this, what will happen? It will result in the formation of this one, NH2, N-phenyl hydrazine. So have a look, nitrogen is retained over there. But remember, if same benzene diazonium salt is treated with more vigorous reducing agent like zinc in HCl, then it will first form this and then it will undergo further reduction. So it will undergo further reduction because it will not stop over here, as this is the strong reducing agent or a vigorous reducing agent. It will further reduce this one and break N double bond, N single bond N, and it will result in the formation of this. It will result in the formation of this one, aniline. Okay. After that, we will be having another reaction in which nitrogen is retained, and that is coupling reaction. Have a look. This is an electrophilic substitution reaction. This is N double bond N, positive Cl minus. Now, if it is treated with aniline, it reacts like that of phenol, but phenol was reacting at, in basic medium, but this aniline reacts with this in acidic medium. Now, what will happen? This will attack, this electrophile will attack parapulsion of aniline like that of parapulsion of phenol, and it will result in the formation of N double bond N, and then it will be like this. So we will get here 4-amino azobenzene. This is also an azo dye, but its color is yellow. So we will get yellow dye over here. So coupling takes place at parapulsion, but if para is blocked, if para is not having H, if any other group other than H is there, then this coupling will take place at what we call ortho position. So this was all about amines. Now let's do previous year questions. So are you ready for that? Let's do previous year questions. Are you ready? Are you ready for previous year questions? Come on, let me know quickly. Let me know quickly, my dear lovely students. Are you ready? Are you ready? So you have to answer me. You have to answer me then. You have to answer me then quickly. You have to answer me then quickly. Okay, let's do. Because time is running very fast. Now, first of all, we have this question. Question is like this. Have a look. Let me see that if this reaction is visible or not. Yes, this is visible. This is visible. Now, which type of reaction is this? Phenol on treatment with base NaH. H minus will replace this H, and this is replacement, and this will form O minus Na positive. Now, when it forms O minus Na positive, then it reacts with this. That means alkoxide will attack this, and it will be a normal SN2 reaction. So this is Williamson synthesis. Yes, Williamson ether synthesis, not alcohol synthesis. This is Williamson ether synthesis, this one, because ether has been formed, not an alcohol. Now after that, my dear lovely students, Is this clear? Is this clear? Is this clear? Is this slide clear to you? Let me know quickly. Okay, this is also clear to you. This is also clear to you. After this, now the question is, for the following reactions, this reaction is elimination, this reaction is substitution, this is addition. So A is elimination, B is substitution, and C is addition. So this is option number 2. This is very simple reaction asked in your, say AIMT or NEET examination. Consider the reaction. This reaction, as this is a strong nucleophile, though this is SN2 reaction. So this is SN2 reaction. SN2 reactions are favored by, remember, polar aprotic solvent. So NN-dimethyl formamide. So DMF, dimethyl formamide, will simply favor this reaction. So this will be fastest in this. Now after that, benzene diazonium chloride. Have a look, have a look. It is benzene diazonium chloride. It is benzene diazonium chloride. On treatment with Cu2Cl, Cu2Br2 and HBr. That means this is Sandmeyer reaction in which we will get bromobenzene simply. We will get bromobenzene. After that, second is on treatment with magnesium in presence of dry ether. What will happen? Magnesium will incorporate between Mg and Br. That means C and Br. So it will form phenyl magnesium bromide. So this is Grignard's reagent. This is the negative part. This is the positive part. Now, on treatment with water, what will happen? It will act as a base. It will abstract this H and it will result in the formation of benzene. So benzene will be the product. Benzene will be the major product of this reaction. Benzene will be the major product. After that, the compound that will undergo SN1 reaction with fastest rate. Remember, rate of SN1 is directly proportional to stability of the carbocation. So just remove. You cannot remove this. You cannot remove this. Why? Because this is very strong because of partial double bond character as a result of resonance. This is what we call a carbocation, which is very stable because of resonance as well as inductive effect and hyperconjugation as compared to this. So this will show SN1 very fast. After that, major product A and B are formed in the following reaction. Reaction is like this. Reaction is like this. This is the reaction. This is the reaction. Substrate is this. And here OH is there. And after that PBr3. PBr3. What will happen? What will happen over here? PBr3 will replace OH and Br will go there. So this is the product. After that, this is A. This is A, major product. After that, it is treated with alcoholic potassium hydroxide. Remember, whenever it is alcoholic potassium hydroxide, it is an E2 reaction. So this is alpha, this is beta, this is beta. So remove hydrogen from that beta which form more stable product, sets a product. So this will be the major product. So it will result in the formation of this one. So this will be RB. This is B. B is the major product. Now tell me. What is A? What is B? A is Br and B is having double bond over here. That means it is this one. It is this one. Am I clear? Am I clear? It's not 4. It's not 4. It's not 4. It can form double bond over here or here. This is Sadza product. This is Hoffman. Sadza here is major product. Okay. After that, identify the major product C formed in the following reaction. Have a look. First of all, NaCN. This will attack this and I will be replaced. That means A is CH3, CH2, CH2 and then CN. Now, this is CN on partial hydrolysis. That means convert CN into CONH2. That means amide. So it is CH3, CH2, CH2. Then it is CONH2. That means it is amide. Now, after that, NaOH-Br2 means Hoffman bromamide reaction. Remove this and C will be CH3, CH2, CH2. And finally, it will be NH2. That means one carbon lesser than amide. So it is propylamine. Is any propylamine there? Yes. Option number 3 is the right answer. After that, among the following ethers, which one will produce methyl alcohol on treatment with hot concentrated HNO3, hot concentrated HI? Have a look. This will undergo SN2 reaction. I will go to this. That means I will go to this, H will go to this. I have already shown this reaction. Similarly, I will go to this, H will go to this. Here, I will go to this, H will go to this. But this is tertiary on one side. That means I will go to this and H will go to this. In which case methanol is prepared? Methyl alcohol is prepared in fourth case. So this is the product of this reaction. The heating of methyl phenyl ether. Methyl phenyl ether is this. This is phenyl, This is methyl phenyl ether. With HI produces, remember whenever you are having, say oxygen attached to benzene ring, break this one, give hydrogen to this, one of the products is always phenol, and another product will be X, will go to this. Now, reaction says that if it reacts with HI, then X is I, so it will result in the formation of methyl iodine and phenol. Ethyl chloride, it will be not formed, iodobenzene will not be formed, phenol will be formed. Yes, phenol is the right answer. After that, the compound A on treatment with sodium gives B. Then B with PCl5 gives C. B and C react together to give diethyl ether. A and B are. So have a look. If this is A, it will react with sodium, will form sodium ethoxide. That means it is not the case, it is not the case, it's not the case, it is the case. So this is simple. When it reacts with sodium, it gives B. And this B, it gives B. And when it reacts with PCl5, it gives C. Yes, so A and B are, it's these two. Simple, very simple. After that, identify major product P, Q and R in the following reaction. Have a look. Reaction is like this. This is very easy. Organic chemistry is very easy. But you have to remember, you have to revise organic chemistry very much. You have to practice organic chemistry every day. Now, what will happen? It will result in the formation of, first, it will result in the formation of this one, CH3CH2. Let me write down CHH as CH2. Then CH2 positive. This will be the carbocation first formed. Then hydride shift will take place, 1,2H minus shift will take place. Then it will form CH3CH positive, then CH3. When this is the carbocation, it will attack this benzene, hence we will get cumene or isopropyl benzene. So isopropyl benzene or cumene is P. Now, after that, this on treatment with O2 and H3, this on treatment with O2 followed by hydrolysis and heat gives Q and R. We know. Upon oxidation, they will first form cumene hydroperoxide. We know this. And finally, cumene hydroperoxide will form phenol and acetone. So let me write down phenol and acetone finally. So the product is, one is phenol, another is acetone. So what are the options now? Are there any option having phenol and acetone? Phenol and acetone and isopropyl benzene. It's the fourth option. After that, another question is, same question. Say reaction is same. That means have a look. This is asked twice. Same reaction is asked twice. It's like this. O2. You have to say what is this A. And this upon acidification or hydrolysis. Acidification or hydrolysis. It results in the formation of phenol and acetone. Now the question is, what is this A? We know this A is cumene hydroperoxide. This A is like this, cumene hydroperoxide. This is cumene hydroperoxide. This is A. Have a look. This is A. That means it is this one. After this. What is the IUPAC name of the organic compound formed in the following chemical reaction? Acetone. Have a look. This is acetone. This on treatment with CH3CH2 MgBr dry ether. MgBr and dry ether. First results in the formation of, this is negative part, this is positive part. This negative part will act as a nucleophile. It will attack this and it will break. So it will result in the formation of CH3CO minus MgBr positive. This is CH3 and this is CH2CH3. Have a look. This upon hydrolysis will result in the formation of CH3C. This is OH, this is CH3, this is CH2, then CH3. Our parent chain is this. So this is 1, 2, 3, 4. So this is butane and all. So butan 2-ol and 2-methyl butan 2-ol. 2-methyl butan 2-ol is the right answer. This one. Very good. After that, given in Lucas test, primary, secondary and tertiary alcohols are distinguished exactly on the basis of reactivity. That's correct. Primary alcohols are more reactive. No. Statement 1 is correct. Statement 2 is wrong. Statement 1 is correct. Statement 1 is incorrect. Statement 1 is correct and sorry. I have given. Okay. Statement 1 is correct, but statement 2 is incorrect. This one. Third option is the right answer. First is correct. Statement second is incorrect. After that, another statement question. Acidic strength of mono-substituted nitrophenol is higher than phenol. Yes, because of electron withdrawing group. That's exactly correct. But orthonitrophenol, metanitrophenol and pentanitrophenol have same acidic strength. That's correct. That's incorrect. Statement 1 is correct. Statement 2 is incorrect. That means this one. After that, you have to, say match. First is, when phenol is treated with NaOH, CO2 and H positive, we get salicylic acid. When phenol is treated with aqueous NaOH, chloroform and H positive, we get salicylaldehyde, and reaction is known as what we call Remer-Timmer reaction. When phenol is treated with zinc dust, we get benzene. Yes, very easy question. So first, A gives, let me write down over here, A is, salicylic acid, that means 4. B is salicylaldehyde, that means 3. Then C is benzene, that means 2. Obviously, D gives benzoquinone, that means 1. A4, B3, C2 and D1. A4, B3, C2, D1. It is second option. A4, B3 and C2, D1. After that, which one of the following sequence is incorrect method to prepare phenol? Now have a look. Cumene followed by oxidation followed by hydrolysis. Cumene can be prepared. Chlorobenzene, NaOH. But this is NSTP, normal temperature and pressure. No, this can never be formed because we can simply form phenol from chlorobenzene by nucleophilic substitution, and haloarenes generally do not show nucleophilic substitution under normal conditions. They undergo nucleophilic substitution only and only under drastic conditions. That is why this cannot form. Okay, phenol on treatment with H2SO4, oleum. H2SO4 plus SO3, that means it is benzene sulfonic acid followed by NaOH. Yes, it can form. And then aniline NaNO2. Yes, this can also form because first it will form benzene diazonium salt that upon heating will simply decompose and results in the formation of phenol. Okay. Consider the following reaction and identify the product. Now, have a look. You have to find out the product of this reaction. You have to tell me the product of this reaction. What will be the major product of this reaction? Have a look. This is HBr. What will happen? This lone pair will attack H. Br will be lost. So first of all, we will get OH2 with a positive. That means a good leaving group is formed. Then this leaving group will be lost and we will get a carbocation. When carbocation is formed, it will undergo rearrangement like this. Carbocation will go rearrangement like this. So this hydride shift will take place. That means 1,2H minus shift takes place. And it will result in the formation of CH3 positive and CH2 Finally, Br will be attached to this. Now, that means our product will be 2-bromo-2-methyl-butane. 2-bromo-2-methyl-butane. It's first one. After that, okay, this is the reaction. This will be broken. Simply give, I to this and H to this, because one of the products will be always phenol if O is directly attached to benzene ring. So now it is CH2I and phenol. CH2I and phenol. Is there any benzyl iodide and phenol? Yes, this is the right answer. After that, which one of the following alcohols reacts instantaneously with Lucas reagent? Remember, Lucas reagent, that alcohol can react immediately, which can form most stable carbocation. Among primary, secondary and tertiary alcohol, it's tertiary. But it's not always necessary it's tertiary. But if it's primary, secondary, tertiary alcohols, among them it's tertiary. Otherwise, form a carbocation. Any alcohol which forms most stable carbocation shows, this turbidity immediately. Now, this is primary alcohol, this is tertiary alcohol, primary alcohol, secondary alcohol. Obviously, it will be a tertiary alcohol. After that, The products A and B obtained in the following reactions respectively are. Okay. When ROH reacts with PCl3, it gives RCl plus H3PO3. That means H3PO3 will be A. A will be H3PO3. Another. When ROH reacts with PCl5, it gives RCl, HCl and POCl3. That means B will be POCl3. So H3PO3 and POCl3. So it will be H3PO3 and POCl3. Because A is H3PO3, B is POCl3. That's why this option, not this one. After that. Reactivity by which benzaldehyde cannot be prepared. It will be this one, because zinc amalgam will never react with benzoic acid. This is Itard's reaction. It will form benzaldehyde. This is what we call Rosenmund's reduction. It will form benzaldehyde. This is what we call Gutterman-Koch reaction. It will form benzaldehyde. After that, of the following, which is the product formed where cyclohexanone undergoes aldol reaction? Have a look. This is cyclohexanone. Self-aldol. You can form cyclohexanone like this. Now, replace these two hydrogens, remove these two hydrogens and form a double bond. So, it will result in the formation of a product like this. It will form a product like this. I mean, say in which double bond and C double bond are in conjugation. That means it is this one. It is this one. After that. Okay. Now, this A on treatment with this shows silver mirror test. That means it should be an aldehyde. If it is an aldehyde on treatment with alcohol, on treatment with copper, hot copper gives aldehyde. That means it should be a primary alcohol. If it is primary alcohol having C2H6O formula, that means CH3CH2OH, that means it should be ethanol. So X is ethanol, this is ethanol. X is ethanol, X is ethanol, and A is ethanol. A is ethanol, X is ethanol. Yes. Then after that, this undergoes ethanol. Ethanol is this one. Ethanol is this one. It undergoes. This is CH3CHO, CH3CHO. It will undergo aldol condensation because it is OH minus and heat. So Y will be CH3, CH, double bond CH, single bond CHO. So it will be simply 1, 2, 3, 4. It will be bit to enol. So why is that? So A is ethanol. Yes, this is the right answer. And this is semicarbazide because this is semicarbazone. On treatment with semicarbazone, it will give semicarbazone. With semicarbazide, it will give semicarbazone. Okay, so this is yes. Third option is the right answer. Reaction between benzaldehyde and acetophenone. Have a look. This is benzaldehyde without alpha hydrogen. And this is acetophenone. This is acetophenone with alpha hydrogens. This on treatment with dilute NaOH. This is simply different types of carbonyl compounds containing at least one carbonyl compound contains at least 2 alpha hydrogens. So this is aldol condensation, but cross aldol. So this is cross aldol condensation. Okay, after that, which of the following acid will form an anhydride on heating and acid imide on strong heating? Obviously, it will be this one, phthalic acid. Because if phthalic acid is heated, it will lose water molecule and form anhydride. But if it is treated with first ammonia, it will form CONH4, and after that it's strongly heated, it will give phthalimide. So it is this one. Okay. After that, identify A in the following reaction. A gives this one, and this is Rosenmund reduction. So this is benzoyl chloride. This is Rosenmund catalyst. So benzoyl chloride. Simple. Very simple reactions are there. Very simple questions are there. Okay, have a look. Very, very good question is this. This is a very good question. CH2, C double bond O, OCH3, NaBH4. You have to show the product. You know, NaBH4 cannot reduce ester. It cannot reduce ester. Let me write down over here. Only NH4 is this because I cannot understand what that is. Was that clear? What is this? No, it's not clear. So, this is NaBH4. Let me write down over here, if this is NaBH4. If this is NaBH4, now we have to tell what will be the product. We know it cannot reduce ester, it will reduce this to alcohol. So which of the following is the option? Ester remains as it is, other groups remain as it is, only C double bond O will convert to alcohol. After that, match benzene COHCl and anhydrous AlCl3COCl3. This is what we call Gattermann-Koch reaction. So A is 2. So A is 2. Gattermann-Koch. After that, this is haloform reaction. So B is 3. B is 3. RCH2OH and acid. This is known as esterification. So C is 4. And then D is Haloalkanes reaction. That means 1. So have a look. So A2B3. A2B3 C4 D1. So fourth option is the right answer. After that, okay, CH3, I mean toluene on treatment with chromyl chloride. Question is like this. Toluene. Question is this. Have a look. Toluene on treatment with CrO2Cl2. That means chromyl chloride in CS2. What will be X? You have to tell me this. This is X. This is very simple. It will result in the formation of CH, and then after that you can write down OCrOHCl2 whole 2. This is the brown complex. So this is X. You have to find out this. So our option will be OCrOHCl2 whole 2. It's this one. First one. After that, RMGX on treatment with carbon dioxide. This is RMGX. This is OCO, carbon dioxide. This is negative part, this is positive part. Negative part will attack this, it will be lost in presence of dry ether. What will be the product? RC double bond O, O minus, and then MgX. So this is RY, RCO minus MgX. This is the Y. After that, which one of the following is not formed when acetone reacts with 2-pentanone in presence of dilute NaOH? Have a look. Acetone is this one. CH3 C double bond O. CH3. Now, pentan 2-on or 2-pentanone means this one. Now, question is, which cannot be formed if these undergo, say aldol reaction? Very simple. Have a look. Cross aldol. Break this bond. As this part is having already double bond O, give 2 hydrogens to this and give oxygen to this. This is acetone and acetone. This can be formed. Break this bond. As this part is already having oxygen, give hydrogens to it. That means 1, 2, 3, 4, 5. This is propan 3-on. This is propan 3-on, but we don't have propan 3-on here. That means this cannot be formed. Have a look. Break this bond. Give H2 to this. This is acetone part. Give oxygen to this. This is pentanone. That means this can be obtained because reactants are this. Break this bond. Give 2 hydrogens to this. Oxygen to this. This is acetone. And this is 1, 2, 3, 4, 5. Pentan 2-on. That means this can also be obtained. But this can never be obtained. So this is the right answer. After that. Okay. This is simply a nucleophilic addition reaction in which cyanohydrin is obtained, but on treatment with OH, when OH is treated with H2SO4, it will be lost and a carbocation will be formed and a double bond will be formed over here, and then water in presence of acid will hydrolyze this CN to COH. That means double bond will be here and CN will become COH. This will be 4, option number 4. Simple. Okay, zinc, mercury, identify product A in the following reaction. This is C double bond O of ketone, this is of ketone. Now, what will be the product? Product will be simply CH2, CH2, that means this one. This one. Product will be this one. After that, identify final product D obtained in the following reaction. Now, first, CH3CHO on treatment with this one, lithium aluminum hydride, this will become CH3 CH2 OH first. On treatment with H2SO4, it will undergo intermolecular dehydration. So it will result in the formation of ethene. This ethene on treatment with HBr, this is HBr. What will happen? It will result in the formation of ethyl bromide. This is alkyl halide, this is aryl halide, this is Wurtz-Fittig reaction. So it will result in the formation of ethyl benzene. Ethyl benzene will be the major product of this reaction. That means this one. After that, okay, very good question. This is Tollens reagent. This is ketone, this is aldehyde. Aldehyde is oxidized, Tollens reagent cannot oxidize this ketone, so ketone remain as such. That means ketone remain as such, CHO is converted to CO minus. This is the product. Then, Fehling solution A is aqueous copper sulfate solution. Aqueous copper sulfate solution. After that, KMnO4, but it is strong oxidizing agent. Remember, it will break this and it will convert this CH to COH. It will convert to this CH to COH. That means cyclohexane carboxylic acid will be the product. Cyclohexane carboxylic acid will be the product. If it is Bayer's reagent, then double bond will be converted to single bond, then OH, addition of OH will take place. But this is strong oxidizing agent. This is not Bayer's reagent. In the following reaction, okay, that's very good. You have to replace this N2 by H. So what are the reagents? H3PO2 water or ethanol? H3PO2 and water. Ethanol is not given, so this is the option. This is the option. After that, nitrobenzene on reaction with concentrated HNO3. Generally, nitrobenzene is already having an electron withdrawing group, so its further nitration is not generally possible under normal condition because it's an electron withdrawing group. It deactivates the ring. But at higher temperature, reaction can take place. At higher temperature, reaction can take place. And what is the electrophile of the reaction? Nitronium. And nitronium ion goes to meta position because this is meta directing group. So 1,3-dinitrobenzene. 1,3-dinitrobenzene is obtained, but at high temperature. Otherwise, reaction will not take place under normal conditions. Okay. This is nitro, NO2. Okay. So 1,3-metadinitrobenzene will be the product. Which of the following reactions is appropriate for converting acetamide? Acetamide means this one. To methanamine. Methanamine is this one. So what is the difference? Have a look. This C double bond O has been removed. So which reaction converts primary amide to primary amine with one carbon lesser? Hofmann bromamide reaction. Hofmann bromamide, Hofmann hypobromide. So this is the reaction. Hofmann bromamide, Hofmann hypobromide. You can write down anything. Hofmann rearrangement. Okay. COH, NH3 strong heating. This is phthalimide. Remember, this is written in, say your NCERT textbook. So this is phthalimide. Okay, which of the following amine will give carmylamine test? Primary amine, whether aliphatic or aromatic. It is this one. This is secondary amine. This is tertiary amine. This is secondary amine. This is what we call secondary amine. So these will not show. Primary amine will show this reaction. Okay. Now, identify the compound that will react with Hinsberg's reagent to give a solid which dissolves in alkali. Primary amine forms solid and after that it dissolves in alkali. So we have to find out primary amine. That means this one. This is nitro. This is secondary amine. This is tertiary amine. No. So primary amine is the answer. After that, statement 1. I will read statement. Primary aliphatic amines react with HNO2 to give unstable diazonium salt. Yes. Primary aliphatic amines form diazonium salts but unstable. Primary aromatic amine can form stable diazonium salt. So this is correct statement. Primary aromatic amine react with HNO2 to form diazonium salt. It is true up to this. But which are stable even above 300 Kelvin? No. Up to 298 Kelvin. 5 degrees Celsius. That means up to 278 Kelvin. It is stable. But after that it is not stable. That means statement second is wrong. But statement first is correct. So statement first is correct. But statement second is incorrect. It is option number 4. After that, it is benzonitrile. Upon treatment with lithium aluminum hydride, it will first result in the formation of this. It will form CH2NH2 first of all. CH2NH2 because cyanide forms primary amine. Now, after that, it is treated with NaNO2 HCl. And it will form, as this is aliphatic primary amine, it will form. It is not directly attached to this ring. So it will form unstable diazonium salt. So finally it will form alcohol. Remove NH2, form a carbocation and to that carbocation give OH. So it will form alcohol. it will form alcohol. It will form alcohol, benzyl alcohol. Benzyl alcohol means benzene CH2OH. That means this one. This one. After that, which of the following reaction will not give primary amine as the product? This is Hoffman bromamide reaction. It will give primary amine. This is, say lithium aluminum hydride, cyanide, it will give primary amine. Isocyanide will give secondary amine, so it will not give primary amine. This is reduction of this, it will also give primary amine. So which will not give primary amine? It is isocyanide. Reduction of isocyanide will not give primary amine. Aniline does not undergo Friedel-Crafts alkylation reaction. Have a look. Aniline will not show Friedel-Crafts alkylation reaction. Why is it so? Is it true or not? We know Friedel-Crafts alkylation reaction takes place in Lewis acid, and if it reacts with Lewis acid, we know this is strongly donating group. It will result in the formation of this complex in which nitrogen acquires positive charge. When nitrogen acquires positive charge, it will withdraw electrons away from ring. That means it deactivates the ring. Hence, it will not show, say electrophilic substitution reaction, which is known as Friedel-Crafts alkylation or acylation. That means statement 1 is true. Aniline cannot be prepared through Gabriel thalamide synthesis. That is also true. In the light of above statements, choose the correct. Statement 1 is correct. Statement 2 is false. No. Statement 1 is incorrect. No. Both statement 1 and 2 are true. Yes, that is true. Both are true. Both are true because it cannot react during Friedel-Crafts alkylation or acylation. Number 2, aniline is not obtained during Gabriel thalamide synthesis. So, my dear lovely students, this was all about today's session. So thank you all once again from the core of my heart for your patience and so much of love that you showed to us. God bless you all. My prayers are always with you, and I want you all to be in GMC in 2026. I hope you loved the session. Everything is revised. I have already told you at the beginning that biomolecule will not be possible today, but I will record biomolecule for you, that is for sure. I will record that for you, and that is for sure. That is for sure. That is for sure. Now, after all this, I will be waiting only for one thing from you, and that thing will be only after end of the session, I will be checking comments of you that I will be waiting for the comments from which place you are watching, number 1, and number 2, write down your name, and in front of that name, that means in prefix, write down doctor. 1, you have to write down your name and write doctor. After that, write down your name. 2, from where you were watching this session. And number 3, how much you like today's session. So this is all about today's session. We'll meet soon in next session. Till then, take care and good night to all of you. Take care. But listen carefully. After end of the session, I will be waiting for your comments. I will be waiting for your comments for sure. So take care. Bye-bye.